All right. Hello, everyone. Welcome to our workshop. There is the fourth workshop of open world, namely visual perception and learning the open world. My name is Shu. I'm one of the organizer in this workshop. So first, I want to welcome you to this workshop. I hope everyone is safe and healthy. The goals of the workshop is to connect people and exchange ideas about the open world vision, and we should discuss new opportunities and challenges about the open world. This is a hybrid workshop. We have on-site participants, so please enjoy and involve by asking questions. And we also have an online Zoom link provided by CVPR conference. The schedule is like this. You can search open world learning on the website to find the link to the workshop website. We have 4 challenges listed below. You can refer to the agenda and come over whenever you like. I want to thank all the speakers, organizers, advisors, coordinators. We have smiling faces of them, so you can say hello to them and they will greet you as well. First, I want to introduce the open world a little bit. Firstly, we emphasize testing in the open world, but we still train models in a closed world. For example, we have an open set recognition, which means that we train models on some closed set, and we emphasize that we have a never before seen novel examples in the testing scenario. That's why we have to detect the novel stuff. And later we have an open world recognition, which emphasize, we should not only detect the novel species, but also do some continual learning for the novel species with human annotation in the loop. These are the old days, but now I want to make an argument that we nowadays train that open world. For example, we sample data from the open world for better open set recognition, where we sample outlier data or outlier exposure to train better models to detect a never before seen novel species. And I want to claim that foundation models are actually pre-trained in the open world. For example, CLIP. With the open world models or foundation models, we can do open vocabulary recognition. We can do zero-shot recognition, so on and so forth. But here we want to think, okay, we train foundation models in the open world. Can we predict testing performance with the distribution shift? Given that we train in the open world represents some data distribution, but in a downstream task, we have some distribution shift. Can we predict the performance? I want to remind people that this is actually an established problem, which we call, we train in some in-distribution data, for example, ImageNet, but we test on some domain shift data or out of distribution data, ImageNet V2. So can we do this? Can we predict the performance? Actually, people report that we can. We report accuracy on the line observation, meaning that empirically we see OOD performance is strongly correlated with the in-distribution performance for a wide range of models and distribution shift. But here I want to remind people that the models tested in this scenario are trained in a closed world, and we wonder, does this conclusion still hold if we test the open world data, open world models? And here we tested 75 models, including vision models, vision language models trained in either the closed world, i.e. ImageNet, or the open world, which represent data from the internet. And if we draw this line again, and we do the scatter plot, we see that accuracy on the line does not hold anymore. But we see another interesting metric, LCE, or least common ancestor. If we use that metric to draw the scatter plot, we see LCE is on the line, no matter what model we train or in what scenario, open world or closed world. But here, I want to quickly explain why the intuition is that if a model can make better mistakes measured by LCA, it can mitigate a spurious correlation, leading to better generalization. This is a work published by our group at the ICML. Okay, and here we see that, this is a very exciting scenario, a very exciting conclusion that we can predict open world models on any downstream task. But if we dive into some failure cases, we see some interesting examples. For example, I work on species recognition. I threw in some species names like this one, Panana citrina, and I asked the GPT-4 to describe the visual features of this species, but GPT-4 fails. This is surprising because we can sort of believe that GPT-4 is already trained in the open world using all the internet data, which OpenAI can obtain, right? But why it fails? If you search Google, you actually can see some examples and some descriptions in this website. Why it still fails? My hypothesis is that some concepts, especially scientific names written in Latin, are too few in the open world to train models. But how to justify this? We count. How we count? We use some open source pre-training data set like ln 2 billion, ln 400 million. If we count, we see that, okay, the Latin scientific names are actually very few sampled in the open world. This is not the end of the world. This is not we have some tricky remedy like this. Given a scientific name for zero-shot recognition, we translate the scientific Latin name to English common name, and we use the English common name in the prompts to prompt the pre-trained foundation model or vision language model to do zero-shot recognition. If we do so, we can significantly boost the zero-shot recognition performance, that is zero-shot accuracy on 2 data sets. As name is the scientific name prompt, common name, this is the same name, right? This is interesting. And we want to test more data with diverse foundation models. For example, I threw in this image, which is a night snake. Night snake is a category listed in ImageNet, and we ask the question, ask GPT-4 and some other foundation models, what is the species name of this animal in the photo? And none of the foundation models can answer this question correctly. And we also ask DALL-E 3 to generate a photo for a night snake, and they fail. This is, again, very, very surprising. My hypothesis is that certain concepts are insufficiently presented in the open world. Examples related to these kind of concepts are very few to train a good foundation model. So we have some evidence to show this. We have a way to measure the concept of frequency in the open world. And here we use the measure. I will describe how to measure the concept of frequency. Just imagine that we have the measure, and we can draw this curve, which is a concept of frequency in the ImageNet. We sort them from low to high. This is the imbalanced distribution of very obviously. And we also draw this kind of a curve, which is a zero-shot accuracy for the ranked class names. And we see a strong correlation between the concept of frequency and the per concept accuracy. This is a kind of evidence showing that certain concepts are just a few in the open world to train reliable foundation models. Okay, now I want to show you how to measure concept of frequency. Of course, we still count. Intuitively, we can count the occurrence of pre-training tests related to the concept of interest. But here we have a challenge. Pre-training data is a large scale. We have billions of training examples. So how to do a reasonable measure? Here we use string matching. String matching is quick, is efficient, but we have two more limited hurdles. The first one is the lexical variation, i.e., there are some synonyms. For example, for the running shoes, we have other names like sneakers, trainer shoes, so on and so forth. A second hurdle is that the linguistic ambiguity. Just remember that we use string matching. We want to find tiger, but we still have other sort of non-tiger examples like tiger shark, tiger woods. Obviously, the latter two are not a tiger animal. So how to address this issue? We come up with this flowchart, this pipeline. To deal with the lexical variation, we ask a large language model to list the synonyms for concept of interesting. This one is a tiger. We ask the question, what are the common names or synonyms referring to tiger? And the large language model can give us some candidates, and we use all the candidates to search the relevant pre-training text using string matching here. And later on, we use the same language model to filter out irrelevant captions. For example, we ask this question, does this concept in the caption referring to tiger? And we can filter out some ambiguous, irrelevant captions. This enables us to reliably measure the concept of frequency. By doing so, we can draw the curves and show the strong correlation between the concept of frequency and the per concept zero-shot accuracy, justifying that some certain concepts are just a few in the open world to train foundation models. There are some interesting insights. For example, if we do zero-shot recognition, we can translate the given concept name to its most frequent synonym in the prompt. If we do so, we can significantly boost the zero-shot accuracy. Another insight is that we can do retrieval augmented learning. I just want to give people a little background. There's another paper published last year called ReACT, which is the state-of-the-art retrieval augmented learning method for zero-shot recognition. Basically, if we care about one concept, we can search relevant examples on the internet or in the pre-training data set of a vision language model. And after we retrieve a bunch of examples, we can train a new model for recognition. Here, people just use the original concept name. But now we know there are some synonyms or other common names. If we use all the common names or synonyms to do the retrieval, we can retrieve more relevant data and train better models. That is our method. Now we use all the synonyms for retrieval augmented learning. We can outperform the state-of-the-art ReACT by a large margin. And I want to remind people that when they do retrieval, they compute image features or text features, but we now use string matching, which is pretty fast. By doing so, we can reduce the computation cost significantly by orders. All right. Another insight is that we can use the most frequent synonym in image generation. For example, here, if we want to generate an image for bank swallow, we can, of course, ask DALL-E 3 to generate a photo of a bank swallow, but DALL-E 3 can fail because we know the reason. Bank swallow is not commonly represented or presented in the open world. That's why DALL-E 3 fails. But now we can find its most frequent synonym, which is the Saint Martin. If we replace bank swallow with the Saint Martin in the prompt, we can let DALL-E 3 generate the correct image. This is our paper. We will present the paper later in the conference, so please come over and discuss with us. All right. I want to conclude my very short talk with three remarks. The first one is that foundation models are open world models. We train models in the open world, and yeah, that's pretty cool. And the second remark is that open world models have open issues. The open issues are mostly related to open world data. For example, the data is long-tailed distributed. It has some domain shift, so on and so forth. All right. That's all about my introduction. So I hope everyone enjoyed the conference, enjoyed the workshop. So Nihar, please take over.
Great. Thanks so much, Xu. All right. Walter, why don't you come up? Our first talk today will be from Professor Walter Scheer, who is a professor at Notre Dame. He's been doing many pioneering works in open set recognition, and he's been leading the field for more than a decade. So today he'll be presenting his talk, Open Issues in Open World Learning. And I think this will be a very exciting talk. So please, Walter, take it away.
Learning. And so I want to talk about to continue working on. So I'm going to talk about some of these that are sort of the most salient things I think we should all be thinking about. But to begin, let me talk about why this is such an important problem, and a little bit of how the computer vision community has underrated this problem historically. Asking a question here, why don't we have self-safe driving cars in 2024? Those of you who've been attending CVPR for the past several years know this was a pretty hyped up area, right? A hyped up application area. Elon Musk, even before this was like reaching its apex in like 2019 in our community, was saying, Teslas are going to be like level 5 autonomy, next year. And he said this over a series of years. And we never quite got there. Now, of course, again, if you look at our expo, which is opening up tomorrow, almost all of those self-driving car companies have disappeared. They've gone out of business. They're being wound down. What happened, right? I think a big piece of the puzzle when it comes to autonomous vehicles in general is, in fact, the novelty problem. Driving is really tough. There's lots of stuff that can appear on the roads. For instance, think about new objects. In much of the history of the automobile, the smartphone did not exist, right? Not only is this a new visual object, right, that could be recognized in the scene, it also changed user behavior, right? Interactions between users changed, interactions between users and the road environment changed, right? All these things were new, right? Things in terms of the behavior of pedestrians that were simply not observed, right? And things like this, of course, will happen time and time again. Another interesting thing, which is also terrible, if you dig into recent accident reports for Tesla's autopilot system, some strange things have been happening. For instance, the car with autopilot engaged will approach the scene of an existing accident and drive into it. Why is that happening? Well, these are rare instances that aren't reflected well in the training data. And also, I'd point out, accidents aren't well characterized, right? There isn't like a stereotypical accident scene, right? The configurations of the objects are going to be different. There's going to be, right, different numbers of emergency responders and emergency vehicles, all these different things. So that's something that's really hard to learn. And right, it's a novelty that the car is simply not managing well, right? You get a secondary crash, which in some cases, right, has been catastrophic. So like all of that's pretty bad. And I want to point out the fundamental shortcoming here is one that's related to this big data strategy we've been pursuing in machine learning for a number of years. Right? It's always going to necessarily undersample the physical world, and often drastically. I think that's surprising to a lot of computer vision researchers because we've been brute forcing a lot of other problems with web scale data for a long time. But again, the physical world, there's just so much that can happen. Neil Lawrence actually pointed this out a number of years ago, just as, again, like the self-driving hype was reaching its apex on X. He noted that there are countably infinite things that can possibly happen on the road. So if you acknowledge this, you know then that you're going to have to do something else when it comes to novelty, right? There's no way to brute force this. You're going to have to come up with a scheme to basically identify it, to characterize it, and then to manage it in some way. And so all of those were objectives of the DARPA Salon program, right? Is the sort of like government folks had known this for a number of years, right? That this was, something that was inhibiting like really good mobile robotics, right? Autonomous agents and other settings. Another thing, again, perhaps again, people working on this problem, this isn't surprising, but researchers have been looking at really simple environments and adding novelties to them and noticing, again, a drastic impact on the performance of agents and recognition algorithms in these environments. Environments as simple as cart pull, right? It's like one of the simplest AI tasks, right? Like balance the beam, right, on the cart. There are fun ways to sort of add novelties to even these very simple environments like cart pull. For instance, changing the physics of the environment, perhaps varying the force, right? The complexity of the task then goes up by quite a bit. This was actually one of the environments that was being studied in the Salon program. Really simple data sets in computer vision, like CFAR10, hold out some of those classes, right? They become novelties, and the task becomes more difficult, right? And folks have done this, right, with all sorts of different simple data sets, MNIST, letter, right? All these really basic things we've assumed to be solved, right? You add the novelty, and all of a sudden, right, a lot of our best approaches are starting to struggle. Like, why does that happen? As was noted in the introduction, right, for many years I've been studying this problem, and a long time ago now, we sort of came up with some reasons for why this is occurring in a machine learning setting. For instance, right, if we look at the training data, we're always going to have incomplete knowledge of the world at training time for these open world domains. Because again, we simply can't brute force this at training time. There's always going to be new things. But why does it fall flat, right, in a classification sense? It comes down to the basis for making a decision. There's no basis from which to generalize to novel data from known data, both of which are typically far away from each other in some feature space. And if you're dealing with things like linear classifiers, this is really dangerous because you get these infinite half space effects, where again, you have a nice clear decision boundary, but this novel thing is appearing way out there in the feature space, far from the support of the known training data. And of course, right, you get misclassifications. The same thing happens too in a slightly different way in a nonlinear context, right? So if I have a really tight boundary around my known features, I still, right, then have problems generalizing to new samples of the known data because I don't get good generalization. And in some cases, again, the feature space has a lot of aliasing, and it's hard to make those distinctions. With respect to the novelties themselves, new things, as I pointed out, are always going to appear in an open environment, right? This is a fundamental aspect of the environment. And it's not restricted to object classes, right? This is something I think that's also underappreciated by a lot of folks working on these problems. Mainly, this literature has been focused on, right, object classes thus far. And again, that's part of the puzzle, but it's not the only thing. I want to point out that novel activities and interactions are also really significant confounds that you're going to have to think about. All right, so again, if you're in machine learning, you may be thinking, well, wait a minute, right? Like, we can probably manage novelty using reinforcement learning, right? Isn't that the point? We're going to go through some iterative process, right? We'll get some new information, right? We'll learn that information, incorporate it back into the model, perhaps with some human feedback, right? No problem. Well, think about this, right, sort of in the limit, right? You can't, number one, have somebody in the loop doing this all of the time saying this is a novelty, this is a novelty, this is a novelty. that means you need a really good automatic novelty detector, right, to automatically figure out that this is something that's new. Now, that's potentially dangerous if you just blindly learn it, because there are many novelties that we don't care about. In the Ceylon program, one thing we recognized quickly was the importance of making the distinction between novelties you care about and novelties that you don't. And we called those novelties that you don't really care about nuisance novelties. So we all know it, like the area of anomaly detection, right, has been pretty well developed over the years. There are lots of different anomaly detectors, but they're really not good at characterizing novelty. In fact, almost all of them don't do that. And so if you think about the world, there are plenty of things that change that we simply just don't worry about. For instance, right, this room, if I have an autonomous agent traversing it, it has a visual recognition system. If it turns out the color of this carpet is a novel shade of beige, one that has never been seen before by the system, that's a novelty. But does the agent care about it? No, right? It's totally irrelevant. But if that's being flagged by some anomaly detector as something to consider, right, and especially in a reinforcement learning regime, all of a sudden you're ballooning your model, right, because you're ingesting all of this irrelevant information. So out of the box, reinforcement learning is not going to help you inherently. And again, this comes up quite a bit, which is surprising to me, right? It's like a lot of researchers just think, oh, this is it. You know, it works in so many other domains. Don't worry about it. That's not true. Okay, so if you're going to build a really good open world agent, what would it look like? Probably something like this, right? It's going to have these three pieces that I mentioned. Novelty detection, novelty characterization, and then some form of incremental learning to incorporate the non-nuisance novelties, the important novelties that impact agent performance back into the system, right? So the input is going to be some sort of image or video. Of course, you're going to extract features, right, or learn features from that data. You're still going to have a classification component to this, right, which will probably be task specific for whatever you're doing. And then you're going to move on to this novelty recognition process. You're going to detect novelty, characterize it, and then figure out, you know, is it important, is it not? You could have, right, external feedback. There could be a human in the loop. But again, that doesn't scale, as we all know. So that's going to be a factor. So a few notes to this basic template. Number one, novelty detection and characterization turn out to be really, really hard. And again, if you've been working on this problem, you know that. Number two, efficient incremental learning is necessary. There aren't that many really good incremental learning classifiers out there. A number of different groups are working on them. I've done this in the past, but there isn't something that I'd say is like off the shelf great at this point. And a related note to that one, classifier research is just not very popular right now. Right? You know, I think like part of that's just the trends of the field, right? It's like representation learning became hot, and then we heard, you know, if you have really good representations, you'll get great separation in the feature space. Use any classifier, any basic linear discriminant will work great. That turns out not to be true. And again, we've been thinking about more complex features to that, like adding incremental learning, that's an issue. Everybody's excited about generative models, generative AI, right? So I feel like more folks need to come back to this problem because there's some big open questions that we're left with, which are important. Okay, so let me talk more about DARPA Ceylon before we get into some of the big open issues that came out of the program. So DARPA Ceylon was really interesting because again, I think it tried in a rigorous sense to find a bunch of different domains that varied quite a bit in different modes, not just computer vision, but also thinking about interactive domains like games, thinking about vision in different instantiations, activity recognition, object recognition, handwriting recognition, right? Lots of different data domains. And again, pushing this point that we should have some kind of domain independence, right? If we're building these systems, right, the ideal would be the agent is moving seamlessly across the different domains. And that's something I think is kind of shocking to the computer vision community, because typically you're working in one domain, you have a very specialized approach specifically for that domain, and you don't think about, right, it generalizing to perhaps radically different domains with very different data, interactive in some cases, right, not just static images, but the program folded all of these things together. The program also had a very specific notion of novelty and how it's sort of introduced into an environment for evaluation purposes. This was called the big red button. So you imagine there's an agent It's in some domain, right? It's operating, as it's been trained, right? Or as it's been programmed if it's procedural. A button is pushed somewhere in the universe and something fundamental changes in that domain. The agent doesn't know this has happened, but it's expected to detect that change and be able to manage whatever novelty has been injected, right, into the environment. So, right, something, if you think about this in like a distributional sense, right, like the distribution is now different in terms of the data that are being ingested by the agent. The agent's got to figure that out on its own and then adjust accordingly. And that's kind of how each evaluation proceeded throughout this program, regardless of the domain, right? The domains were quite different, right? Again, it was like everything from like carpool to like visual object recognition, Vizdoom, Carla, like the autonomous vehicle simulator, like all these different environments, but they would all sort of be structured around the same idea. What was also interesting, again, moving beyond just this notion of object classes when it came to novelty. The Sail-On program organized things like most DARPA programs in different phases. They had 3 specific phases that they carved out where different aspects of novelty would be analyzed. So in phase 1, we indeed did start with just objects, right? So this is like new classes, attributes, and representations. But in phase 2, we were looking at novel agents, right? Novel things interacting with the agent that like we sort of designed, right, in the environment. Actions, right? Like how are these things behaving, right? If it's an interactive setting, or even in computer vision, right? Novel actions reflected in a recorded video sequence. Relations, right? If there are different objects in a scene, how are they related, right? Do those relationships change? Again, something that we typically don't think about in computer vision, but that's something that's quite consequential, even in still images. Interactions, again, there are different ways of objects or agents interacting in some environment, right? I already pointed that out as a confound for self-driving cars because like pedestrian interactions change as we introduced the smartphone. And then in phase 3, we looked at more complex phenomena. Rules, right? Especially for game playing, right? What happens if you change the rules of a game like Monopoly, which was another one of the domains that we considered in the program? Can an agent figure out that something has shifted because the points being assigned, right, are not the same in terms of the gameplay? Goals. Can you change, right, the goals of perhaps winning a game without telling the agent? Does the agent figure it out? And then events, right, like big things, right, that are sort of introduced into an environment that the agent will have to negotiate. Again, an event could be compositional, right? A lot of different things have changed that's all building up into one big event, right, that has to be negotiated. And so, again, I think this is interesting, but when we're thinking about open issues, right, this hierarchy is pretty arbitrary, right? It's just the organizers of this DARPA challenge came up with this, right? And so we could probably think of more things to add to this. We could probably fold some of these things together, right? This was sort of an initial cut at coming up with, right, some structured challenges for the program. Okay, another big thing, the metrics. How do we assess open world recognition? Again, I see a lot of heads nodding here. We know in the literature that many things have been tried, right? Everything from like very basic classification measures, right? Because ultimately, if you're thinking about a task like just open set recognition and object recognition, you're thinking about like the accuracy of the classifier in some sense, right? And of course, right, accuracy is not a great metric if the distribution is not balanced in terms of like novel things versus known things, right? So we sort of know that, and, things can get buried. If it's like some sort of classifier, right, that always says everything is novel, and you've shown it mostly novel things, right, the accuracy is going to be high, right? So there's some ways to game the metrics there, which isn't great. So in literature, including my own papers, we looked at other measures like an F1 score, precision recall, right, things from information retrieval, but all of those, again, sort of have different pitfalls. That said, you need some metrics, right, to figure out, is the detection part of this working? And so the Sail-On program looked at different specific measures for detection, right, coming, down to basically this measure of like correct detections and also false positives. Is the detector working in some rigorous sense? But that's only one piece of the puzzle. As I pointed out, right, the program, and I think researchers overall are really interested in these 3 things, right? Detection, characterization, accommodation, right? Or, that's the incremental learning piece. Weirdly, characterization, nobody could come up with any good formal metrics. That remains an open issue. So the program skipped ahead to accommodation, right? How well is the agent responding to changes in the environment? So there were metrics that were formulated sort of like pre and post red button push, pre and post introduction of novelty. What happens to the agent's performance? And so these various metrics were sort of proposed, looking at like different ways of assessing the ability of the agent to sort of like perform in the environment, to learn these new things, right, and perform different temporal sort of aspects of that as well. This was sort of a good first cut, but again, we need more work there. So what did we learn out of all of this? As I mentioned, right, this talk is really about the open issues, and I want to like spend the rest of the time talking about the 8 big ones, which cover these aspects and some other ones which I think are really interesting. We organized these in terms of 3 different categories related to novelty. Number 1, theory of novelty. As it turns out, there's a lot of good theoretical work out there in the computer vision community, especially on like what is novelty, right? Are there other communities thinking about this? Yes. Stand by, we'll talk about that. Design of agents. That's mostly what we spend our time doing, right? Building algorithms, right, to tackle this problem. But as I mentioned, right, there's some really interesting big open issues there. And then finally, what I was just mentioning, just introducing evaluations. Are we there yet when it comes to the metrics? Are we there yet when it comes to actually organizing benchmarks, right, for us to assess whether or not this is actually working? And it's tricky, especially, right, if this is open world learning, information leakage, right, that's really dangerous, right? So trying to mitigate that is going to be a big thing. So as mentioned, yeah, let's talk about these 8, right? The need for better developed theories of novelty, differences between activity and perceptual domains, domain independence, better representation for novelty learning, robustness to novelty versus novelty detection and characterization, risk-based reasoning, spectrum of partial knowledge the system designer has about novelties, and the lack of measures that are really specific to open world learning. Yeah, plenty of time here to wrap this up. Okay, so number 1, the need for better developed theories of novelty. As we embarked on the Ceylon program, it became apparent, what were we working from? Like, what are the assumptions? Like, what are the first principles? Turning to the literature in pattern recognition and artificial intelligence and computer vision and natural language processing, there wasn't a heck of a lot, right? And so that meant we had to go back in time all the way to Plato, right? You don't typically get a talk on Greek philosophy here at CVPR. But it turns out Plato, in one of his Socratic dialogues, actually considered this question of what does it mean for something to be novel? And it actually has some interesting advice for us today for artificial intelligence. Plato claims that new things are generated by reconfiguring existing material into a new form through the guidance of set patterns. Interesting. So you could think again about some kind of generative universe, right, where some things are kind of fixed, like say the particles in the universe, the forms of matter, etc. There are great rules of physics that the universe needs to conform to create things that we assume to be new. That's kind of interesting, but perhaps not entirely practical for our purposes, right? So we want to figure out, is there an algorithmic way we can sort of, reason about all this? So flashing forward to another philosopher writing in the 20th century, Thomas Kuhn, who was also thinking about this. Kuhn argued that novelty reduces to the perception of things in an environment that are new to the observer. This one is very interesting because as we know, we won't have comprehensive knowledge built into any agent that we program, that we train, etc. And some things that are perhaps known to us humans may not be known to the agent, but the agent is going to have to figure them out eventually, right? Especially if they impact some task performance. So this really becomes a matter of, is it new to me versus is it new to the universe itself? That said, folks within the DARPA Ceylon program were really interested in the environment, not necessarily just this agent-forward perspective. For instance, Pat Langley, who some of us probably know is a really sort of old-school AI researcher, who knows a heck of a lot about machine learning too. He was really interested again in this sort of generative mode that the environment operates in, and argued that environmental change in a strictly generative mode is the basis of novelty, right? You have to sort of reason about novelty from this environment first perspective, right? So there was a lot of debate within the DARPA Salon program about these two perspectives, right? Is it the agent's observations, or is it really something fundamental in the environment? And there's arguments, for and against all of these things. I landed, I and some of my colleagues landed on Kuhn's sort of, perspective here, just because it's more practical when you're sort of building these agents, right? I can't comprehensively account for everything in an environment, right? That's really, really difficult. But I can, like, in an easier sense, like, figure out this is new to me, right? I can formulate an observation sort of way to reason about these environments. That said, so in a paper we had at AAAI in 21, we did sort of break this out into things that do change in the world, but again, in a dissimilarity measurement sense, so that still conforms to what Kuhn is saying. From the agent's perspective, in an observation sense, so I'm sensing information from that environment where something may have changed, or maybe nothing has changed, I've just encountered something new. And I'm, again, performing a dissimilarity assessment. And I'm also factoring in my regret, right, because I have to solve some tasks, like, will this actually impact me or not? And that's really consequential, as I pointed out, for managing nuisance novelty. And that I think is probably the more tractable approach, right, instead of accounting for everything in the universe. But still, there are open questions when we think about these theories. Given the two overarching framings of environmental novelty and agent-centric novelty, is it possible to reconcile them into a single theory? Is there any theoretical basis for a novelty hierarchy? As I mentioned, DARPA kind of came up with that, right? The creators of the program came up with that. But we can probably think of more things to add to a hierarchy. We can probably think about rearranging that hierarchy in other ways, eliminating some things, adding some things, right? All of these things are possibilities. I think, again, all of that's sort of built out of assumptions we make about our tasks, right? And that ties it then to some domain, which could be dangerous or maybe not. And does any extant theory help make predictions about agents and their interactions with the environment that can help guide agent design? Because what we want are better autonomous agents, right, that handle all these things. Okay, a second theoretical concern that came up: differences between activity and perceptual domains. As I mentioned, the DARPA Salon program had interactive game environments. In some cases that didn't have any vision component. And they also had just straight up computer vision data sets, right? All of these things were seen as being places where novelties could occur. But what the real goal was to have some sort of, right, agent that could cross them seamlessly. That's really, really tough. Right? Because again, if we look at activity domains, right, the artificial intelligence community has like a totally different set of like planning-based techniques. Right? In some cases, there may be a vision component, usually not. On the flip side, right, we typically don't do planning for static image sets, right, for object recognition, because there's no temporal dimension, right? There's nothing to plan. This makes this really, really hard to sort of, unpack. But again, if people can seamlessly cross these domains, why don't we have agents that can do it, right? That's a big question. Can the two be reconciled? I mean, there are some hints that this is possible. Mobile robotics, right? This happens all the time, right? It's like I need a vision system in many cases, right? Some piece of it is trained on static images, but it's on an agent that is operating in the environment. Now, of course, I hear complaints from my roboticist colleagues all the time. Computer vision, you folks created these highly accurate object recognition systems, right? These great neural networks trained on these data sets from the web scale data, right? The papers look amazing. The benchmark numbers are so high. I put this on my mobile robot and it's just misidentifying everything. It's crashing, it's exploding, right? The magic smoke is pouring out of it. Like, why is that happening? Good question, right? Because it's a domain shift, right? There's a problem there. Something though I think perhaps is a little bit more useful for thinking about this. Remember like DeepMind style video game play, right? Remember like 10 years ago, it was like really like exciting and OpenAI was doing this too, right? It's like you have a vision system that is playing a video game like a person is playing it, right? So it's doing all of the visual recognition, and then it has like the planning pieces, right? And playing the game like a right? Like a human player is playing it, you know, in the sort of back end as well. That's really, really interesting. Predictive coding is a classic idea in computer vision, which also has a temporal dimension, but it works for fixed images. I think that's another way to sort of bridge this gap. And then this notion of dissimilarity assessment through agent observation, right? That's another way you can sort of reason about this. So again, I think there's some clues, right, and some also prior work that fits this regime really well. Okay, the third thing, so going into the design of agents, domain independence. We've heard all of these bold claims about deep learning generalization, but they've really never been true, right? If you think about deep nets, they're basically limited to just a single domain, the one associated with the training data. You know, when we think about generalization, it's usually like generalizing to new instances, usually objects if it's object recognition, within that one data domain. But the Ceylon program had this much broader notion of domain dependence, right? Where it's like I should be able to move from object recognition to, say, an interactive car simulation environment or a video game environment or anything. Planning, of course, suffers from a similar problem. If an agent moves to a new environment, the old plan may provide it no useful information, right? Everything has been intentionally designed for that other domain, which is an issue. So the big challenge is crossing between activity and perceptual domains. Is it possible to have a feature representation that applies in a universal way? No such feature representation currently exists, right? So that's a big constraint. One possibility is, though, to pick a universal representation, perhaps something like a spectrogram, which has been suggested in the machine learning literature, and transform all of the data into it. So maybe that works. One then would be left minimizing domain dependence rather than achieving strict domain independence. Because ultimately, again, you're going to need some sort of domain dependent information. For instance, like the sensing, right? There's got to be some piece of this system that interfaces with the domain in an intentional way. All right, a related issue too, better representation for novelty learning, right? So a few more thoughts on this idea of representation. There is an intrinsic link between the goodness of a representation and the ability to detect novelty. If known information can be clearly represented, then what is different from it can be discerned without significant effort. But of course, as we know, again, a lot of this has been training systems to do this, right? There's too much aliasing between the known and unknown information. You're gonna get a lot of false positives and false negatives, right? That's bad. So like, what can we do? One thing that surfaced, which I think is kind of interesting, is the notion of a representation edit distance. This is suggested by Josh Allspector recently. It actually builds off of some earlier work suggested by Francois Chollet of Keras fame, who's been out there more recently, like with these grand challenges on like human level, like cognition, right? But he has some interesting things to say about representation too when it comes to these problems. Perhaps, right, we need a measure of novelty that can be used by agents to adapt to it. And a change in information content in bit strings, if you think about this in an information theoretical sense, could be measured by comparing pre and post novelty skill programs. What's nice about a bit string representation, again, I was just talking about, like, is there some common representation that's useful across radically different domains? This is one of them that could potentially work. And also across different algorithmic approaches. Right, if you think about AI more broadly, it's not just neural networks. And I realize that's shocking to the audience here, but there are other things, right? Knowledge graphs, other regression algorithms, even intuitive representations of knowledge, if you're gonna be very, very old school, some of that stuff still works. This is a representation that'll cross all those different algorithms, and of course, neural networks. There is a constraint, though, if we think about information theory. You need good approximations to what should be formally the optimal in terms of the framework. We think about information theory, it's usually about formal coding in formal systems. These real environments are a lot messier, right? So you're always going to be dealing with approximations, and some of your assumptions may not hold if you're trying to prove things in a rigorous sense about what this representation can actually do. Okay, number 5, robustness to novelty versus novelty detection and characterization. As I pointed out, there is a huge literature on novelty detection through anomaly detection, but it's not inherently useful by itself, right? It's like, fine, we detected it, but as I pointed out, if you're always, or not always, but most of the time you're detecting nuisance novelties that are true novelties but don't impact agent performance, that's not great. So that means you need some way to characterize these novelties. to sort all of this out. And that means you need some regret calculation in your agent to do this. Novelty adaptation then means an agent uses novel information to adjust its decision-making process or as a conditioning agent to ignore it, but not factoring in those nuisance novelties, right? Throw those away. You found the salient novelties you're actually interested in, put that back into your agent. There are different strategies for doing this. And again, this is where you sort of break domain independence, or at least this is what we found to be useful in the DARPA Ceylon program. But again, there were questions about the domain independence aspect of this. So the strategy for perceptual domains, number one, you're going to have a feature extraction via a neural network. Number two, novelty detection using extracted features. Three, you're going to use a clustering algorithm over novel features to identify new categories of novelty. That's your characterization process. Four, you're going to incrementally learn to incorporate this new type of novelty back into the model. Now, the process isn't altogether dissimilar for interactive agents in some activity domain, but there are some differences. Number one, the agent is going to sense information from the environment. Number two, the novelty detection using sensed information is going to take place. Number three, that detected novelty has to be characterized in some way. And then four is the key distinction, right? The agent's plan is revised to incorporate the novelty. All right, another big aspect of this, risk-based reasoning. Novelty detection carries the risk of being too insensitive to hard to detect instances of novelty, or being overly sensitive to all instances of novelty, leading to this problem I keep harping on, right? Nuisance novelty. So I think this notion of regret is a really powerful one, right? Especially right in the training process, if you're trying to anticipate, right, the impact of this novelty on future states. And then finally, like checking it, through like a loss formulation, that's going to be really, really insightful, right? As you try to manage these novelties. If the regret is quite low, you're going to learn what these nuisance novelties are quite quickly, right? For whatever your task is, because they're not really impacting the agent in the future. If the regret is extremely high, oh, I need to incrementally learn this novelty because it's really impacting agent performance in the future. So building that in, I think it's something that we typically don't do in these algorithms, but it's something that I think is really key for more successful agent behavior. Okay, to wrap up, let's just talk briefly about the evaluation of these agents. There are two open issues here. Number one, the spectrum of partial knowledge the system designer has about novelty. This is a general problem in AI research, right? Evaluations may leak information. If you're trying to brute force the problem, you may have sucked up some novelties, right, that are in the evaluation unintentionally, or shame on you if you're cheating intentionally. This comes up quite a bit. In fact, we saw this within the Ceylon program with like large vision language models like CLIP, right? In some cases, right, like we can't go and look at all of the training data by hand. And in some cases, these novelties, right, are very subtle, right? And so they're going to be missed, even if you did a large-scale manual inspection. So that makes this really dangerous, right? Because you may think you have a really like good agent in terms of its performance, but it's really cheating on all this stuff, right, that we thought was novel at evaluation time that was actually in the training data set, right? So you need a really strict firewall. One thing I think which is nice if you're doing these activity domains that are like in simulation, you have a lot more control over the environment, right? So the chance of unintentional leakage is pretty low. That is not the case with traditional computer vision data sets, right? Where we're sort of blindly collecting data, having people label them, right? We know there's some inherent noise in there. And again, if we're thinking about latent novelties, especially nuisance novelties, right? There could be a whole lot going on there, which is an issue. So there are some leak mitigation strategies. Number one, have a sufficiently large validation set of data for the novelty detector to be trained with novelties that do not occur in the testing set for debugging purposes. Number two, clearly describe everything considered to be known. This can be especially difficult with perception domains, but is crucial since the problem becomes underdefined otherwise, making it impossible to tell the difference between nuisance novelty and managed novelty, right? The novelties we care about. During the creation of the novelty detector, ensure that the system is defined by looking for novelty rather than guessing a predefined set of potential novel states. So that is a risk in these interactive domains. I will just anticipate all of the possible states and brute force the problem. You can actually do that with really simple domains like carpool. More expansive virtual environments though, right? I think like a self-driving car simulator, that's not going to be as easy. And then finally, ensure the problem space potential novelties is large enough that it would be impossible to hand code most of the novel states. Again, that's sort of like the human brute force approach. All right, one more here in terms of open issues, the lack of measures specific to open world learning. I pointed out earlier that the metrics that we find most commonly in the literature are pretty inadequate alone to assess the success of open world learning, right? Accuracy, precision, recall, F1, AUC, MCC. These are basically all limited to classification performance, right? I already said there's this characterization piece that's really hard to figure out metrics-wise. No, there's more when we think about the performance of incremental learning, all these different things. Also, I think really important, something we don't do enough in computer vision, measuring the uncertainty of these systems. What's really fascinating when you think about uncertainty and novelty, in many cases, the uncertainty of the model is quite high when it sees something new because it's something new, right? That's a really like diagnostic measure, right? But we're not looking at that when it comes to evaluation. And then finally, domain-independent measures for estimating the complexity level of the domain also provides a way to compare different domains, right? Which is pretty interesting. As I mentioned, right, just sort of in an informal way, some domains are really simple, like carpool. Some are really sophisticated, right? Like a self-driving car simulator, right? There's a range of that. It'd be nice to actually put some numbers to those. So we do this in a more rigorous way. All right, I'll wrap up here. I just want to acknowledge my collaborators on this work. Steve Cruz, who's a postdoc in my lab at Notre Dame, Chris Funk at Kitware, who was on our team for the DARPA Ceylon program, and Katerina Doctor from the Naval Research Laboratory, who was running parts of the DARPA Ceylon program with respect to evaluation, who helped us sort of formulate these open issues. If I have any time left, I'm happy to take a question or two. It looks like I do. Woo. Questions from the audience? Surely there's a question. I know it's early and I'm like the second talk in this workshop. Everybody's still caffeinating. Yes, yeah.
As you mentioned, Swift is trained on tons and tons of data, we don't know what's in it, and your solution is have a sufficiently large validation set. So how does that actually solve the issue? Because we don't necessarily.
Yeah. Let me add another clarification. I think the warning I would give everybody: don't use CLIP out of the box. Like you're gonna have to retrain these things, right, with like a better curated data set. And again, this is true of a lot of like the sort of like foundation model, large model, right? It's just they're a huge headache to work with in open world evaluation, just because again, you don't know what's in there. So I'd say you have a much better handle on this if you do it from scratch, but there's still pitfalls, right? Because there's just so much data. And again, especially if you're thinking about nuisance novelties, things you didn't anticipate that are in there. That's going to be a factor. Again, not as much of an issue when you're dealing with an interactive environment where you control like the game engine. But yeah, this is a really important point. Anything else? Yes.
Processing for your good presentation here. My question will be, if we jump out of the abstract definition of the novelty, we look at some real cases, for example, the open world detection, then we need to figuring out the granularity of the novelty. Because if you really take, for example, this building, you could take it as a whole, and you could take it as a piece of this wall, this windows. You could also take it as a piece of the material, and this kind of stuff you could always divide it into the small pieces and what to the end. And if you always do the incremental learning, then the capacity of the model is limited. Then how?
Yeah, this is a great question. It comes back to flip back all the way here. This idea of a hierarchy, right? As I mentioned, this was just one first cut of the hierarchy. I agree. This could be an enormous hierarchy, and much of what's in the hierarchy is irrelevant for the task, right? So this comes back to my point on nuisance novelty. I think this is one of, again, the more underappreciated aspects of this problem, managing that. I think in most cases, right, you need an agent that knows that those really fine-grained distinctions are not impacting task performance. That could be through its regret formulation, and it's simply ignoring them, even though they are truly novel and exist in the hierarchy in some sense, right? But that's not easy, right? That's a really tough situation.
I think this back to this evaluation of the novelty, because not only want to find it, but we also need to figure out what is really important for us. So
Yeah. Great. All right. I'll turn it over to our next speaker. Thank you,
Thank you.
everybody.
Let's thank the speaker again. All right, it looks like we need a bigger room for this. All right, I am very happy to introduce our next speaker, Deva Ramadan, who has won basically every computer vision award under the sun, including the Mara Prize, Pascal VOC Lifetime Achievement Award, Longan-Higgins Prize, Best Paper Awards at CBPR 19, CCV 20, ICCV 21. And over the years, I've had the opportunity to have many interesting discussions with Deva about open world perception. And he has a very unique perspective that we will see today in his talk, Open World Learning in the Era of Multimodal Foundation Models. And with that, I'll hand it off to Deva.
Okay, thank you. It's sort of nice to get introduced by your own student. Okay, so let me kind of motivate sort of my own sort of foray into this open world setting is when I arrived at CMU in 2015, I had a conversation with Andrew Moore, who just recently returned at that point to academia from Google. And at that point, that was right around the deep learning revolution. And I think he was probably the one person in the world training more machine learning models than anyone else. And he had this statement that always stuck with me. He said, quote, I spent most that. Okay, I'm going to say more. Hide. Okay. So first off, there's a continual learning workshop happening right now. And so one of the things that frustrated us when we first looked at this is that the data sets were all very toy, sort of a continual learning MNIST. And if this is really such a big problem that you're sort of faced with it, even if you don't want to in the real world, we shouldn't have to really invent a setup for this. The data should just be screaming at us. So the first thing we tried was we went to Yahoo Flickr 100 million. We assembled a data set of different categories of objects that we thought actually interestingly evolved over a span of 10 years. So this data is timestamped. There was a wonderful talk in one of the workshops yesterday by Dima on the fact that 10 years ago, we all had Walkmans, and now you don't see that anymore. So even the radios that we've been using have changed from before to now. So we put together a benchmark. The lead student involved with the CQ, and he sort of put a lot of blood, sweat, and tears into this. A whole slew of categories. I think we even talked about this in previous iterations of the workshop. And let me just tell you some sort of take-home messages. First was that one of the reasons I guess we became disillusioned in this space was that the setup for continual learning felt a little bit artificial to me. The traditional setup was really sort of on the left-hand side, where you got data that evolved over time, but your train and test data both evolved. And the problem with this is this doesn't address the problem that Andrew Moore said he dealt with, which was domain shift. So the right-hand side is more of a realistic setting where the new data comes, and the new data is shifted because it pertains to this year. Now you see, this year's models of iPhones versus before you just saw flip phones. And so what's kind of interesting about this is that once you test on this data, so today's test data next year will become your training set because you'll get a new fresh fire hose of data arriving from this continual stream. And one nice sort of aspect of this is that you can sort of theoretically avoid overfitting because essentially once you test on a data set, at some level, once you learn that transformers work better than convolutional networks, you've done model selection on this test set and you've somehow polluted it. And so what this is saying is that in a true continual learning setup, that should become your train set and you should get new fresh data next year. But one more sort of take home from the this sort of large scale effort we put is that it felt even more important to emphasize the role of unlabeled data. So this fire hose of data is coming in, and you can't really afford to label all of it. You actually only afford to have a smidgen of this. And so we found is that just like continual learning algorithms that really leverage unlabeled data did much better. And in fact, there's something wrong with this picture, because if I can only afford to label a little bit data for training, I can't really afford to test on all this data. So in fact, there's another problem that we have, is that even testing, we should think about is we evaluate models with a little bit of labeled data and a whole bunch of unlabeled. And so just like we have this problem of like semi-supervised learning, I think there's an analogous difficulty of semi-supervised validation. So we had this old paper on this, and it turns out you can apply a lot of similar ideas from the semi-supervised learning, but there is some wrinkles there. Okay. But now I want to sort of zoom out. And so this suggested that the role of unlabeled data is really important. And that's no surprise. We live in the foundational self-supervised era. Oh, let me sort of, okay, let me just sort of skip this then. The thing that kind of kept me up was this, this perspective of, if the real challenge here is really about shifting kind of distributions, then we actually look at this as a community using different nomenclature. Sometimes we'll use the term domain adaptation in addition to continual learning. And I think one of the world experts on this is Kate Senko, and we were having this conversation with her at the workshop, where she held a whole bunch of like domain adaptation benchmarks where sort of, her group was working on innovations of training models that'd be easier to domain adapt. But her take-home statement is that it was sobering to see just how well scaled up models performed compared to models deliberately designed to adapt. And so this is also not surprising. Like in some sense, the OpenAI did not make a bet on domain adaptation, did not make a bet on continual learning. They made a bet on scale, and it seemed like that was the right bet at that time. So the perspective that I want to think about open world learning is that I think it's important to think about how do we characterize open world learning in the context of foundational models. So is Walt still here? Okay, well, so I'm curious here to think about this. So I would make the claim that like we need to have a formulation of the problem that lets these big behemoth models enter into the conversation. Because if we say that they can't because we don't know what you were trained on, then it seems like somehow we're dead in the water, because we know it feels like one of the biggest tools we have for generalization is scale, and we need to be able to like ask about it. So there's a wonderful exchange with Bharath and Jitendra that stuck with me as well. So you brought up this question in one of these workshops, like, okay, if we don't know what models are trained on, how can we test them? And Jitendra's answer was perfect. He said, well, that means we have to rethink the way that we frame the problem. So my claim is we need to rethink, 100% agree, we have to rethink the way that we frame. We should not allow that. We should allow it, but it's on us to sort of figure out a setting that allows those things to come into play. So what is the right setting to think about open world, few shot learning with foundational models? And the starting point for us is, well, do these models really solve vision? So this is an autonomous vehicle data set where what we did here is we ran an open world detector, GLIP, I think, or DEDIC, but here's the results of this. And what's kind of interesting is that this is actually, this does not score well according to the ground truth. And it turns out that the way that this data was annotated was the bicycle bounding box included the person and the bicycle, and the truck just included the front cab of this tractor trailer and not the trailer portion. So it feels like there's a disconnect between the way these data sets were annotated and what, I don't know, GPT for vision or these foundation models think a truck or bicycle should be. So I guess any guess as to why this exists? Well, what's kind of interesting is that you can pinpoint exactly why this exists, and that is there's an instructions protocol for this data set where the annotators were instructed to label bicycles as only containing a bounding box that only contains the bicycle and not the person. So this is very literally what annotators were told to annotate. And what's kind of confusing is that this is actually a different definition than what Waymo thinks is a bicycle. So according to Waymo's definition, you should not annotate a bicycle that has no person on it. So it's the exact opposite. So at some level, it seems like if we don't agree on the definition of bicycle, how do we expect a foundational model to know what we mean when we say bicycle? And in fact, I think it gets even worse than this. There's been sort of well-known analysis of like errors in analysis of errors in data sets, in particular high stakes data sets like autonomous vehicle benchmarks, where folks have analyzed, oh, these benchmarks are missing ground truth annotations, and this is really dangerous. This means that there's safety critical systems that are being trained with flawed data. And there's sort of an enormous, like a sort of an interesting Twitter response that said, actually, no, the labeling policy told annotators not to label cars that were not on the drivable surface. If you're in a parking lot, don't annotate them. Somehow it feels like we have to come to grips with this. So clearly there's directives from on high in the White House. So we need trustworthy artificial intelligence. And one of the things about how we can build trust in what a system does is we have to understand what it was told to do. Something we've been thinking about is thinking about instructions as a technical artifact. And I think instructions are incredibly interesting. It's almost like how a stakeholder explains to an annotator what they want. And oftentimes it's done in a very deliberate multimodal way. We give textual descriptions of what we mean by barrier. These are the actual instructions for this data set. We give visual examples, and the visual examples span different things. Sometimes we show prototypes. This is a really nice, clean barrier. Sometimes we show partially occluded barriers. We show corner cases because we want to make sure the annotator knows you should also annotate this. And sometimes, this is cool, you show what a barrier is not, because annotators get confused by that. So, and sometimes you just get really weird descriptions of classes. So one of the classes you have to annotate is debris. If I asked you to annotate debris in images, I think you'd have a really hard time. You kind of need to see what examples mean and need to see this. It seems very helpful to see this description and also see these visual examples. So what I claim is that I remember this time in the self-driving space myself, that oftentimes, anytime you're involved in a labeling effort, there's this incredibly complex and laborious conversation that happens between the stakeholders and annotators, where they keep saying, is a reflection of a person, should I label that as a person? If I have a construction crane that's mounted to the ground, is that a vehicle? And you keep refining a policy of what it means to be a person, what it means to be a construction crane. And here's a sort of maybe a controversial claim. Maybe that actual policy is more valuable than the annotations themselves. Because it takes money to build that policy, because you have to iterate, you have to have a conversation. So the claim that I want to make is that we should almost treat labeling instructions as a first-class citizen. It's part of a data set, and it's a vital part of how a model gets trained and oriented. And if you look at work from the fairness community, data sets for data sheets was a landmark paper. It falls a little bit short of saying we should also release annotation instructions. So in fact, we've tried to get annotation instructions. Some of them have just been forgotten in the test through the annals of time. I don't know what the instructions for ImageNet actually were, and which is kind of a problem, because there was a fantastic piece of work by Ben Recht where he collected ImageNet v2 to kind of verify how well does it actually, have we been overfitting or do we actually generalize? And in order to collect a v2, it would have been really great if you just had the exact same instructions and you could just run them again. So even for like policing ourselves and doing due diligence, it's nice to have these things as historical artifacts. Okay. And what I claim, though, is that this is actually maybe a really nice way to think about few-shot recognition. What I'm showing here are 6 examples that try to describe a class or a concept. And there's positive examples, negative examples. And in fact, this is what Anish and Nihar and Shu have put together as one of the benchmark competitions associated with the workshop. A way of thinking about, one claim is you can think about few-shot recognition in the foundational age as almost multimodal fine-tuning of, you have a foundational model and it might think it has its own definition of what a truck or a bicycle is, and I want to kind of adapt it to what I mean when I say truck or bicycle. And I can actually use the exact same artifacts that we use to adapt each other when we explain to an annotator. And now, what's also, I think, kind of interesting is that you could think about this as almost just like multimodal prompting. But rather than sort of picking random examples, these have been prompt engineered, because that's how it's been engineered through this laborious process of how we explain to each other what this concept means. So this is one sort of hypothesis for how to think about open world learning. We really think about it in terms of adaptation or alignment of these models to the particular thing we want them to do. We don't really have a good word for this. We welcome any ideas. Like right now, we're calling this benchmark a foundational few shot. And I don't know, I almost feel like it should be called multimodal few shot. Okay, and this is work that Anish and Nihar will talk about later today. Hey guys. And I think there's been, so I've been involved in various benchmark competitions, and one hallmark for me for success is that if the winning entry does much better than the baseline, and that's true here. So something interesting happened when we set this up and challenged people to attack this problem. They came up with interesting solutions. So I encourage you guys to listen to that later on today. Oh, and so my bet, now that we think about how should we kind of adapt a model to what we want it to do, we can do it via prompting, we can do it via in-context learning, we can do retrieval augmented generation, we can do fine-tuning, gradient updates. There's all this kind of new tools that we have. My own bet that I've told my students a lot is that I think it's just going to be in-context prompting, but I lost that bet. So if you look at the winning results here, they actually do some real gradient-based fine-tuning. Okay. Oh, and I'll show like one, do you know how much time I have? Okay. I'll show one kind of fun example of one particular approach of fine-tuning a multimodal model. That's really simple and kind of motivated by, maybe I should first kind of, even though I sort of motivated this multimodal adaptation task from a practical perspective, I think there's a lot of cognitive motivation for this. So in the cognitive development literature, there's evidence to suggest that when you teach the concepts to children, it really helps to give multimodal cues. You show visual examples and you explain what you mean. And it's remarkable to have both of those different modalities. In fact, in neuroscience, there's a lot of evidence to suggest that when you say a particular word and when you see that object, the same neuron fires. So it's sort of interesting to think about multimodal representations that are biologically motivated. And of course, we use them quite a bit, things like CLIP. And the intuition that I want to throw out is that here's a really simple multimodal fine-tuning algorithm that leverages this kind of cross-modal space that CLIP has. So importantly, sorry, here. Okay, it says audio encoder. It should be text encoder. What I'm saying is, pretend you're trying to solve a two-shot problem where you give them two examples of a class, but you also have a class description. And normally, if you're going to train a few-shot classifier, you would just take these two examples, unless you would just do linear programming. You would extract a 512-dimensional feature associated with the two examples and feed that into a classifier. Let me remove this. Okay, feed that into a classifier. But since I'm trying to sort of emphasize this multimodal perspective, we also have a textual description of the class. At the very least, we have the class name. But maybe it's even more. Maybe it's one of these rich instructions. But I can take any of that text, push it through my CLIP text encoder. I also get a 512-dimensional vector. So now I can think about learning my linear probe classifier using 3 examples instead of 2. And as you might imagine, this is going to help because 3 examples is way more than 2. I've doubled or increased my data set by 50%. And so just by training a linear classifier on top of these 3 examples, you can do much better. And this is in contrast, I think, much more complicated prompting models and prompting techniques that sometimes take half a day to train versus this thing literally takes seconds because you're just training a linear classifier on pre-extracted features. But the features are actually using different modality encoders, your text encoder from CLIP and your vision encoder from CLIP. Because they always map your data points to the same space, you can just treat them as 3 examples. So a kind of a fun artifact of this is that this works for any kind of modalities. So we tried this on a data set of vision and audio examples. So something called ImageNet with sound. So there you can have image classes, let's say of dog, that's one class. You also have audio clips of dogs barking. And just as we showed before, if training with 3 examples is always better than 2, the same holds here. You can train with these 3 examples that are multimodal. You get a linear classifier, a linear probe classifier that works better just because it's been trained with more data. And that linear classifier can be run on any one modality at test time. It can be run on audio stuff, audio clips, and visual examples. So what's cool about this is that what this means is that actually listening to a dog bark helps you do better at visual classification of dogs, which is sort of a cool result. It's sort of really leading into this multimodal encoding. Okay. All right. Let's say, this is just sort of a shameless advertisement for ZK will present a poster this week on if we're leaning into this space of really leveraging text and visual examples to do adaptation. We know that annoyingly, these models are really sensitive to the textual prompts that we give. And so this is why I've heard this derived as we don't want to just resort to prompt engineering. That's a hack. One of the things we've been looking at is, can you actually automate prompt engineering by using another LLM? And it turns out you can. So language models as black box optimizers for vision language tasks. So the idea is that you can actually give it, and maybe you have your few shot training set, and you can say, give me a prompt that will help me learn visual classifiers that will correctly classify my few shot examples. And then you can give it feedback about what prompts worked well and what prompts didn't. And it can actually do a form of hill climbing. This is one of these wacky things that chat models can do. But the end result of this is we can learn prompts, or not we, this system can learn prompts that are actually better than prompt engineered results that we've seen. And what's kind of neat is it actually learns prompts. We can evaluate this on ImageNet or other target data sets. It can actually learn prompts that sort of describe what the data is. It kind of makes sense in this reasonable way. So if you're processing Caltech images that tend to have centered objects, if you give it a textual prompt that's not just a dog, but it's an image of a dog with a blurred background that emphasizes the subject, you'll do better on Caltech. And so you can discover that automatically. You can apply sort of similar things for increasing the accuracy of DALL-E 3 image generation or prompt inversion. So we actually are using this code quite a bit to avoid prompt engineering ourselves for all of our projects. So I encourage folks to try this out. Okay, in the last few minutes, I want to talk about how to extend such foundational knowledge to multiple modalities. So the argument that I want to make once again is that we kind of need to embrace this enormous, massive knowledge source that exists out there and figure out how to use it. And one of the ways that I want to exploit this is that I want to bring it to other modalities that we don't have all this massive knowledge for. So I talked about one method already with this cross-modal linear probing. We have a couple of other projects in collaboration with folks as well that try to bring this knowledge to LiDAR. So in the space of autonomous vehicles, LiDAR is a very important sensor, but right now, I don't think we'll ever have the amount of data in LiDAR that we have for images. And so how can we best kind of leverage foundational models for images to help us improve processing of a different modality that we don't have foundational knowledge for? And it turns out there's actually a really kind of simple philosophy that we've seen work fairly well. And that is, assume you have unlabeled data that is across modalities, so cameras and LiDAR. So this you can get just by mounting a camera next to a depth sensor. We all have one right here, a multimodal sensor. The black thing is a LiDAR. So my claim is it's easy to get multimodal data. We have lots of foundational image data, and maybe I should say foundational image models that are encoded in the models, but we don't have anything like this for LiDARs. But how do we kind of transfer it? And so one simple approach is we take these foundational image models, we can run SAM, DEDIC, or any of these other things on the images. And then using the aligned LiDAR, we try to unproject into labels that we have for instances into the LiDAR point cloud. And this is relatively straightforward because we have knowledge of where all the points, these LiDAR points project to these image pixels. We can use extra knowledge of maps and the fact that 3D objects tend to be aligned to driving directions. But once we do that, now we can get pseudo labels for 3D annotations. And now we just interpret this as pseudo labeled multimodal data. And from this, we can then train, I should have started with, we can train a LiDAR 3D detector. That's the top one. we can train a multimodal 3D detector. And what's also kind of interesting is we can actually distill this back to the image domain and train a RGB 3D detector, now that you have this aligned data. And so we have a couple of papers, including segment anything in LiDAR. Aliosh is there, that's his baby. And then we have some variant of this that looks at 3D detection. And then segment anything in LiDAR does one remarkable step further, which is instead of actually using annotated cuboids, it preserves a clip embedding. And what that allows you to do is learn a representation just for LiDAR that allows you to type in any bits of text and then find objects that correspond to trash cans or debris or any of these other complex things that I hinted at before. And there's some results from the detection side as well. Where here we've also focused on RGB only detectors or even multimodal detectors where you have access to both modalities at test time. Okay, let me skip this for the moment. Okay, and actually I want to maybe I'll kind of call it here. So this was sort of the let's say a take-home summary. So this is all motivated by thinking about this problem of domain shift. What happens when your test data doesn't look like your training set? And so while that really prompted the problem, at least for me personally, looking at domain adaptation and continual learning, somehow I got a bit disillusioned from that perspective when we saw all this incredible innovation just by brute force scale. And so I want to think about still this problem of how do we adapt to our particular test scenario using these massively trained models. And so I think these multimodal instructions are a nice way to think about it, because at the very least, that's the way we talk to each other. That's the way we instruct our kids what these new concepts are. And then finally, one of the aspects of doing sort of multimodal learning is that being able to transfer information across modalities. And here, I think the assumption is always going to be that the elephant in the room is we have so much knowledge for images that will always dwarf any amount of data that we'll have for LiDAR, for audio, for tactile. And we have to think about how to transfer this this incredible knowledge source to the other modalities. Okay, and I will end there. Thanks. Yes.
I think regarding the second one that you mentioned, the instructions for actually creating good data sets. This is a problem that we face in the industry quite a bit. We have a team of 1,000+ freelancers working as annotators there. We've got a lot of domain shift as well as tricky annotation instructions. But in your approach, what you're mentioning, right, basically treating it as a prompt engineering problem by itself.
Yeah.
I think one thing that we're missing here is the continuous feedback loop, because for like the analogy that you took, right, you have to, how do you tell a kid about how to go about describing the scene, right? It's not a one-shot learning. It is always a continuous feedback process. It may be a few feedback steps or a long series of feedback steps depending on coaching versus kind of one-set instructions. But do you think that for continuous or for more complex problems where real-world scenarios have to be captured, this prompt engineering approach can be kind of created through feedback loop, which can continuously kind of keep improving?
Yeah, you know, I agree 100%. So in fact, the analogy I want to make is like, I definitely saw that as a conversation between stakeholders and annotators. And that conversation was incredibly laborious.
Yeah.
It took a long time and it was backbreaking. And then I almost feel like, you know, maybe in the future, instead of having conversations with the annotators, we will have those conversations with chatbots, which that's what they enable. They enable chat with history. So I actually think that's very doable right now. Yeah, so I think it actually fits in very well into current technology.
So very nice spot. So when you're developing a model, for example, try to evaluate it against the benchmark, and I think what you described is basically if your model actually aligns better with the instruction, they will learn that it'll perform better, which doesn't mean that it'll actually perform better when you put it on like application or so. I think there's that coming from the like lack of instruction. And I mean, how should we interpret all those benchmarks can you trust them for like from the application development perspective? I think there's a different right?
Yeah. So I don't have a great answer. So in other words, what you're saying is it could be that the stakeholders are wrong. Because ultimately what you really want is to, I don't know, in the perspective of a self-driving car, I want to build a self-driving car. I don't want to just make someone happy that has labeled, I think a bicycle should include a person. It's kind of an arbitrary distinction. So I think I don't have a great answer for you there. The angle that I want to take is that at some level, when it comes to perhaps these high risk applications, we need to have some visibility into what we think the model can do. This is sort of the transparency and trust argument for AI. You know, the White House dictate. And so for that, I think it's almost like instead of trying to build trust in the model, we almost build trust in the instructions given to the model. So I don't know how to ensure that, but I think that's going to be part of the equation. And right now, it seems to not be. Like right now, there's a lot of the instructions are sort of lost in the history of time. And I really like what you said too. Like sometimes this is maybe a bold claim. I almost feel like their ads are more important than the actual data annotation themselves.
The process of passing on this information is actually much more critical than the annotation process.
Which is fascinating because then that's not how we talk about data as well. We talk about data and labels. We don't talk about this other thing. Go for it.
So, one is to this idea of using instructions. It also happens back a little bit to some of the older work in the classical, but now classical ways of zero-shot learning. So I think some of Serena Nakata's work included like the combination of, well, the text would be descriptions in that kind of like attribute descriptions of birds and so forth, introduction images. And in the fine-grained characterization limit, it's sort of very common because field guides often have big textual descriptions.
Got it.
But the question I wanted to ask actually was about, so I guess if I was to go back to the original question of like open world,
Yeah.
do you still think that there will be a distinction when we are adapting between sort of concepts that the model has seen in some way training versus not? Is that something that is worth testing, or it's harder to produce?
Yeah, okay, I can tell you, and this may be the wrong way, but this is the best way I would think about this now, is that I want to come up with a framing of it where I don't have to know what it was trained on, because I want to let things that have been trained privately to enter in the conversation. So if that's the case, then I don't want to shackle handcuffs on what you're allowed to train on. But then I want to argue that it's my due diligence as a benchmarker or evaluator to make sure that, for example, I can go out and take pictures right now. And if I go out and take pictures right now, I know those don't exist on the internet. There might be very similar ones, but at least those don't, because I just took them right now. I can take it, I can put them on a computer that is, insulated from the internet. And then I can say, this is my validation set. And so I would rather sort of take it, put the onus on the collection of the validation rather than the way that it's trained. Go for it.
So I guess this is also a benchmarking question, but suppose I want to set up a benchmark with a multimodal prompt. Do I take the prompt that's been engineered for human communication on a particular task, or do I take one that you've done hill climbing with respect to a particular model? So ideally, I would like this interactive setting, but of course, that I also don't know how to set up a consistent kind of evaluation that uses interactive, short of just asking lots of humans to evaluate.
Totally. That's exactly the right question. I don't have any answer for that, but that's exactly what we're sort of wrestling with now. Like, what is the right way to formalize it or set it? I mean, one nice thing that I do like is that it seems interesting that like instructions we have right now are already engineered, so might as well like start with that. It's been engineered so that we, in a way that we think helps communicate to each other what we mean by something, and then we can see if we could do better. So it could be that like maybe they haven't been engineered well. Maybe if we had just said the right thing to the annotator, we would have gotten even better quality than what we did historically. Like I remember this artifact when we were looking at the Cocoa annotation. There was like this cultural issue. We had a lot of annotators from China and India, and they didn't quite know if a hot dog was a sandwich or not. And so that was one of those things that came out of this conversational process where we had to refine the instruction to say that. And so my guess is probably if we worded things a different way and gave different visual examples, we would have gotten higher quality. And so, so hopefully we can start with what exists there and then actually see if we can optimize. But then in order to optimize, you need to have some data. I guess that would be the few shot examples like that's what we technically hook on down. Yeah, go for it.
Just wondering if you just because you definitely see the value. There's a ton of stuff with images, there's a ton of stuff with text, but it seems like most of the power that we come from multimodal is the stuff that's unique to whatever domain. So think about audio, doing stuff that isn't in the scene by definition. How do you see a path forward?
Yeah. So I don't have a great example for the audio setting, but like, let me give you an example from the one-shot setting. So if I give you an image of a purple cowboy hat, and I say, find me one-shot examples that look like this, and I just give you the visual image, I don't think you know what I'm asking. I might be asking you to look for hats, I might be asking you to look for cowboy hats, maybe you're asking you to look for purple cowboy hats. And just a little bit of text, there's a dramatically helpful in resolving that ambiguity. I think that's one of those reasons why, when we sort of explain things, having the different modalities is oftentimes helpful. So it's definitely the case of like sometimes, like in that case, that bit of text is even more useful than another visual example because it totally explains what it is you're trying to find. So my intuition is that things like this would exist for audio and other modalities as well. I haven't really thought about that. But I think that'd be cool if somehow like the sum of the modalities is more than the parts.
Can you put it this way that it's easier to actually state a rule or state a exception in text rather than in images, right? You can label an image, but you can't really express whether, so the bicycle example, right? What to exclude, what to include, or similarly the hat example. You have to label 1,000 images.
Yeah.
To basically kind of make an understanding that okay, you are supposed to only label cowboy hats or purple hats or whatever, but you could just write it in the text, stating rules in text.
Yeah. So I could imagine, like, I think an interesting space maybe to answer Charles's question as well is thinking about this maybe not just wholly with text, but a bit more programmatically. Derek was saying this. So for example, like finding not purple cowboy hats. If you just put that in text, like there's a lot of text encoders that get confused by that one word not. But I could easily kind of algorithmically code something like how purple is it, and then downweight the score based on that. Like I almost algorithmically change sort of clip cosine similarity. And so I think programming some of this is really natural. And so that's one of the things I also was super excited about the instructions, that they naturally include negative examples. Like in FewShot, we normally don't, it doesn't enter in the story, but once we think about how we talk to each other, it's very much there. Okay.
Thanks.
issue. Is everything okay on the Zoom side? Great. Hey, how's it going? Yeah, exactly. Oh. Yeah, no, I did, yeah, thanks a lot. Thank you so much. All credit to my students. For folks over Zoom, can you, did this fix the problem? Are you seeing the right thing now? Ah, great, okay. Thank you. Thank you for letting me know. Yeah, sure, sure. And it's, I think it's a 40-minute block.
Yes.
Okay. Okay, great.
Actually, let me just double check. If you wanna. We were good to go until 10:55. Yeah, 10:55.
Okay, great, great, great. I'll try to finish for that.
Uh, All right, thank you everyone for joining us. Let's get started. Our next speaker is Andrew Owens from the University of Michigan. This is Professor there. And he's done a ton of cool work in multimodal learning, learning from video, image forensics. Some of you may be familiar with his long-running workshop, Sight and Sound, which has been in its 7th year.
No.
If you're frequenting on academic machine learning Twitter, maybe you've seen some cool visuals of visual anagrams, and all these projects. But today, Andrew will be talking about learning multimodal models of the physical world
and I'm very excited to see what he's been good to at the University of Michigan. Please. take
Thank
away.
you, thank you so much for the very kind introduction. I'm really excited to be here, and thank you so much for inviting me. So we still get a lot of our supervision today from humans. In the past, some of the information we get would be from really specific things like labels or semantic segmentations or scene categories. But as we've seen in the last few talks, increasingly we're relying on language-based supervision. There's been this move toward learning from correspondences between vision and text. And while it might feel like this data is really abundant and it's free, at the end of the day, you still need humans to provide you with this data. And there's a lot of limitations to the information these humans might provide. For example, it can be relatively high-level information that in some ways may be imprecise. And maybe more subtly, you can't learn from this kind of data autonomously. Like if you imagine a robot that learns from language, and the only way that it can learn about the world is as a phone home and ask a human to provide it with instructions, it's really going to be a very limited system. And so if we're building these so-called foundation models that we're using to build for other computer vision tasks, you might ask whether we're building them on shaky foundations. On the one hand, you have these sort of high-level forms of supervision, like labels and language, and the other major form of supervision is just the raw images themselves that you learn from self-supervision. But I think there's kind of this missing middle of supervision that comes from other sensors. Like Deva mentioned LiDAR as one, but there are also others that are maybe more familiar to us, like touch and sound. And so the work I'm going to talk today is about learning from this sensory supervision that comes from other sensors. And in particular, I'll be talking about two different ways that you can learn from this kinds of data using 3D constraints to learn from tactile signals and using a kind of analogy reasoning to learn from audio. So one of the constraints that I think these other that we have on these existing vision systems is they have a lot of trouble understanding like the nuances of the physical world. If you consider like our very best reconstructions of a scene, we're gonna have this kind of shell of the scene. We can't tell that beneath the surface of this concrete, it's actually this really rough, complex microgeometry, or that it's a rigid surface. If I put my hand on it, it's not going to move. Instead, we just have this kind of like empty shell that we get from say a Nerf. And also what's missing beyond microgeometry is this notion of physical interaction. Like if we see this dirt, we as humans know what will happen if you manipulate it. It's soft, it's crumbly. If you put your hand in it, it will deform. But it's challenging to learn that information, except in a very high level way from signals like language right now. And so how do you connect vision with this sense of touch? And we wanted to create models that connect images with their corresponding tactile signals. But unlike in other modalities, it's a little bit less clear how you do this with touch. The sensors are less standardized. It's not as obvious how you collect the data, and not clear how you define the models. And so we started out with this, so our group has been working on this for several years. And as just a put the background, we were relying on these recent touch sensors called vision-based touch sensors that you might have seen before, that are really enabling some really interesting applications of touch. And if you haven't seen these before, they're sensors like GelSight or Digit that essentially convert touch sensing into a tactile sensing problem. You're going to create an image like this one here that captures what you're touching. So in this case, we're touching an avocado, and you can see the ridges of the avocado in this video, and the hardness of the avocado is apparent in its the amount of deformation that you're seeing in the video. And in fact, you could like predict if it's a ripe or pre-ripened or before ripe avocado this way. And here's how these work. You're just going to take a commodity camera, put a piece of gel on it, on the lens, And then when you push the sensor into an object, the object deforms the gel, and then you see a video of the deforming gel in the camera. And to make this image a little bit easier to interpret, we can add colored lights that illuminate the gel from many different directions, the same trick you might have seen in photometric stereo. And this is an idea that's originated from Ted Adelson's group and has been really carried a long way by Wenjun Yuan at UIUC. And so we've essentially convert this, this touch signal into this video of an illuminated gel that captures shape over time and that you can process with off-the-shelf video understanding. And the work I'm going to present, we're going to use these touch sensors and we're going to exploit the fact that it's under the hood a camera. Okay, so how do you actually collect paired vision and touch data? When I was starting out, I thought a really good way to do this would be to use robots. You just take a robot in a room, you give it all these objects, and you have it repeatedly touch them and record video at the same time. And well, you could do some interesting things with this. Unfortunately, it's very hard to get diverse data. The robot really only sees one thing, the table that it's sitting on. And there's almost this like chicken and egg problem. Like if the robot is able to successfully perceive an object with touch, it probably is already capable of manipulating it to some extent. And so it's hard to learn really like diverse objects and that would be difficult for a robot to autonomously manage. And so there is something though that's much better than robots for this, and that's undergrads. So we can we have this in our later work. We got this team of amazing undergrads, some of whom are now PhD students presenting work at this conference, and we just had them. They just went out and they just collected everything they could with a touch sensor while simultaneously recording egocentric video. And they really took this really far. They went all over. They went to parks. They went to offices. At one point, they got politely told to leave a museum. And you can see these videos here. They have a egocentric video with the corresponding tactile signal. And what you're seeing is this video of this deforming gel. And the changes in the colors convey the microgeometry. And over time, you see how it changes. And really, went all over Ann Arbor, captured roughly 14,000 different tactile signals and 4,000 different object instances. One of these students, Fred Young, is here presenting a paper on Friday on touch sensing as well. And once you have this data, now you can use it in much the same way you can in other areas of multimodal learning. You can do things like learn a joint embedding between vision and touch and distinguish between real visual tactile pairs like this and fake visual tactile pairs like this that are mismatched. And one preliminary experiment with this that I thought was really interesting is that even though we trained this embedding on entirely real data collected by humans, we were able to take the features that we learned and use them for a robotic tactile sensing task, namely some grasp prediction work that we had previously studied. And we found the features we learned outperformed ImageNet features for this task on the touch representation. And one preliminary experiment, I think it shows that because you can scale up this procedure and collect more diverse data, more adventurous kinds of data in the world, you can potentially compensate for the mismatch in domain between the robot and the human to some extent. And other things you can do, like the same students, Fred and Jie Cheng, they tried to predict images from touch. So you can train a diffusion model to condition it on a sequence of touch signals and generate a corresponding image that might have gone with it. And we have some tricks for getting rid of the hand here. So you can see the real image is in the middle. It's got a hand in it. The generated image on the right. It looks like other grass with no hand. Here's another example. If you're touching this wood, this is what the model thinks you're pressing. And you can even do other things that have been considered in the language domain, like you can stylize images using touch. So let's say you have this input image of these bumpy rocks, you can restyle it using this touch signal that comes from the smooth surface using SD-edit, and we get this result. It like kind of smoothed out some of the rough parts of that signal. You can even try crazier things like make this carpet feel more like this tree, and this is what you get. It clearly knows like what's being pressed, but yeah, I'm not really sure what it should do in that case, but it has kind of an interesting result. Okay, so as ambitious as as great as undergrads are at this task, unfortunately, there's a lot of limitations to this approach. And Deva talked about how LiDAR data collection will never be quite as large scale as vision. This is even more extreme because every time there's not like some device that's capturing tons of data passively. In this case, you have to actually physically probe everything that you want to record. You have to manually press all of these different locations. There's also this more subtle issue of occlusion. If you're touching something, the visual signal won't see exactly what you're touching because the touch sensor will occlude it. And there's also this other issue that it's, at least the way we capture this is very object-centric. There's nothing that tells you how the touch signal relates in two different parts of a scene. And so we wanted to see if we could reduce some of these limitations by putting vision and touch in a shared 3D space. So we'd like to create 3D reconstructions where you can select different locations and estimate what the corresponding touch signal is. And I think these the multimodal 3D reconstructions are potentially very useful because they can give models a sense of touch. You can just directly access what the touch signal would be at different locations. They're also potentially useful as sources of paired training data, because if you have paired sight and touch, you can sample arbitrary viewpoints for each touch signal. And I think ultimately what makes me excited about this is the potential to create multimodal environments where you can imagine learning an agent, creating an agent that learns in a visual tactile reconstruction, both what things look like and how they feel. And so this is some work that's being presented here at CVPR on Friday, led by Yiming Dao, also with Fred Yong, Eve Liu, and Antonio Loquercio, who's starting at Penn in the fall. And we want to see if we could create what we call tactile augmented radiance field. It's going to be a NeRF where you have a sense of touch in many of the locations of the NeRF. And so here's how this worked. We wanted to register the touch in 3D and find where it lies within a 3D reconstruction. So the way we did this, we took a selfie stick and put a camera on one end and a touch sensor on the other. And then Yiming just went around and he just pressed the selfie stick on all these different objects and simultaneously recorded both a touch signal and also a visual signal. And now that we have both of these signals, we have a way that we can register the touch in 3D. Because if we can register the location of the visual signal, and we know the relative pose between the vision and touch, then we can chain these two transformations together to figure out where we're pressing things in 3D. But there's also this question: how you get this signal? How do you get this transformation? How do you get the relative pose between vision and touch? Well, we can take advantage of this fact I mentioned before, which is that these vision-based touch sensors are cameras in disguise. You have this camera and it has some gel on it. And so we can just use tricks from multi-view geometry to find the relative pose between real cameras and touch cameras. So here's how this works. We'd press the touch sensor on a braille board in each scene. Yiming would then manually annotate correspondences between the bumps that we're pressing in both signals. And then we'd use simple camera resectioning techniques to solve for a relative pose between the touch sensor and the visual signal. And we'd have to do this in each scene because the calibration between them would change over time. And so I like that you can kind of take advantage of the fact that these are, at the end of the day, just ordinary cameras that are being reused for other purposes and use all the tools we've seen in computer vision. And after creating this capturing procedure, we went out and captured a large, or many of these different scenes with something like 19,000 different touches total. But there's one limitation here, which is that these touch signals are still very sparse. We only have the touch signals for a subset of the scene. And so we wanted to see if we could fill in the touch signals in other parts of the scene that we didn't directly touch. And so here's how we'll do this. We'll reuse this idea of using a diffusion model to estimate touch from images. We'll take the NeRF that we captured. We'll take a given pose RT of where we want to estimate the touch for. And then we'll just train a latent diffusion model to estimate the corresponding touch from an image and depth map that were extracted from the NeRF at that location. And so this will be a way to kind of take the touch signals that we do have and try to use them to fill in the touch signals that we don't have in the rest of the scene. It's a little bit like in-context learning. And I should mention there's really interesting related work in robotics that has a similar idea. They Coral this year, they have smaller objects they use robotic proprioception for, and they use a GAN to like us to impute touch. So it's a very nice work that I recommend checking out. And okay, so then this is the result of this procedure. We have a bunch of training probes, and you can see in this overhead view, different locations that we probed. And then on the right, we're going to show generated touch for a selection of different locations of the scene, each of which is close to the places we touched, but not that close. So it's about at least 10 centimeters away in each one. And you can see what this is, we can estimate here what this would feel like. You can see that it estimates that it's an edge. You can tell this is kind of a softer surface. This is a flat surface. And we've seen enough carpet that we know that just like the texture of the surface should look like that. And even though we've never directly touched this table, we can infer something from other tables or from other flat surfaces. And here's some other examples of this. We also have outdoor scenes. We even have some scenes that were collected in snow, which are more challenging. And you can see the model is learned to propagate this touch in kind of this quasi-dense way. And one of the things you can do with this model is you can learn joint embeddings between vision and touch and use them to localize tactile signals in a scene. So you give me a touch signal, I'll tell you where it's located in the scene. And just to visualize this, we can just take a bunch of crops from this image. This true tactile signal is located at the center, and I'm highlighting all of the different locations that it's attending to. And you can see the model, it knows that this is an edge. It doesn't know which one though. It's one of these different edges, and it's unsure which. Here's another example where we press this fabric, and the model lights up the whole area that has fabric. And one thing that I thought was interesting about this approach was that the imputed touch is good enough that you can use it for training data. So if we train our embedding with the densified, estimated touch versus just using the raw samples we collected, then we get a slight boost in performance on the tactile localization task, which suggests that at least the touch signal we're generating is useful enough that the simulated data may be useful for other downstream tasks. And likewise, in representation learning, you can take the features you learn, apply them to a material recognition task that we developed in our previous work. And you can see you again get a boost from using our data sets and maybe like a small boost from including both the real and estimated data. Okay, so just to summarize this as part of the work, these tactile augmented radiance fields, I think are exciting for the sort of open world setting because you can use these 3D constraints to collect multimodal data in a shared 3D space. You get paired vision and touch for free. There's no occlusion, and it lets you kind of impute touch in other locations. And you can, in principle, collect this autonomously either with a robot, but in our case, we used a human to do it. And I think what makes it exciting is that you could potentially eventually have these sort of models that use 3D to learn about the world in an autonomous way. Okay, so just for the rest of it, I want to talk about some of our other work on learning from audio-visual signals. And we're going to have a different way of learning about the world that doesn't exploit geometry. Instead, it's going to use this idea of an audio-visual analogy. So one of the assumptions behind a lot of audio-visual models and a lot of multimodal learning in general is that you have some paired data. Somebody gives you an image and audio or image and text, and there's a known correspondence between them. Your task is to predict one from the other. This audio goes with this image, this text goes with this image, so on. But in a lot of applications, actually isn't quite what you want to do. For example, in the task of visual to audio generation, merely predicting the corresponding soundtrack for a video isn't always what you want. Sometimes the actual sound in a video is actually not what a user would want to hear. And just as an example of this, the names for the artists that create these sound effects are named Foley artists, and this is how they work. So if you hear a sound in a video, it's made on a sound stage, and the way that the Foley artist produces the sound can be quite different from what's actually happening in the scene. So here's an example.
Walking on leaves or in a forest.
That's what you're hearing when somebody's walking through leaves.
For snow, what we normally use is regular play sand. And then to add to that, sometimes you hear that familiar crunch, which we use cornstarch. Your ear hears snow, but in actuality, it's sand.
So what you're hearing in movies and TV is really this very artificial sound. And so actually, if you were to actually correctly produce the sound that you want in the video, it might not actually be what you need for this downstream application. And so we took inspiration from this work, the classic work from Aaron Hertzman on image analogies. For those who haven't seen it, the idea is given some input image B and a pair A prime, we want to create a new image B prime that relates in the same way that to B as A prime relates to A. Like take the change from A to A prime and apply it from B to B prime. And we can try to do something similar here. We can take a silent input video, and our goal would be to take some conditional audiovisual example and use it to create a corresponding soundtrack with that input sound video. So we're going to make this silent video sound like this other video that does have sound. So this is an appealing idea, but how do we actually get the supervision for this? So this is some work that was in collaboration with some folks at Adobe, led by former undergrad Yuxi Du and Xiang Chen, as well as Justin Solomon and Brian Russell. We found that we could sort of automatically create these analogies by taking audiovisual data and creating analogies from it as follows. We will take one subsequence of the clip. We'll call that a conditional example. And then we'll take another sequence in the clip taken from a few seconds before or after. And our goal will be to estimate the audio from that second clip using the conditional clip as a kind of a hint. And this takes advantage of the fact that audio tends to be repetitive. A lot of times if you hear an action, you probably hear a similar action some other time during the scene. And so the model can exploit this conditional audiovisual example as a hint to allow it to fill in audio that it hasn't been provided with. And again, you can think of it again as another kind of like in-context learning, but it's one where we have the special time-locked multimodal signal. We have vision and sound that correspond in time. Every frame has a corresponding sound. It's like a very particular type of in-context learning that we're training our model to solve. And so the actual model itself looks like a very standard vision to audio model. We adapted from this very nice work from Ye-Shin and Ratu on basically applying BQ GANs to sound generation. We'll just tokenize the input video, we'll tokenize the conditional video and audio, and then we'll generate from all three signals together the code of a corresponding audio signal. And then we can convert that then into a waveform. And one thing we found that was interesting here was we could also improve the synchronization of the audio with the video. by using what are called synchronization models. These are models that take a given visual signal, take a given audio signal, and they tell you whether they're in sync or not. And we can use re-ranking, just like flip re-ranking, but with a synchronization signal, to rank the audio generations that have the highest degree of synchronization with the input video. So we'll just generate like 100 different audio tracks, pick the one that's most synchronized, and just produce that. And so this lets us do things like take this input silent video, somebody hitting things with a drumstick, and we can take a conditional example of somebody hitting a phone or a plastic surface and transfer that sound to the silent video. And we can even swap out the conditional signal. Like, what if we make it sound like this instead? Slightly different surface, get this result. And we can take also more kind of real world videos. We can take a silent video of somebody juggling this soccer ball, condition it on this video of dropping ping pong ball, and generate this sound a little bit. Another example, sound video of this ball bouncing, condition it on this drum, and generate this corresponding sound. One more, chopping a vegetable. Again, make the sound like the drum. Okay, so and then finally, one other project that kind of puts both of these threads together, uses 3D constraints and uses analogies together, involves sound localization. So one thing that we noticed that, or that I guess is well known, is that sound conveys changes in camera pose. Like as you move your head around, the direction of this sound source will change in both the visual and audio source. Louder in your left or right ear, depending on where you're looking, and the visual signal will change in a corresponding way. And so we wanted to see if we could use this idea to self-supervise visual camera rotation estimation systems and audio localization systems. And again, this worked for my PhD student, Ziyao Chen, in collaboration with Xingyi Qian, part of David Fowey's group. And we wanted to, again, use this idea, like if you're staring at straight ahead at a sound source, like a ringing phone, and you rotate your head to the right, it's going to get louder in your left ear. So this binaural sound in your head that you're perceiving will get louder in the left ear and softer in the right ear. And then simultaneously, there will be this motion. The sound will move to the left. And so if we can try to use these simultaneous changes in vision and sound to train models that can solve sound localization and camera pose estimation. And one way we can kind of learn, one way to do this is just to learn features using these signals. We can train a model to take all of these inputs, A prime, and B, and try to estimate the corresponding binaural sound B prime. And again, it's like a little analogy. A is to A prime, as B is to B prime. Can you figure out what the corresponding sound in B prime is, given these other inputs? It's a self-supervised learning test that kind of forces you to understand the relative pose and from visual data and the change in the sound direction from audio. And likewise, you could also kind of just fill in one of the two channels. And we found that you could learn features this way. You can train the kind of a cross-view binauralization model that's conditioned on video and learn features that were helpful for camera pose estimation and sound localization. But we also wanted to see if we could use these features for slightly crazier downstream tasks. So what if we just use these two signals to just jointly train a model that can estimate sound directions and a model that can estimate camera rotation? So we want, can we like do this without having any supervision, no labels on sound directions or camera rotation? We'll just force these two models to agree with one another. We'll train the model in particular such that the estimated visual rotation between a pair of frames S and T is corresponds to the change in the estimated change in audio sound direction. The predicted sound direction at time t and time s, when you subtract those, should correspond to the visual change and camera rotation. And you can like then try to jointly train both these models, the sound direction estimation method and the camera rotation estimation method. There's some subtlety here. There's like ambiguities. You can't tell if the sound is in front of you or behind you. You have to add some constraints to avoid degenerate solutions. But you can actually train these models, and we train them in a simulated environment from Chongyuan Chen called Sound Spaces. And what's cool is even though it's trained in simulation, you can apply it to off-the-shelf real data sets. For example, you can take just the camera rotation estimation model and plug it into this Stanford 2D, 3D benchmark. And you can see that the model can estimate camera rotation pretty well, not as well as like SIFT plus Ransack, but actually pretty well. You get like something like a mean error of 1 degree of rotation error on our benchmark. And we can also use the sound localization model to solve sound localization benchmarks, where again, it's not the state-of-the-art method, but it's surprisingly good on a lot of tasks. And we can even apply them both to real video. We recorded this video where we rotated the camera while the sound was playing, and you can see the sound direction corresponds to the change in the camera rotates, sound direction, camera rotation. All right, so just to summarize, I think these sensory modalities like touch and sound are going to be increasingly useful for learning about the physical world and giving you information that'd be hard to learn from vision alone or vision and language, which I think makes it really exciting for open world settings. And in particular, there's 2 ways that we can learn from these signals: 3D constraints that allow us to impute missing observations and sparse signals like touch, and we can use this idea of analogies to do self-supervision and solve a variety of downstream tasks. I want to thank all my collaborators and also thank you. Yeah.
I'm wondering what would happen if you gave the rendition that was like completely mismatched, like
Yeah. If it's too far out, it'll probably just ignore it. But it's like really incentivized to use anything it can, because during training it always sees similar data. But yeah, if it's too far out, it just fails. And I should say there's the one limitation there is we can only really deal with these sort of percussive sounds due to the generation method. But I would think it would be interesting to try that with larger scale, training and more diverse data. I suspect that if you add camera cuts, it also might break for the reason you might not have examples where it learns to ignore it. Yeah.
Touch sensing work. What would happen if you apply this to like truly deformable? Because a lot of the examples you showed were rigid or things which don't really visibly change when you touch them.
That's a great question. Yeah, and I think I think what's interesting about touch isn't so much the geometry part of it; it's the deformation, the material properties. That's something you can't really get from like LiDAR or any depth sensor, and I think that's what makes touch unique. And there's a little bit of that in these data sets, like the grass, for example, and in the touch and go data set where the undergrads capture everything. We do have some of that. But I think that we need to look at it a little bit more carefully, because I think one of the main issues is we're just generating a single touch example here, a single frame, and it doesn't really capture the motion. And so I think we really need to apply like video synthesis to this to really analyze it more carefully. Because I agree, we didn't explore that as much for this work as we should have. Yeah.
For the touch imputation, I guess you're imputing this sort of raw sensor data.
Yes.
But if I build my own gel sensor, presumably its raw sensor data will look much different than what you're doing here. So what's the right way to kind of measure?
I think it's a great question, because the touch signal sensors are really
It's very holistic.
Yeah. I think it's a little bit frustrating that touch is so so diverse. Like it's not like microphones where they're pretty much the same, or other LiDAR where it's like somewhat unified. So I think there's a few different ways to address this. We have a paper on Friday led by Fred Yong, who in a collaboration with Alex Wong at Yale, that's about learning embeddings by just taking all of the vision touch data from all the different sensors we could find on the internet and just learning a single embedding for all of those. And I suspect that that sort of approach might be one way to address this. You just collect a lot of touch data, and there's enough similarities in it as a human that you can kind of tell what's going on. Maybe a computer will also eventually learn that even though one sensor is gel sites, another is digits, different sensor, it learns what's important there. Another answer that we're exploring is translating between touch sensors, and it looks as though you might be able to just take the touch sensors from two different sensors and predict one from the other. But I do think that it's like an issue that is an open problem in this field. Yeah.
So my question is, what do you think is like the most natural way forward to like scale up this touch and vision data? Let's build a multiple foundation model for touch and vision. Is it like just brute force collection of data, or like
yeah, that's a really good question. I think there's a lot of different approaches. One that I didn't talk about is synthetic data. People often generate touch, but I think it's really hard to model like the microgeometry and for the deformation. I don't think there's actually very good physical models there. It's actually a very difficult thing to simulate. But I think that is like a possible source of getting at least some data that you could like pre-train a model with. The other source, I do think that just like the hiring a bunch of people to go out and collect touch sensors is actually a pretty good way to acquire a data set that you might be able to then adapt to other things. But later, I think the ultimate approach would be like to actually have a robot collecting the data. But so I kind of view this work as a way to just kind of get started with pre-training, the same way you might have a foundation model with vision language. This would be the equivalent with vision touch, albeit with much less data than the entire internet. But it's just a way to kind of get started ultimately for robotics.
Thanks.
Thank you.
Yeah, I'm mute.
Make sure your volume is.
Do I have my video turned on?
Host is, no, start your video.
Oh, there you go.
That's good. Thanks, Shu. Then you can take this and maybe minimize it or put it somewhere in the corner.
Wait,
The videos.
oh,
Yeah.
there we go.
Okay.
I don't know how to make it full screen then. Here,
I like that.
but do I have it my presenter screen here? No,
No, you don't.
wait, then how do I show my presenter screen? Do you know how to do that? Huh? That's a bit rough though. See. Probably this is the way to go.
This is probably easiest. This is
Okay.
okay with you.
Okay.
Okay. All right, our last session before we break into lunch is a session by Yun Han, who is going to be talking about a challenge, the inaugural challenge on instance detection, which we'll hear more about. So please take it away.
All right, thank you. Hi everyone, my name is Yun Han, and it's my great pleasure to present our challenge, InStat, Object Instant Detection Challenge on behalf of the organizing committee, including Qian Qian, Yanan, and also Shu. And all right, without further ado, let's get started. So first, what's InStat and why we care about this problem? So InStat is basically try to detecting a very specific instance from a 2D image in the format of a bounding box. And instant detection is actually one of the fundamental capability of humans. For example, in the airport, like when the passenger is trying to find their luggage
from 100 similar like instance, and they'll be able to quickly and accurately identify which one is their luggages, even though they probably under heavy occlusions, or maybe under different lighting conditions, or maybe have slightly different pose from what they see at their homes. And people mostly able to quickly identify them. And that's one of the fundamental capabilities. And in this case, we try to study instead and to bring this like capability into machines and also foster like the research into other directions. So in a one-line summary, basically instead we'll be trying to locating the wanted object at distance. And instant detection is also being significantly important in the field of robotics. For example, in a elderly assist robot, if they want to fetch some like object from the kitchens, and they need to first be able to locate the object instance at distance before they make any following operations. For example, the pathfinding, or when they get close enough, they do the grasping. So instead is actually one of the very first step before the robot takes any moves. So that's why we believe instead is a very important problem. So here we present the protocols for the instant detections. So instant detections, normally they take the two type of input. One will be the testing image, commonly known as like the scene image, or some people also call them query images. And they also take a bunch of like profile image, or so-called reference, basically specify the visual appearance of the object instance of interest. So for example, here, the object instance is provided as object-centric multi-view images with a QR code placed on the tabletop. And by feeding both of these two parts into the instant detection models, and we can see the model outputs the three bounding boxes, which is represent like where's the location of these instances in the 2D images, basically the chip, the mouse, and also the Steiner saw. So that's the general protocol for the instant detection problem. So comparing to the well-studied object detection in the literature, so it's very close. Instant detection is very closely related to the object detection, but it comes in with fundamental differences. So object detection aims to detect all objects that belong to some predefined classes. So I think like in the very well-studied, or like very like popular in the previous years, autonomous driving like applications, some of the most common classes will be some like vehicles or pedestrians, or maybe cyclists. While instant detections actually try to detect a very specific object instance, and they define by some visual examples. In this case, each of the instance will be treated as a separate class. For example, taking the coffee beans as one of the example, if we want to detect the coffee beans in the object detection, then all the three coffee beans showing on the top should be detected. While if we try to detect the coffee bean in the instant detection, then we first want to specify which instance or which like coffee bean bag we want to detect. Obviously, there's three, right? And only one of them we want to detect. And that's the fundamental difference between the object detection and the instant detection. So in the past, instant detection problem mostly developed in the closed world. By saying that, basically, we feeding the profile image of the instance, and also some like background image randomly sampled and majorly follow the cut-paste-learn method. Basically, what cut-paste-learn do is that they cut the foreground of the object instance and then try to paste them onto the random backgrounds. And then because since the code actually controls where's cut it like the foreground pasting onto the background. So this actually produced the free annotations. And then by doing this, this strategy is able to produce or synthesize a large amount of training data. And then following this, the pipeline will train a detector by treating each of the instance as a different class, and then with the free annotations. That's the so-called the closed world setup. Basically, after the train, the detectors they will try to detect these like predefined object instance, and then try to detect it with the incoming query image during the testing time.
However, we want to point out by sampling this random background, it is already an open world strategy in terms of since this randomly sampled background is coming from the internet, and so it could be any images like during the data synthesis process. Therefore, we believe we want to just point out developing. So the previous copy-paste-learn strategy is one of the insufficiently way to use the background image in the open world. So right now, we want to advocate developing incident detection problem in the open world. So basically, not only we want to utilize the open world sampled background images, we want to also leverage the open world trained foundation models. So as we can see, both of the background image and also the models are learned onto the open world data, which is like at the internet scale. And these foundation models are generally trained for the general purposes, and we adapt these foundation models as a specific like model for the incident detection task. And so these adaptive foundation models will be used for the testing, and we still follow the same protocols. At the testing time, we'll be feeding these profile images to specify the object instance for interest. And of course, we're feeding the scene images, and together, these adaptive foundation model will output the bounding box of the object instance of interest. So by the way, this is also the general pipeline for the challenge winner this year. So then let's dive deep into the challenge. So beginning with the challenge data set. So our challenge data set comes with 100 object instances, and each of them come with 24 profile images, and they capture with object-centric manner. Basically, we capture at every 15 degrees in azimuth and around 45 degrees in the elevation view. And we also place the QR code on the tabletop. This is for the potentially falling like to compute the camera pose with the COMAP. So for example, with COMAP. And these profile images come with a high resolution, basically around 3,000 by 3,000 pixel resolution. And for our testing scenes, we come with a diverse different indoor scenarios. And we have 160 validation images and 320 testing images. And all these testing images are extremely high resolution, basically around 6K by 8K in pixel resolution, and they cover diverse scenarios. And also they come with very challenging cases. For example, many of the instances may be heavily occluded, or maybe they are extremely cluttered. For example, in the kitchen scenario on the bottom right, you can see many of the instances are cluttered together, and the model need to be able to detect each one of them in this very cluttered scene. And also in the maybe the top left one, as we can see, for many of the instances, they are extremely small and also far, and they are partially occluded by the shelf. And these are all the challenging cases that the previous data set doesn't come with. And some do's and don'ts for our challenge. Basically, we try to advocate doing the challenge in the open world. So we basically allow the challenge participant to pre-train on anything. Basically, we encourage them to pre-train on the open world data or curate any of their own training data set, and basically leveraging any powerful foundation models for the purpose of the incident detections, except they are not allowed to train on our provided validation and testing images. And other than this, they are allowed to do anything to basically detect all these instances. We also provide 200 indoor background images, which we randomly sample from the background. That shares a little bit similar layout or office lookings to these validation and testing images. A little bit comparison against the existing data set. So in the past, most of the incident detection models are mainly developed on the GMU dataset or AVD dataset. As we can see, they only come with 23 or 33 instances, which is not that many in terms of the modern scales, and their resolution also a little bit lower. In comparison, our dataset comes with 100 instances, which all features these multi-view object-centric views, and it covers 14 or more diverse indoor scenes, covering, for example, office, like kitchens, and different diverse indoor scenes. and it's also publicly available. And we believe this is a better data set right now to foster the problem, to develop the problem of the instant detection in the open world. In terms of the challenge evaluation metrics, we're following the spirit of the COCO data set, adopting the average precisions, aka AP, and they are over different IOU threshold with 0.5 to 0.95 with a step size of like 0.05, and similar for the average recall, aka AR. We also tag the scenes with easy and hard, depends on their clutteredness level and also the occlusion levels. This is kind of like a based on the human judgment. For example, if we see the object instance in the scenes are mostly very small and they may be mostly heavily occluded, then we just manually tag them as the hard scenes. And if the objects are sparse and they are fully visible and also big enough, then we just tag them as an easy scene. Of course, we also evaluate them across different scales. This is determined by the size of the object instance shown in the testing images. By plotting the statistics of the data set, we determine the areas which is less than 200 pixel squares will be determined as small, and between 200 to 400 will be medium, and over 400 will be determined as the large. And so this is we follow the same labels for the AR. And okay, now it's time for the exciting leaderboards. So this year we have 13 teams and 30 submissions, and many of them are being very competitive. So we talked we have just basically in-depth conversation with all these teams and try to summarize their methods and also collecting what type of data they are using. And we summarize these methods and also results and presented in the following slides. So before we goes into the sophisticated approach developed by the challenge participant, we want to begin the method review from the old days, which is the very beginning of how people do the instant detection before this deep learning era. So in the past, most of people do this instant detection problem by using this key point matching based approach. As you can see, given some profile image, and they compute these descriptors, for example, like SIFT, and then they try to match these key points or doing some template matchings to detect the object instance in the images. And of course, we also want to mention the strong baseline, which is the copy-paste-learn, which we have already mentioned before. And here is a general pipeline for how copy-paste-learn works. Given a bunch of visual descriptions or profile image of each of the object instance, of course, I cut it already cut it with a foreground, and by randomly sample some background images, for example, this case will be an indoor scene, and the copy-paste-learn strategy just to try to randomly paste these object instance onto the background image without quite following any physical surfaces. But you actually try to synthesize very many diverse appearances, try to simulate the potential diverse changes in the testing cases. Even though this approach looks a little bit naive, but this has been proven to be very effective, and this is a very strong baseline and has been dominated for years until the very recent before the emerging foundation models shows up. So some remarks in terms of the copy-paste-learn strategy. First, it generates these free bounding boxes. So one of the major challenge of adapting the major object detection models for the instant detection will be a lack of large-scale annotated data set, while copy-paste-learn enable us to synthesize almost an infinite amount of numbers training data to train the detector side by treating each of the instance as a separate class. And yeah, as we said before, you can generate almost infinite numbers and synthesize any appearance with these from these profile image, maybe we can just by rotate or like by 2D rotation to synthesize a little bit different appearances. As we pointed before, it's insufficiently use of the open world background images. Since you only randomly sample some background image, open world background image, but without leveraging the other open world models and open world data. So nowadays we leverage the open world foundation models to approach the instant detection in the, of course, open world. And so let me walk through the pipeline here. The very first step will be the proposal generation. This step we leverage the SAM, which is one of the foundation model. It can basically detect exhaustively detect all the object instance in the scene. As you can show, that's one of the illustrated figures like showing on the bottom left. So SAM here basically serve as a purpose of the just the foreground instant detection. And they just need to exhaustively generate all the instant they see in the images. And in the second step, all the generated proposal from SAM will be feeding into another foundation model, which is DynaV2. This is a self-supervised, internet scale model, which will be extracted very meaningful features for all the proposals. As you can see, that's like all the proposals from this testing image. And by extracting the features of the profile images and also the proposals, we have a collection of the instant features and also the proposal features. Next, we try to do a cosine similarity matching between the proposal features and also the profile features. And for each of the proposal, we'll try to rank and select the most similar looking instance, and then basically assign that as the final prediction of that instance. So as you can see, eventually we use the stable matching, and so that's a small dot, a yellow dot, or like that yellow object in the middle will be in this case will be matched to the green object showing on the right. Even though it's wrong, but it demonstrates how this matching step here is done. Some remarks in terms of this SAM plus DynaV2 features. First explore the open world models, the SAM and DynaV2. These two models are both trained with open world data and it's on the internet scales. But it's one thing to notice that this is a non-learned method. So both SAM and DynaV2, we can see the snowflake signal over there. It seems that these models are frozen, and none of them, the weights is not being tweaked. So this non-learned method actually achieved the new state-of-the-art approach. And SAM actually achieved very high recalls. Basically, it just means that it can detect almost all the object instance, but we just might not be able to match it correctly. And DynaV2 is also a powerful representation. Motivated from this, many of the challenge participants see the high recall from SAM. So they are thinking about fine-tuning the DynaV2 to achieve more accurate feature matching step. And that's actually one of the leading participant do in the leaderboard. So basically, they try to learn some feature representations, and from the experimental results, it shows a little bit of learning to adapt these foundation models for the specific task of the instant detection. Actually, make it actually improve the performance. And we have seen submissions that try to fine-tuning the DynaV2s with cross entropies. Basically, for each of these instances, they try to treat it as a separate class, and they do the cross entropy for the classification. And we also see some teams using metric learning. The intuition behind this will be they just try to naturally grouping the profile image belong to same instance closer in the feature space. And we've seen many teams that try to fine-tune different top layers of the DynaV2. And in the just the key takeaway in this slide is a little bit of learning for the foundation models or like foundation model adaptation is actually very helpful in terms of approaching the instant detection in the open world. Next line of strategy is try to augment the profile images in both the training and the testing. So in terms of the training will be just as the previous slide shows, by augmenting a little bit more profile images, and they could still following the cross entropy or metric learning to fine tune the weight of the Dino V2. And in terms of adopting these strategies during the testing, then most of the team try to adopt this still following the previous state of the art, which is SAM plus Dino V2, basically using these additional profile images for the matching. So these like additional profile images provide more diverse. So they expect to getting from these additional profile images, they try to capture more diverse features and to achieve like more accurate matching results. So of course, the first line of thought we see will be using standard data augmentation. Here we see mostly will be some like affine transformation, something like skew rotations, and or like even some standard crop. And so another line of thought we have seen will be using commix. So the idea behind the commix will be try to blending the patches from two objects and merging them into a new object. And this is try to hallucinate some different visual appearances and try to augment the profile images. We have also seen people using NeRF to render novel views to augment the profile images. This is a pretty natural consider we already placed a QR code and the people estimating the code map. And by perturbing the camera pulse, they're able to render some novel views. Some qualitative results, like by using learnable features, we have seen right now, most of the teams still developing these in the closed world, performing the best. And by using some like open world approaches that is performing the second, and then with the baseline here will be the non-learned method, which are using SAM plus Dino V2. But we have seen some like more robustness coming from by using the open world models, which we will be showing in the visualization later. This results actually highlights the potential of like developing the models in the open world, and we're expecting to see more sophisticated methods coming in, and eventually we expect that the open world will be outperforming or performing the best. A little bit quantitative results on the augmented line of approaches. We have seen right now the standard transformation performing the best. So we believe the standard transformation actually is done on the fly, and they're able to synthesize very diverse views in both training and testing. So that's why they are performing the best. Of course, NeRF render novel views, they actually being very high quality and also very realistic looking, but they are kind of like come with a fixed views. So basically we've seen submissions that they generate a fixed number of views, and these views will be fixed in the training and the testing. So the model might be overfitted to these views. So that's why they perform the second. And among all these approaches, commix performed the worst. And this is probably not very surprising considering the quality of the generated images. So it might be too trivial to fine tune a better model with a commix, but it is maybe worth to investigate using commix in the feature space. So right now we have seen most of these are done in the RGB levels, which is a little bit trivial. Maybe by bringing this strategy into the feature space, we might see some more like performance improvement. And here's some visualizations, and the yellow box showing on the left will be the ground truth, and of course the number there will be show the instant detect, the instance index, and the blue shade is just representing the predictions. And now we have seen like the closer world model perform the best. In this case, like the SAM plus Dino V2 and the open world model both making some predictions, while the closer world models actually accurately detect all the instances in this images. In this like visualization, we have seen on the rightmost bottom, we can see open world model actually find this object that is that has been making mistakes on some closed world models, which is like this. Of course, on the average, the closed world model performed the best, but in many cases, we have seen these challenging instances are being detected robustly by the open world model, which is still highlighting the potential of like modeling the problem in the open world. Of course, the non-learned approach, they just are using the fixed weights. So in comparing to these like fine tuning or using additional like profile images, they perform the worst. But still, like these like are already way better than the previous methods using the copy learn, which is developing the models in the closed world. So from this perspective, we still encourage like or we expect to see more methods trying to develop the trying to approach the instant detection in the open world. So looking into the futures, we have a few like suggested like future directions. First, we'll be trying to better exploiting the open world data. So right now we don't see many of the challenge participants trying to collect a large scale of the open world data, and none of them actually try to use like synthetic data in the open world in the large amount of scales. And so we feel this could be one of the very promising directions if we could carefully curate a data set. So that's one promising direction we think about. And the second interesting thing to discuss will be the novel instant detection. This is one of the future focus as well. So right now, for the instant detection, all the object instance we try to detect at testing time are all available for the model to train during the training time. So basically, the collection of the instance during training and testing are all the same. While we have seen some related work focused on the novel instant detection, and in that case, the object instance trying to detect at testing time are not available at training. So basically, we train a model, and at testing time, we provide some profile images and some testing images. The model should be able to handle these unseen object instance and still be able to detect these object instance at testing time. So that's still one of the interesting problem, and it could be go parallel with our instant detection problem. And lastly, it will be interesting to explore some efficiency in computing. So right now, one of the problem with these foundation model is that they could run very slow, while most of the instant detection application could be on robotics, which they are actually require some real-time processing time. It might be interesting to try to explore some knowledge distillation or trying to explore some lightweight foundation models to make the model run faster. And it will be also interesting to explore some like adapters between the foundation models and also their output to make the model runs more efficiently. So these are all the three suggested directions we summarize for the future research. And that'll be all. Thank you so much for listening. So yeah, feel free to ask any questions like if you guys have. All right, cool.
Okay, thank you so much.
Thank you.
Yes. So what is it so?
It's on the calendar link that you have.
Because this is
Recording in progress.
So you, then in that case, you can turn this off.
Again. Do I have to stay connected through audio?
No,
Okay.
otherwise there'll be an echo. I'll move this into your computer,
Right,
just so we can check the projector.
sure.
Hopefully this works. Beautiful. Okay. Okay, I think we're good to go. We will get started in 5 minutes. Yeah. So, Yunhan here will introduce you. And then we
Okay.
can get started.
Okay,
Sounds good.
thanks, good. Do you mind not recording it?
Yeah.
Yes. Yes. So the meeting is being recorded.
Maybe we can just try to turn off the recording option.
Is it possible for me to turn on, stop recording?
Neural symbolic kind of assistance. Another part is AI assistant with this end-to-end, it's VLMs. And after building this AI assistant, of course, we want to benchmarking to make sure it's robust and it's also can act in the open world, can also reasoning. So we also have this all a lot of like benchmarking works. And finally, we want to also try to combine with like previous Xiaolong's work. So whether our AI assistants can be applied to this embodied sessions, that is embodied AI assistant. Of course, this work are collaborating with amazing students in MMLab. Okay, so you can imagine there's scenarios that is you are going to a campaign and you are maybe wearing a smart glass and you want to try to finding a seat, right? So you can ask like so many people, can you find a seat? Then this assistant may try to localize some positions for you. It also wants to understand relationships, right? So who is your friend and maybe give way to another like pedestrian over there, right? So your seat is marked in green, but please give way to approaching person first. So to accomplish this kind of task, you have to first parse the scene and also understand both the visual entities and relationships inside. So that's our actually previous works, line of works on this panoptic scene graph. So I'm building scene graph from image, static image to videos and finally to this 40, these 3D videos, because nowadays a lot of sensors, they have this like depth sensing, so you can get a lot of like point cloud as input. So of course, we will first want to advocate this beyond object recognition. So what is inside the image, I think is already well solved, right? So currently the detection, segmentation, and also all the basic vision tasks are considered solved. We have like 2 persons, 2 bench, tree, and pavement. But what happened in the image, right? So besides what, we also want to understand like well and how, right? So maybe the story is like woman and man touching and looking at each other. The woman is sitting on the bench on the left, and the man is sitting on the bench on the right. So they are in front of many trees. So this kind of capability is still lagging behind for current models. Even for the very powerful vision image models, they don't have a very good sense of these visual relationships and also the spatial combinations out there. So here we want to advocate a test that tries to give one image as the input, then we want to output the scene graph. So the scene graph, I think, is pretty much different from the original scene graph because we want to ground the whole symbolic things on the masks instead of the bounding box, right? So bounding boxes are still coarse. It's not very good for a lot of manipulation tasks, such as in robotics or in generative AI. You actually want these pixel level understandings. So we have like the person, the bench, sitting on, looking at, in front of, right? So we want to list all these spatial relations out there. And using the scene graph, we can also enable QAs. So actually this task or this data sets have helped us pave the way to train more powerful vision language models out there. For example, we can ask them what happened in the image, where is the man sitting on, what are the man and woman doing, right? So you can see that's a typical questions for even for like GPT-4b, right? So we can generate training data as well as the benchmarks from this symbolic approach that using the scene graph. So a formal definition is given an image with very complex things. Our output is the scene graph as well as these panoptic segments. We also try to ground all the visual entities and relations to the segments out there. Of course, here we want to kind of enable a lot of properties that is previously not achieved, like accurate grounding, proper class granularity, and also able to invoke background. Because you know the object detection only tackles about objects. They're not talking about backgrounds or stuff out there. And I think this data has already been open source. A lot of people have used that. You can also try it yourself if you're interested. We have now much more than this 50K. And I think the object classes has also increased. So at that time, we have tried like two approach. So one is the two-stage. So first through the segments, then we do the scene graph prediction on all the tokens from the segments, right? So each of the regions, we can have certain tokens out there. Then we try to pull the features, do the relations, right? So it's pretty good. It's easy to use. It also support a lot of classic methods. If you have your own favorite segmentation models, you can use that. But it's very heavily rely on this segmentation model or the detectors. Of course, another way is more like this one-stage approach. So here we kind of try to train the whole model and train. It's focused on vision and it's direct training, but I think downside is need a long time to learn the whole pipeline because everything is tokenized and just use the transformers to predict both like the predictions for the mask, prediction for the class, and prediction for the relations out there. So it's also may have like the conflict with current pipeline of this panoptic segmentation. So combining these two, we have this another transformer network. So it's good. We have both the advantages of the direct modeling as well as quick convergence because we can leverage some of the pre-trained features. So the time limit, I will not go to the details here. So here we can actually run some like live demos. If you are interested, you can when you do the registration out there, or you are like listening to some workshops, you can try to run our kind of demos that is well man with a fancy backstanding, who is very much effect the photos, something like that. So after that, I think nowadays more of the people they are like interested in these videos. So especially for the long videos, right? So we want to understand what's happening in the video and also tries to ground all the elements inside the video to do the trackings along a long time, as well as the relations out there. If there's very complex videos involving multiple persons, multiple objects, as well as very complex things. So that's why we try to start this PVSG that is called Panoptic Video Scene Graph. So I think the program is like this. So given one monocular video, so it can be quite long, minute level long, then we'll try to predict both the mask, this panoptic mask, as well as their relations. So one thing to know is here the relation is dynamic instead of static, right? Because maybe from frame 1 to frame 10, person A is kind of in front person B, but after frame 10 it goes to behind, right? So it tries to predict all the dynamic relations out there. So it's actually a very challenging task because you have to do these groundings, pixel level groundings on the videos, as well as these dynamic relation predictions. So that's why we propose this called dynamic scene graph. So I think this can be very useful for two subfields. So one is definitely this kind of embodied AI. So when the robot is working outside, if it can understand the world in this way, it has more understanding of the relations and context information. Another, I think, is on this more like VLM. So we are training like GPT-4o, right? If you want to also generate a lot of QAPLs, so this is a very good way. It can help you not just understanding the static spatial information, but also all these dynamic things. So you can see it's actually a dynamic graph. So the relation changes across time. We also, there are some new relations will happens afterwards. So to enable all these like applications I have mentioned, so we actually build this data set. So you have very long videos, and also we contain both ego-centric motions and also third-person views. We contain both. And for the different scenarios and for the kind of multiple perspectives, we have included them inside. So you can use this one for any task from low level, middle level, panoptic segmentation to like captioning, QA to the kind of embodied AI, right? So here is one of the examples here. You can see there's a boy, right? It's kind of receiving, giving, and unwrapping the gifts on a holiday, right? So there are some dance description of there that is from frame 0 to frame 18, that the little boy is passed through the television and the pick up gift, right? So that is a very important, contains actions, also contains all the fine-grained relations. So maybe you can also ask some questions. So why did the little boy give the gift to the woman, right? So you can also try a case to the GPT-4o, something like that. So current VRM actually is not quite good at this symbolic reasoning. So the answer is actually it might be a gift exchange moment, and the gift is for the woman, right? So you have to understand the interpersonal relations and also the rationale behind that. That is reasoning across the long time. Of course, for this egocentric, we're building upon this application and ego for the. So this one is very useful for like the embodied AI applications. So we also make a live demo out there. You can see this one. So that is, we actually implemented on some of the first-person class. So when we go home, and it tries to also parse the scene around us. It can provide this frame level panoptic segmentation for the long videos. You can see when we open this refrigerator, it tries to parse all the things out there and also relations. You can have your tables or bottles, and tries to predict the kind of action relations. And the one holding something, and something's on something, and he's doing something else, right? Like tries to clean in the that one and open another part. So I think it's quite valuable beyond the previous task, that is the symbolic task. And we can also do some QA. So what will the man do next, right? So it's try to do the action anticipation. And also you can do other things, right? That contains both third-person view and first-person views. Of course, the model I don't want to emphasize more, so it's much more like what has been built. But here the features is a tube instead of just a token on the static regions. Because we are operating on the videos, right? If it's a long video, you actually want to do the tracking and also make the aggregate features across the tube. So stage 2 is tries to predict the spatial temporal relations across time. So of course, we have some demo results. It's also online, open source. If you're interested, you can check out and try to play on your own videos. So after that, nowadays, we are not just have molecular videos, we also have like 3D sensors everywhere, right? So that's why we try to add in this PVSG, this panoptic graph with the videos, with the 3D, then we got this PSG40. That is, we want to parse inside this 4D world. So I think the concept is just that we have some visual input from this 4D, it's also dynamic world. So it can be point cloud, it can be like depths, it can be anything else, but we contain these 3D informations. So you try to aggregate this information to parse into this 4D kind of scene graph. So you not just have the positions X, Y, you also have the Z there. So that's, like how far is the object, right? So it's very important for the robotics. So after that, you also try to figure out the relations. What is the different objects they are interacting with each other, what the person doing, so what you should do next, so that we can accomplish some of the tasks, right? So you can also do the reasoning and the planning out there. So of course, we have included like two parts. The first is more like a synthetic dataset. So we are building on GTA. So there contains like 7 videos and 35 different classes for 3 relations. And we also build on another real-world dataset. It's called HOI40. So pipeline, we actually included like 2 different options. So option 1, if your camera is RGBD, then you can use this RGBD-based method. And if your sensor is outputting point cloud, it's also great. So we try to aggregate the 2 different input modalities together. Of course, the major thing here is also to do the tracking. There's also very active research here that is how to track within the 4D world, right? So after tracking, we try to inference and also learn the relations out there. So here we also have implemented on very cute robots out there to help us to clean up the graph. So we find that it's also very accurate if you just implement on some like very cute robots. So it's first try to segment the scenes, then it tries to pick up and also can also have some interactions with the VLM, right? It can be integrated with the GPT. So the GPT has the have the reasoning, and this one can help the GPT with some intermediate steps. So give your GPT with some relations, with some the parsing, with the groundings out there. Right. So after we building this kind of AI system with scene graph, so we are thinking of we are not just want these symbolic things, right? Neural symbolic things. We also want to go to just LLM prompts, end-to-end based approach. So we want to go from this multimodal input to scene graph to LLM based method. So that is the second part is AI system with VLMs. So actually we try to follow the same path. The NLP domains, that is from these language models to language assistants. We can see from GPT-2, GPT-3 to GPT 3.5, ChatGPT, GPT-4. So they are actually following the same path. You first have the capability of zero-shot learning. Then you will want to add in some in-context learning. So that is very important. And finally, you want to align with the human instructions. So that's why you want this ability of instruction following and human alignment. So in VLM, we should also do the same, right? So like 2 or 3 years ago, everyone is working on Clip. So Clip is good because it enables these zero-shot things, right? Zero-shot learning. And then we have like Flamingo models or Lava models. So they are doing this in-context learning. So however, they're still not a very good assistant because not tries to very friendly following instructions. So that's why we want to build something that can do the instruction following. It's an auto model. So at that time, we are building about Flamingo. So of course, we have doing some upgrades after that. So Flamingo models, I think everyone is very familiar, so very quickly goes through. So it can do the instruction in context learning, given some image text pairs. You can also do the inference, completion. It can also operate on videos. So that's a good thing because it can operate on image, multi-image, and also the videos. So it's a very unified models. So even though it's a very good model for zero-shot, but it's not a good model for assistance because it's not trying to follow instructions. Your training objective is just to accomplish the next reasonable sentence, right? It's training this way. So it's just a pre-trained model instead of instruction following models. So that's why we want to build something more than this MMC4. So there's a lot of people building on very fine-grained, accurate data sets nowadays for this multimodality models pre-training. And we argue that beyond this pre-training, we also want something that is have this capability of instruction tuning, right? So that's why we have built the Mimikits data set. So for this one, you can see we try to find a clever way to automatically finding this interleaved data, right, from pre-training to instruction tunings. Of course, the model itself, I think, is more or less the same to what we have seen for this multiple models. We have vision modules, we have language modules, we have some resamplers or MLPs to connect them together. So I think the major part I think is on this data set. So we try to enable both the perception, reasoning, and plannings out there. So here I will give some examples. Of course, we also try to include this multilingual things. This comprises of 8 languages: English, Chinese, Korean, Japanese, German, French, Spanish, and Arabic. Right? We try to be more inclusive. This contains a lot of TV captions out there. We can also enable this visual storytelling and even do the planning. So this thing you can see, can you suggest any recreational pursuit that can be enjoyed with this group, right? So it's definitely needs certain degrees of reasoning out there. And also, is there enough space in the room to set up a home grooming station? So you have to also have some spatial understandings out there. And for this one, we also have this egocentric video understanding. So this is also important. It's safe to work while the woman is cleaning, right? You should have some common sense to do the results out there. And of course, it's capabilities out there. You can try our demos. It's all open source. And I think we're also doing some like benchmarking. So, it's very hard to keep the top on the benchmarks every day. There's new models comes out. So we have the GPT-4 as the judge. We also evaluate on some objective benchmarks at the MMBench, something like that. So at that time it's good. So after that, we also building another model. It's called AutoHD. Because if you want really accurate grounding, but really fine-grained reasonings, you have to see the image with every details, right? So if the current like VLM can only support like 256 by 256 as an input, that's definitely something that can't be recovered. Because when you do the pooling, when you do this kind of embedding, you already lost a lot of information. So here, actually, our AutoHD is building from these FuYi-based models. So it tries to operate originally on this high-res visual inputs. So we don't do any of the poolings, any of the encodings out there. We just use the raw visual inputs so that everything that is of the information is inside. And the good thing is also supports flexible input size. So test time, you don't have to use the same size of the image to retrain it. You can use like flexible image inference. It also eliminates the need for vision encoder, right? That's a good thing. It's an encoder-free approach. So I find that this kind of AutoHD is very good at kind of the tables or the fine-grained figures. You can see this whole approach is very simple. It's a simplified version of the FuYi. You just feed your input patch using a very simple linear projections to do the transformers that you output. We find that in this way, you can also do this VLM effectively. So we also have some benchmarks called Next5 benchmark to test whether you can see all the tiny things inside the image, right? So sometimes you can understand 10 tiny things as well as the relationships out there. So of course, for this one, I would like to skip. You can like spot all the numbers, or you can see all the text. It has some OCR capabilities out there. And this year, we are collaborating with the Lava team. So we are trying to combine the strengths of AutoHD to this Lava. So we have proposed Lava Next. So I think the major lessons we learn is, of course, the stronger LM can supercharge the smart capabilities in the web. So we just extend our previous Lava Next to the 3 times larger. So now we have 2 models. One is 72 billions. Another is 110 billions. So you can see it's still following the scaling law on the graph, right? So on this MMLU scores, when your model is larger, we find it's constantly achieving better performance. It's still following this on this log scale, it's still good, right? So we find that under the same training strategies, stronger LM with larger model size, larger training data brings stronger multimodality performance. So good thing is that our Lava Next now already on certain metric, it reaches its GPT-4 level multimodal performance, right? I think it's one of the most powerful open source model nowadays. So our largest model, this Lava Next, 110 billion models, it actually can be trained on this 100 GPUs for 18 hours. So we also open source all the training scripts, also some of the configurations, so you can try to reproduce yourself. So here is some of the results out there. Of course, I will try to skip. It can be very fine-grained captions with no hallucination. So it can also understand this multilingual, right? Just write the Chinese poets to this image. You can see it's kind of good. It's also understanding this basically of the poet from this multilingual perspective. So here is our link. We also have a set up an online demo. You can try. You can use your own photos to convert to some code, to understand it, to give some caption. That's definitely good. So of course, if we have a very powerful image models, next step is always have a very powerful video models, right? So OpenAI already goes from GPT-4 to GPT-4o. So now we also want like a video model that can have the same or similar capability. So that's our project for Lava Next videos. I think the major lessons are just twofold. So the first is just using the current pre-trained image level models can already achieve strong performance on the video level. The second is that the suitable or efficient representations in the video is just a bunch of patch across time. So you can try to think of our input is just a bunch of multi-resolution, like multi-aspect ratio patches across time, stacking together, then fit into the transformers, right? So you can see here is one of the examples. We use the Sora demo videos to do this captioning. You can see the results are actually pretty good. So we also provide another version that is using the DPOs. So it's kind of reward tuning. So we have the DPO. You can see the content, they are more or less similar, but it's more relates to our human perceptions out there. Yeah. And here is the benchmarking results. So you can see it's currently the most powerful video models nowadays. So this one is the video Lava Video Next. So first models, they are more like 30, 40, this kind of accuracies. So we push it to 66, something like that. Here is the GPT-4, GPT-4v. So they are just 70. So we still have like 10% of the gap. But we are still nowadays the most powerful video model nowadays. Since our group is also working on generative models, so we find that it's a very good tool to generate all the fine-grained captions for like video generation, image generations, or 3D generations out there. Okay, so after talking about this AI assistant with the VLM, this end-to-end assistance, next I will briefly talk about our efforts to benchmarking them, right? So I think we propose an efforts, it's called AMC evals. So everyone has faced a problem. So every day there's new benchmarks comes out, new models come out. There are some numbers on the papers. So you can't reproduce it, you can't compare with them, right? So how do you can do a very efficient comparisons across like 20 to 30 benchmarks? So that's our initial motivations. We want to solve the problem for you. So if you just install our toolbox, you can run the evaluation with just one line of code. So you can try to align all the performances across the 20 to 30 benchmarks and help you get the results to compare with all the previous models, both open source models and closed source models, right? So you can see nowadays we have to compare across a large different benchmarks, like in Flamingo, right? So they compare to these 20 different benchmarks nowadays. So sometimes even for the evaluation itself, it will take 2 days because you have to run the evaluations on lots of benchmarks, lots of samples. So here we give you a unified interface. So here is something we have included. We have both the image level benchmark, video level benchmark, like the eco schema, activity net. Then we have this evaluation toolkits, right? So you can choose your task, which kind of benchmark you want. You choose the models, then you also try to select the metric you want. Then with just one line of code, we are trying to align all of them for you. We also provide some analysis tools to give you a sense of which part of this benchmark that the model is very good at or is very bad at, so that you can debug your models to find its shortcomings, right? So we have a lot of these log tools, or GPT eval score tools, we can try it out. So nowadays we already have like supports 50 plus image tasks and 10 plus video tasks. And we also include like 10 state-of-the-art multimodal models inside. So if you have interest, you are more than welcome to contribute, right? It's open source project and just PR, and your models or your data sets will be included inside. And all these kind of like video data sets, they are focusing on more like the very ordinary things like the action recognition or like the anticipations, but there's very profound thing that is the kind of how humans tries to understand humor, right? So that's why we propose data from QA. So we find it's very important to understanding the fun part of the videos. Like this one, right? So if our humans find this very funny, so how will the machines feel about that, right? So like the QA file is like localize this amusing part of the video. So why do you think the video is very, very kind of a comic, right? And for this one, it's the same, right? So humans find it very surprising and how the machines or the smart models will feel about that. So it provides a lot of these QA files to help you to evaluate. So we have 3 parts: humor QA, creative QA, magic QA, and how the kind of market models will understand the magics. For this part, it's just the magic, right? So how will this kind of AI perceive all the magic tricks of our humans? So I think I will just skip this part. And here's overall like the kind of the distributions across different benchmarks. And we find that the current VLM is not very good. So they are not understanding our human humors out there. So they are not kind of tries to understand the funny part or the counterintuitive part of the videos. You can see we have experimented with authors or lava videos, or even like the GPT models. You can see the results here. So they are not quite good. So current models only like achieve like 20 to 40%, right? There's still a long way to go for VLM to truly understanding these counterintuitive and surprising videos. So another part, very important part of the video is about the word knowledge, right? So everyone is talking about word models. So what is word models? So word models is tries to understand the kind of different aspects, like the common sense, like the tool use, like the conceptual information out there. So here we provide the benchmark for us to understand all the word knowledge inside this VLM, whether your VLM has something inside. So we propose something called reasoning steps. So I think all of you have heard about the chain of thoughts, right? So you have a long chain, then that means this task involves much more of the reasoning. So we find that our benchmark is 4 to 5 steps of the chain of thought to solve, compared to other like existing QA tasks, they only need 1 or 2 steps. So this one actually needs very deep thoughts about the word knowledge inside. So here's distributions. I think I'll just show the video demos of this data set. So you have a very intuitive sense. So the question is, where the lady go when she was absent from the video? So you can see. She's making coffee, reading newspapers, and goes to the clock. She look at the clock, and she realized she should go. Then she picked up her suit, then she goes. Then how do you answer this? Where did the lady go when she was absent from the videos, right? So this thing is very intuitive for our humans. But for VLM, we find it's very hard, because it have to aggregate information from the visual domains, from frame 1, frame 100, and also some of other cues, like why she look at the clock, and why she kind of put up her suit, right? Something like that. So we have to understand both the actions, the reasonings, also the song. So these data sets containing the soundtrack. So your model should be multimodal enough to take both visual input and the audio input together, right? So I think finally, your model has to aggregate all this information together. You should have some common sense. You should understand the tool use. You should also have this multi-model associations out there. So you can try yourself. It's also open source. And finally, is the unsolvable problem detection. So that is, a lot of people try to trick the current VLM. Right. So using something that is definitely not should be answered. For example, for this one. So given this Pokemon kind of image, that is, what color is a car? Right. So it's definitely an irrelevant question. But current VLMs will try to answer, because you have asked questions. You also give ABC, like GPT will answer or A or B or C, something like that. For example, Lava will answer, I will choose A. But the right answer is actually your question and your input, they are irrelevant. you should not answer these questions, right? So we want to equip the current VRM with the abilities to reject some of the questions, right? So you should have a sense whether the question is sensible or not. So we also have these 3 different types. So absent answer detection, incompatible answer detection, also incompatible visual question detections. So I think the observation is current model is not good at that. So they are always trying to answer from GPT-4b to Lava series to Gemini to others. So they are still very weak. So current model don't have these mechanisms to handle unreasonable inputs or out of distribution input. So that's a very important lessons for us. And due time limit, I think we'll very quickly go through the final part, that is embodied AI systems. So essentially, we try to combining the VRMs we build with the kind of the scene graph, the spatial perceptions, parsing to embodied environments. That is, we want to go from building multimodal AI system to building embodied multimodal AI systems. So I think for this one, we'll just skip. Of course, we try to generate some data with some data students. We try to tune our models for partners. We have some reinforcement learning inside. So it's just like the reinforcement learning from human feedback, but here our concept is reinforcement learning from environment feedback. Because when you do an embodied AI, what we're facing is a dynamic, changing world, right? So that's the open world. So how can you learn from this open world? We just use this RL-based method to update in some of the parameters in the VRM. So for this one, we give some of demos. So we are trying to generate executable code. We're generating code out there. So we actually want to drive the pad. Then our models tries to generate code. The code will tries to complete tasks inside the GPT, inside this one. So the input is a visual input in the video, and output is actually an executable code. So the code can be executed inside this environment. So if it is an embodied environment or it's a game engine, you can just follow the code. You can do all these actions. Okay, so for more details, you can just look at this this one. Yeah, there's our demos and project page. I think that's all for my talk, and thank you. Yeah. Oh, I think I should have time for take 1 or 2 questions. Yeah. Okay.
So you show that the current VRMs suffered an understanding the long videos or the more QA data sets.
Yeah.
So what do you think about the bottleneck? Is it because the training data does not contain such videos, or it's because the architecture of the models? And what do you think are the ways to improve to go beyond this bottleneck?
Okay, I think that's a great question. I think the reason comes from 3 different folds. So first, it's definitely from the pre-trained data. So current pre-trained data don't have this long chain reasoning. So it's more like 1 or 2 steps. So I think that's lacking. And the other side is on the architecture side. So current architecture, Lava series or others, they just have a very simple bridge between this visual input and the language input. I think it's not enough to have a very deeper understanding of the visual inputs. And the third is, I think it's on the post-training side. So a lot of models, during the post-training, they're using RL, HF, or something like that to improve, or DPOs. So that part, I think, still needs some improvements to enable the truly reasoning abilities. Currently, this post-training only enables very fluent, these interactions, but no reasoning is inside. Thank you. Okay, thank you. That's all for my talk. Yeah.
This now works. Yeah. It's still showing. Yes. Slide. It's right. Okay, good.
Yeah. Yeah, they can hear the sound now. Okay.
Okay, cool. I'm sorry about that. Yeah.
All right. So you can.
Okay, cool. Yeah. Thanks. So as we know, generative AI has emerged as a new wave following the discriminative AI. The community has developed various types of powerful generative models, such as large language models, diffusion models, neural reading field, and video generative models, to name a few. They are able to create very impressive text, code, images, 3D things, and even videos. But creating alone isn't the ultimate goal. What we need is to understand and take actions in the world through the generation process. So what is missing when integrating generative AI in the real world, which is inherently open and dynamic? First, our world is 3D plus time. Only synthesizing 2D images is not enough. The generation should be rooted in 3D and even 4D. More importantly, we need to bridge generative models and discriminative models so that they cooperate with each other and improve the perception in the open world, going beyond mere generation. This alone is insufficient for navigating the complexity of the real world. We aim to push the boundary of generative models, empowering them to address desired decision-making and problem-solving tasks, effectively function as autonomous agents. Ultimately, considering the variety of generative models available, ranging from large language models to visual generative models, they potentially encode complementary aspects of the underlying world. It will be exciting to compose all these generative models to create a somewhat comprehensive supermodel, enabling us to address even more complex tasks that were previously deemed unattainable. In this talk, I will discuss some of our group's effort in pursuit of this research objective, unifying generative and discriminative model, as well as their diverse capabilities and the different environments. To this end, we first need to advance generative models to perform a high-fidelity generation in the 4D physical world. The first step is to leave the successful 2D image generation models, like diffusion model, to synthesize objects or scenes in 3D and 4D. Not only do we want to precisely reconstruct the 3D object or scenes, we would also like to manipulate the generative models to edit the objects or scenes through language-based instruction, as illustrated here in the well-known instruct nerve to nerve. However, unlike 2D image generation, the fundamental difficulty here is the lack of 3D training. That means, so far, we still don't have strong generalizable 3D diffusion model. As illustrated here, current 3D diffusion can only generate simple 3D object from specific classes. So the widely adopted solution is to somehow distill the 3D generation or editing signal from pre-trained generalizable 2D models, like 2D diffusion models, such as using score distillation sampling proposed in DreamFusion. The basic pipeline, such as in instruct nerve to nerve, is formulated as follows. So nerve is first trained on the original images to reconstruct the object in 3D. And then a 2D diffusion model, like instruct pix to pix, is used to edit images in 2D with a language-based instruction. And the nerve is tuned to reconstruct the edit object in 3D from these generated images. Now we can render the edit objects in 3D. while NeRF tries to produce 3D consistent reconstruction from the given images. Unfortunately, the 2D diffusion model cannot provide multi-view consistent images during the editing process for NeRF to operate. This leads to failed editing results in 3D, and it becomes one of the major challenges of this widely adopted solution. So we have developed a series of work to overcome this issue. For example, our VCA NeRF generates 3D consistent editing or style transfer result across a wide range of scenes and instructions, with significantly improved multi-view consistency, editing controllability, and efficiency. Our Consistent Dreamer further enhances the 3D awareness and 3D consistency, achieving high fidelity, high resolution editing or style transfer in complicated scenes, particularly in large-scale indoor scenes, with significantly improved sharpness and fine-grained texture. Our key insight underlying these approaches is to not solely rely on NeRF, but explicitly propagate editing information across different views so as to ensure multi-view consistency. So here I will mainly talk about one approach, Consistent Dreamer, which introduces 3 synergistic strategies to explicitly propagate the editing information across the different views: structure noise, surrounding views, and consistent enforcing training. With these strategies, we designed the framework of a Consistent Dreamer to achieve 3D consistency in 2D diffusion. Intuitively, consistent editing result should be also denoised from consistent noise. We therefore construct the structure noise by putting noise on the scene so that we can render 3D consistent noise in map. So in this example, we can observe that the noise also moving together with the object. So the structure noise set up the foundation of the consistent editing result, enabling and consistent editing from beginning to the end. Only structure noise is insufficient. We also observe that lacking contact in some views lead to unstable or even abnormal editing result, as illustrated here. So to this end, we construct surrounding views by surrounding a large central view with 16 smaller reference views. We use them as the input to the 2D diffusion. With the sufficient context implicitly reasoned by the self-attention modules in 2D diffusion model, we now achieve consistent and desired editing result. So you can see. We further propose a multi-GPU framework to edit N surrounding views in parallel on N GPUs. So we apply self-supervised training on the diffusion model by constructing the target through warping and averaging all the 17 N views, which are used to self-supervise the diffusion model. We also similarly self-supervise the predicted noise at each denoising step to ensure a consistent denoising procedure that starts from consistent noise and ends with consistent edit images. So with the framework composing all these strategies, our Consistent Dreamer achieved a high fidelity scene editing result. Compared with the baseline instruct NeRF to NeRF, our Consistent Dreamer generates much sharper result with higher instruction fidelity in a variety of the tasks. So for example, in the editing results of the top left, which is a Fangzhou scene, our Consistent Dreamer consistently generates result with cleaner, more detailed texture than instruct NeRF to NeRF. And in the indoor scene editing result at the bottom, the scene is a bit more complicated, large scale scenes. So the baseline instruct
nerve to nerve actually feels and generate very blurred result. While our considered Dreamer's edit result has bright color and shining appearance as shown. So we also conduct an ablation study or 4 ablation tasks to quantify the fidelity of the distillation from 2D to 3D. We propose a novel metric, distillation fidelity score, DFS, which is defined as a FID between the diffusion generated images and the rendered images from the editing sinks. So a lower DFS indicates better 3D consistency and improved editing result. So we can say removing any of these 3 components result in blurred result and a significantly increase in the DFS. This indicates that all these 3 synergistic strategies are crucial to our high quality editing results. Our most recent Instruct 4D to 4D work further extends this success from 3D to 4D, achieving style or object-specific editing of challenging 4D dynamic scenes. So in addition to style editing, we also would like to edit the 3D shape of the scenes. Our neural editing work integrates the explicit representation of point cloud into the implicit scene representation of nerve, therefore achieving shape editing by directly manipulating the underlying point cloud. So our approach achieves high quality result in both shape deformation and the more challenging scene modeling tasks. So we have introduced geometry awareness into the generative models when extending them into the 4D world. Another important property is that the generative model should be also aware of physics when integrated into the physical world. Well, this can be achieved, let's say, by considering physics simulator. Our recent work shows a simpler strategy in the context of the diffusion models for the task of 3D human object interaction synthesis and prediction. So given the past sequences of human object interaction as illustrated by green meshes, our approach predicts the plausible future interaction sequence as illustrated by the colored meshes. So here the physics means that there should be no penetration between the synthesized human body and object, and their content should be modeled reasonably. Okay. So far, we have discussed how we advance the capability of generative models in the 4D world. So they are geometry aware and physics aware. Now we consider how these generative models can facilitate discriminative tasks. This remains an open question in the community. So here I will briefly show some examples. As you may imagine, one straightforward strategy is to treat a generative model as a data engine and use the generated data for data augmentation. This strategy has been shown great success in simple tasks like image classification, object detection. So here is an illustration from a little more complicated task, open world hierarchical object detection. So we can see the successful segmented object together with their constituent part in the subparts. Our work further demonstrates the effectiveness of these strategies in dealing with the more challenging pixel-level dense prediction tasks, for which the model needs to estimate semantic labels, depths, surface normal, edge, and key points. So we achieve this by extending either nerve or diffusion model to synthesize not only RGB images, but simultaneously also semantic label, surface normal, shading, edge, and key points. These are crucial for comprehensive 3D understanding.
So experimental result in this work shows that our synthesized data greatly boosts the performance on top of the state-of-art baselines for various dense pixel level prediction tasks. So our recent work, iTrainDeep, moves a step further and shows that synthetic data are also helpful for more challenging reinforcement learning tasks. So we introduced a diffusion model to generate full synthetic trajectory based on the initial state and the task prompt. As illustrated in this figure, given the initial state and the task, turn on the light, our synthesizer generates the corresponding trajectory of turning the light. Intuitively, we can decouple our method into two parts, the replay buffer and the learning algorithm. So we modified the original replay buffer with iTrainDeep. So in our modified replay buffer, we store the original sample in one replay buffer, and we store the synthesized sample in another replay buffer, and we randomly get samples from both buffers. Since our iTrainDeep only affects the replay buffer without the need for changing our learning algorithm, so our approach can be applied to all RL method with a replay buffer. So experimental result validate that the generated trajectory significantly and consistently accelerate a variety of online RL methods, right? So the right plot here actually shows noticeable performance when integrating iTrainDeep with a variety of RL algorithms like SAC, RLPD, and Parrot. The left figure further shows the strengths of our method, especially in a little bit more complicated environment where RLPD actually feels it well, but our approach with the synthesized data substantially improves the performance. Okay, so we have shown the effectiveness of using the visual generated models like diffusion models to synthesize additional useful data and to facilitate the learning of the discriminative learning. If you think a little bit further, this actually indicates that the generative models have in fact learned useful feature representations. Therefore, an even simpler approach emerges, where generative models are directly used to extract pre-learned representation without the need for additional data synthesis procedure. We investigate this in the context of text-to-video diffusion models and find that they provide a semantics-aware and temporally consistent representation that can be used for a wide range of downstream tasks, including video object discovery, post-activation, and video object segmentation. So again, here the most interesting observation is we can directly use this kind of pre-trained representation with very light decoder to deal with these complicated video perception tasks. While it is intuitive to assume a visual generated model would likely offer valuable representation for visual perception tasks, our recent work dives into a more interesting exploration. Can linguistic generative models like LMs provide useful representation for visual perception? Since the emergence of LMs, they are mainly used as encoders for language or decoders for tokenized output. On the other hand, due to their training on massive data, LM encodes a vast amount of knowledge, capturing high-level and abstract understanding of the world. So our intuition is that the knowledge within LM can directly benefit the representation learning of another modality. For example, refining and enhancing the representation of images from cloud time series data. Along this line, we discovered that a single frozen transformer from LM can be an effective encoder layer for visual tasks. Our approach is quite simple. Directly appending a pre-trained LM transformer
layer after the kind of original encoder layers of any visual backbone. Because of the mismatch of the dimensionality, we introduce additional LMLP to linear layers. We can see the approach is basically as simple as it. Despite its simplicity, this paradigm is actually generalizable across a wide range of modalities, including 2D images, 3D point clouds, videos, and non-semantic time series, and be effective across a wide range of tasks like image classification, point cloud classification, action recognition, and motion forecasting. When combined with the language modality, it is also useful for 2D and 3D vision language tasks. By default, here we use the last transformer layer from Llama. As for our design choices, a crucial analysis is that we first remove the LM transformer while keeping the same number of trainable parameters, which is basically plus MLP as shown here. So the result shows that the performance improvement is not as large as using frozen pre-trained LM block. So this observed improvement for visual encoding is not just a result of a larger capability or large capacity, but more like the leverage of this additional LM layer. We further analyze if fine-tuning the frozen transformer could lead to better result. So this is basically shown as Llama. From this result, we can see that full fine-tuning actually leads to a performance drop because of overfitting to the training set. So in the following experiment, we mainly use these frozen LM layers. We further found that our discovery is applicable to various LMs and layers. For example, here we use another LM OPT. We can observe that, again, there is kind of consistent improvement, not just the last layer of Llama can improve the performance, but also the last few layers. This shows that this kind of behavior is somewhat generic. So from the experiment, you can also observe that often the highest performance improvement comes from the last few layers of LM, but the beginning few layers, you can say, is actually not effective. So this is reasonable from kind of in-tuning perspectives. The first few layers are basically converting words to embeddings, while the later layers conduct high-level recognition and reasoning, which might be the best beneficial to the other tasks. So we additionally consider different scales, OPTs, and with their final transformer blocks. So as shown in this table, we can see that the improvement of LM for visual encoder only emerges with LM with sufficient large scale. So now we would like to ask this question, right? Why pre-trained transformers in LM have such an effect on visual recognition tasks? What is the underlying mechanism? Our idea is this kind of information filtering hypothesis, which is derived by our observation of the feature activations, actually. So we can say from this kind of feature visualization, it explains how a frozen LM transformer actually improves the representation ability on visual tasks. Specifically, we visualize the feature activation either in magnitude or frequency. Surprisingly, the model trained with a frozen LM transformer shows the emergent tendencies of segmenting the foreground objects, which is not observed in the original event. For example, you can see, right, so the bird is basically clear show on the activation in either frequency or magnitude domain. So this is somewhat surprising because this kind of segmentation ability was only demonstrated on self-supervised VIT like Dino before. So encouraged by this behavior, we formulate our hypothesis as LM benefit from distinguishing and amplifying the informative tokens. So as a side note, here we are not totally clear about which layer actually is LM attention or LM FM, or we are not clear is most notable in the magnitude or the frequency. This needs some further exploration. But what we show as a consistent behavior is that the magnitude after output by the final layer clearly illustrates the target objects. Again, this phenomenon is not only limited to classification. So on other tasks like action recognition, right? So this kind of information filtering hypothesis is also supported and observed. So here we also visualize the tokens on actual action recognition. So different from the image task, so video tokens are activated joint in all the frames. So every video token is a cube covering 2 frames and image patches of 16 by 16. So as shown in the low stress showed row, right? So the model with llama focused to the foreground with less noise. And furthermore, the high stress shows that the most focused frame to indicate the temporal selection of the models. So after ending llama, we can see the model significantly introduce a larger activation on the frames with actual manipulation movement or the hand object interaction. We also consider another task. So this is basically an even more challenging task, a 3D vision language task called situational QA, where an embodied agent is given position and then question to answer. So in this example, the situation is basically I'm standing in front of the table and facing trash can, and the agent has to understand its location and facing like the green arrow. And the question is how many chairs are at the table behind me. So what we visualize here is basically this kind of activation of the seed point from the point cloud, where a brighter color indicates actually bright color indicates a larger activation. So we can clearly observe that ending llama enables a sharper activation, especially for locations behind the agent, which is consistent with the situation. Okay, so I have shown the remarkable effectiveness of utilizing generative models, such as LM, to perceive the world, not only the linguistic world, but also the visual world. However, this alone is insufficient to address the complexity of the real world. Recently, there has been a growing interest in extending generative models, particularly LMs, as agents for decision-making and problem-solving. As I discussed earlier, right, so this is promising for 2 key reasons. So first, LM can perceive the world through natural language. And with a vision language model, it can also integrate image-based perception. And more importantly, LM acts with common sense and high-level task comprehension, so which is difficult for traditional control theory and RL agent, particularly in task transfer scenarios and with highly complex tasks. To achieve such operational agent, several essential capabilities are required, such as internal reasoning and external decision-making or acting planning. There are existing methods that have focused on a specific capability, but constraining LM to specific tasks. So for example, as a foundation to many follow-up work, chain of thought, COT, is introduced for reasoning, which guides basically LM to think step by step and provide a justification for the answer. So this means a unified framework that is seamlessly integrates all these capabilities is essential and much needed for effective LM problem solving. So our recent work, language agent tree search LARS, fulfills this need as the first method by unifying reasoning, acting, and planning into a general prompting framework based on the Monte Carlo tree search. And therefore, outperform prior method from any individual domains. So how we integrate all this capability into one system? Well, to achieve this, we build upon the tree of thought, TOT, which addresses planning by combining classical search algorithms with LM. So we improve upon TOT with the 4 step. And so here we use an example of buying an apple as an illustration. The first step is prospective evaluation, which is kind of a smart initialization of value functions. Suppose I want to buy an apple, right? So I want to make my LM agent to buy a Fuji apple on Amazon, given the XML file of the website. Given such website, the LM agent has many possible choices. For example, extract the keyword and enter Apple in the search box, or enter Fuji in the search box, or even simply log out as it feels that it shouldn't buy Apple here. If we use a search algorithm such as DFS or vanilla MSCTS, we will have to evaluate each choice many times before we figure out which action is good, which is very inefficient. So here, if we leverage the common sense encoded in the pre-trained LM, which is the knowledge that traditional planning algorithm always dreamed for, so we can actually let LM to perform prospective evaluation and to figure out which action might be the most promising. This will save many trials for us. The second step is basically heuristic selection, where we sample multiple next steps and select the most promising one with MCTS rules, right? So we select such a step by generally considering the novelty and the LM evaluative value function of the candidate next step. And the third step is the feedback update. So if we succeed on the first trial, we can simply end the search and output the answer. However, our agent can make mistakes from time to time, right? For example, it might mix Apple pencils with real apples and purchase the wrong item. So to learn from such failure cases, we use a feedback update that updates the value function along the path trajectory. So the last step is the self-reflection, where we fully leverage LM's comprehension ability to let itself generate instruction on how to do better for the next trial. So for example, it might figure out, right, it shouldn't mix up Apple electronics with real apples, so which will go to the next trial as part of the prompt. To sum up, in LARS, right, so an external environment enhances both reasoning and planning by grounding it to the real world condition. This also reduces some kind of hallucination. And reasoning improves acting by organizing feedback and context. And the planning as a search over acting trajectory introduces global trajectories and global decision makings. So notably, our approach is applicable to a lot of tasks for both reasoning and the decision making. This is benefited from the shared state space of action, thoughts, and observation. So from this different tasks, including mathematical reasoning, programming, question answering, and the real world navigation, we can see there is a consistent performance improvement from LARS, making it as a leading approach in LM agent learning. Okay, so far we have mainly focused on the exploration of individual models, each a powerful tool in its own. However, the potential of generative models not lie in just isolation, but in their collaborative synergy. So can we compose and synergize heterogeneous generative models like LMs and other generative models, while each model illuminates different aspects of the world? We consider this synergy of generative modeling in the context of generating human-object interaction, HOI, given text description, by fusion of LMs, motion generative models, and interaction price. So here, basically, LM understand the semantics of human object interaction. Motion models understand the dynamics of the physical movement, and additional interaction prior, like physics, can be also integrated. By fusion of them together, this enables us to bridge the gap between textual comprehension and the physical movement, so as to allow us to generate this kind of 3D human object interaction, particularly in a zero-shot manner. So more specifically, our task is defined as, given a task description of a human object interaction, we want to generate this kind of interaction sequence, as shown here, that aligns with the textual guidance. So, but this task faces several challenges. So the first is the complex property of object, including various shapes, as well as diverse motion patterns subject to internal physical characteristic of objects. And also the intertwining of the dynamics of both the whole body and the object and their shapes. So for example, the body needs to fit on the surface of the object during the interaction and driving the object to move. But these are not the main difficulty here and not the main fatal issues here. The crucial thing is that we only have a limited amount of 3D HOI data. And we don't even have any paired textual description together with this kind of HOI data. So this leads us to question whether it is feasible to learn text condition HOI generation in a zero-shot manner without paired supervised data. To address this challenge, right? So our key insight, as discussed earlier, is to leverage a variety of knowledge through generative models, not dependent on text interaction pair data. And importantly, such knowledge can be individually harnessed, ultimately composed, due to that semantics and dynamics can be decoupled in HOI. That is, semantics can be shifted by human motion and the initial object pose. Meanwhile, dynamics, that's the subsequent previous object, is driven by forces applied by the human under the law of the physics. So the semantics of interaction can be harnessed from LM, right? So which is with a pre-trained text-to-motion model. But such large models lack a crucial low-level dynamics. So we address this by developing a word model that predicts the subsequent state of an object affected by the interaction. So more specifically, we propose InterDreamer formulated as an MNDP. We basically tokenize humans and object dynamics into actions and states. Under such an MNDP, our framework starts with high-level planning, which basically, given the text description, deciphers the detailed text. As shown in this example, right, we refer to the answers provided by LLM for extracting object categories and body parts. And we also use that to provide a modified description. So it sort of narrows down the vast range of possible interactions into a more manageable distribution within the capability of our framework. So we utilize few-shot prompting and the chain of thought prompting to enhance the in-context learning capability of the LM. So the low-level control aims to create the initial state and the sequence of human actions such that they correspond with the information provided from the high-level planning. And here the interaction retrieval is basically set up an initial object state based on the rules we discussed. So the key to the retrieval is the information provided by the high-level planning in the previous step. And the output is basically a contact map that can lead an object of its initial pose. So we then have this kind of text-to-motion model, which is pre-trained to generate the actions based on the rephrased text. And finally, with the initial state and iterative generated action from the low-level control, so the word model or the dynamic model simulate the state transitions affected by this kind of applied actions. So a naive method would be directly taking the wrong action, right, as a condition, which suffers from this kind of severe overfitting issue, generation issue, right? So during inference. So the dynamic model is like to encounter some kind of actions that don't exist in the training data. So we basically model the interaction from the context vertices on the object. This kind of locality ensure that the dynamics models focus on only the interactions in the contact region without being distracted by the motion of the body parts that are not irrelevant to the object. And the most important thing, so the dynamic model is the only component that need to be trained in our framework. All other components are just used as off-the-shelf models. So we conduct a quantitative comparison of our approach with the existing text to HOI work with the framework of supervised learning. Again, I would like to emphasize ours is complete unsupervised zero-shot manner. So this comparison is a sort of unfair. So we directly evaluate our master by testing our trained models on their annotated data available from their website, specifically retrieving their generated videos for direct comparisons. So remarkably, right? So even with training on this kind of a data set, our approach generates high quality interactions. And the more impressive, our approach is able to generate vivid interaction sequences given this even longer and more complex text descriptions, and shows effectiveness in synthesizing complex interactions involving dynamic changing objects, dynamic changing content, such as a handle. Okay, so as a summary, in this talk, I have shown how we bridge and unify generative models and discriminative models, and further compose heterogeneous and synergize heterogeneous generative models to create a somewhat supermodel. So these integrations empower AI system and agent to advance their comprehensive perception, understanding, reasoning, acting, and planning capability within the open real world, potentially in a zero-shot lab. Again, this is a very initial step towards a bit long-term vision. That's all. Thank you for your attention. Yes, please.
Is there a straightforward way of incorporating some kind of physics into the pipeline?
Yes. So you mean the last part of the work, right? Again, so here, that's a good question. I would like to address it from two aspects. So first, here we want to show that it is possible to learn this, generate this kind of plausible interaction sequence without any additional tools for physics simulation or something like that. So of course, because you don't have this additional guarantee, right? So the result is not perfect. But again, it's kind of a comparable and even outperform the existing approach with the supervised data. Okay, that's a main investigation in that line of work. Meanwhile, I agree with you, if you want to fully model the physics, you probably need some kind of physical simulator. You can integrate that. We have some ongoing work actually uses physical simulator to guarantee the physics and integrate it into this kind of. Thanks for the question. Yes, please. Okay. Yeah, I think that's great questions. Again, this is a kind of open question, right? So people are trying to leverage these different modalities to align them and generate a stronger representation for different modalities. My 2 cents are first, there's a somewhat alignment between this representation learned for different modalities, even when you don't learn them in the cross-modality scenarios. That's what we show in that kind of the piece of work, right? So even you train the LM with a pure language, you don't have any access of visual data. It can still help with the visual task. Yes, we showed a variety of tasks, including 2D image classification, 3D point cloud classification, action recognition, and motion forecasting, and even 2D and 3D vision language reasoning. So across the board, right? So they have consistent benefit, consistent improvement, but the biggest improvement still comes from, let's say, semantic tasks. For example, image classification, video recognition. There is some benefit for this kind of motion forecasting. That's a kind of non-semantic task. But the gain is sort of much less noticeable. Yeah, coming back to the question. So what I mean is, while this kind of representation are learned for different modality, there is still some kind of sharedness, some kind of alignment between that, because essentially they are learned from the same word, right? Same underlying word. So there is some kind of alignment. That means that you can sort of compose that with minimal, let's say, tweaking or minimal fine-tuning, you can actually have a good model. But meanwhile, they also have some kind of complementary aspect. This is what I show in this kind of the last piece of work with human-object interaction generation. LM basically understand the semantics, but it cannot understand the low-level dynamics and physics. Then you need this kind of additional model that is good at understand this kind of low-level dynamics, physics. But once you compose them, like this kind of high-level planning and the low-level control, right? So you can sort of address tasks that might be very challenging. Thank you. Yes, please.
Here you show you can incorporate the knowledge from generative AI, such as LM, to help image classification tasks. So how do you ensure the LM generated content is correct? Like say also other generative models like motion generated data. Like what if they generate some false text? So how do you work with that?
Yeah, so that's a good question, and also a slightly different aspect, right? So what we show here is basically they are helpful, but of course there are successful cases, right? But there's also some misleading and let's say failure cases. My sense is probably we need kind of some additional layer that sort of tells you maybe can able to predict this capability in advance, right? So if it is helpful, you should use that. If it is not helpful, you probably don't want to use that. So you can have a little bit more hybrid strategy to some extent. But I guess the most important is first to understand. Again, I think that's an open question in the community, right? So under what setting this different modality can help with the target modality, why it helps, right? So what we show is this LM can actually help you to identify the desired foreground objects, right? That it helps, but there is a need. We need some additional more in-depth and exploration analysis under what settings actually can do so, in what setting we cannot do so, and then we can probably have a little bit hybrid strategies to further improve.
Thank you. We're running out of time, so that's give one. Thanks.
Thank you, everyone.
I'll introduce myself. No worries. What's the when does this technically end? 4:15? Okay, half an hour. That's plenty of time. All right, good afternoon, folks. Today I'll be talking about the foundational few-shot object detection challenge. So my name is Nihar Perry. I'm the guy on the right, the second guy over there. And today we'll be discussing the inaugural challenge and highlighting some of the insights from our community. So I think the first thing to call out here is that we've seen remarkable progress in zero-shot open vocabulary detection performance. And by simply typing in a text string, you're able to detect basically anything that you can imagine. So by simply typing the keywords laptop, you're able to detect laptops in any arbitrary image. So this raises a natural question. It seems like, given this impressive performance, it seems like 2D object detection is a solved problem. Should we be able to use these VLMs as automatic annotators? And can we simply use this to annotate large-scale data and be able to scale up our vision language models? And I think the answer as of right now is not quite. So these VLMs are not quite there as automatic annotators. And I think we need to observe this problem a little bit deeper. And it really turns out that the key reason why we can't necessarily use VLMs out of the box is because there's poor concept alignment between the data that these VLMs are pre-trained on and the target domains that we actually care about here. So in this example on our left, we can take an off-the-shelf state-of-the-art VLM. We can type in the text string truck, and our VLM will detect the entire truck, whereas the annotation is just the front cab. Similarly, for bicycle, we find that when we type in the text string bicycle, VLMs will only detect the part of the wheels of the bicycle. But according to the annotation instructions in new images, this includes both the bicycle and the rider. So importantly, there's this disconnect between the data which we use to pre-train our models and the web scale foundational knowledge and what we actually care about in target domains. So importantly, the concepts for particular data sets are misaligned. And at first glance, this seems like it should be pretty easy to solve. And this issue itself is not all that surprising because human annotators themselves need multimodal concept alignment. So when we want to collect a new data set and when we want to annotate this data set, we usually need to describe with a few visual examples, some rich textual examples, and oftentimes some examples of what we don't want them to annotate to get these human annotators to understand what we actually mean when we define some of our target concepts. So one natural question is, because we want to be able to turn VLMs into automatic annotators, can we actually align our foundation models to work more like how we align human annotators? And the answer is obviously yes. So ideally, we'd like to be able to fine-tune these models with a few multimodal visual and textual examples. And for those of you familiar with the task of few-shot object detection, what I just described, using a few examples of text and images, sounds a lot like this few-shot object detection problem. But importantly, the existing setup is incredibly limited. So the existing few-shot object detection setup has a set of base classes, so something like Coco that you can train on, some subset of Coco that you can train on, and they evaluate on some other subset of Coco, which they call the novel set of classes. And importantly, there should be no overlap between these two sets. And given that we want to be able to leverage the foundational VLMs and given their strong performance, it seems a little bit strange that we can't even use these VLMs in the current paradigm. So foundational VLMs violate current FSOD benchmarking protocols. So importantly, as I mentioned, the standard setup has the split between base and novel classes, but VLMs like CLIP are trained on private data sets. So we don't even know what it means to be a base class. There's no way to identify whether or not something was included in CLIP pre-training. And we also have this other concept called concept leakage, which is something which existing FSOD benchmarks try incredibly hard to avoid by having disjoint sets between their pre-training and fine-tuning sets. And importantly, for common FSOD benchmarks like COCO, some of these novel categories which they want to avoid training on are things like cars, cats, and people. So these are the things which are novel in COCO, but if you really think about it, these are things which we see all over the internet. So your foundational vision language models have seen many examples of these in practice. So concept leakage is sort of impractical and maybe even impossible to avoid if we want to use VLMs for this task. The other sort of surprising observation here is that zero-shot VLMs beat state-of-the-art few-shot object detectors. So if we think about that statement for a second, this is really not all that surprising because zero-shot VLMs are trained on internet-scale data, whereas existing few-shot object detectors are basically only trained on COCO. So a claim here is that if we really want to embrace this, this foundational view of the world, pre-training on large-scale data will be a key enabler for generalization. So importantly, if we really want to buy into this notion of foundational few-shot object detection, we really need to make these foundational models a first-class citizen. So if we want these foundational VLMs to enter the conversation of few-shot object detection, we really need to embrace the concept of pre-training, and we need to embrace the concept of concept leakage. And this really requires that we reframe what we mean when we say base and novel classes. So to make an analogy to the standard few-shot object detection setup. So in the standard setup, your base classes are some subset of COCO, but in our proposed setup, this is really data in the open world. So this is all of the internet pre-training data that you can get your hands on. And in the existing setup, your set of new classes will be a few-shot set of examples from some subset of COCO. But rather than doing this, we propose that the novel set or the few-shot classes should be whatever classes you actually care about in your target data set. So given this problem formulation, given the motivation of trying to use foundational VLMs to bridge the gap between human annotation and automatic annotation, we've set up a challenge called the Foundational Few-Shot Object Detection Challenge. So first I'll talk through the challenge setup, highlight a couple of the baselines which we propose, and then discuss some of the community insights. And interestingly, even in the few short months which this challenge has been live, the community has more than doubled our strongest baseline performance. So I think this is in and of itself a very exciting result. So first, the challenge setup. Unlike the traditional few-shot object detection task, we repurpose a data set called new images. And this is a little bit different from the standard setups which use COCO or Pascal. This is actually a 2D autonomous vehicle data set. And this has many challenging categories like pushable, pullable, and debris. So these are things that, just given the textual description, it's not quite obvious what we're trying to detect. So this further motivates the need for multimodal examples. And why do we choose new images over some of the more traditional data sets? The answer is because new images provides multimodal annotator instructions. So this is unlike many of the contemporary data sets. We actually know what the new images curators instructed their human annotators to label whenever they constructed this data set. And unfortunately, new images is one of the few data sets which we were able to find which includes such rich multimodal annotator instructions. So I think, moving forward, given that we find these multimodal instructions are such a key asset for aligning foundational vision models with target domains especially in the context of this challenge, we hope that future data sets will actually also release these. Since this is an object detection task, we do evaluate using mean average precision, and it's nothing fancy here. We simply repurpose COCO style evaluation for the 18 classes within new images. And we outline a couple of boundaries for this challenge. So whenever we talk about foundational models, one of the challenges is understanding what we can and can't train on. So the first thing is we allow competitors to pre-train on anything except two data sets. One is new images and the other is new scenes, because these two data sets are basically the exact test domain which we're trying to evaluate on. So it doesn't really make sense to let people pre-train on these. And competitors can fine-tune on 10 shot examples within the new scenes or new images data set. So for each of the 18 classes, we provide competitors with 10 examples per class, and this is what they can train on. So now that we understand the challenge setup, we define 3 baselines. So first, we define a federated fine-tuning baseline. And this comes about from a rather interesting insight that few-shot object detection benchmarks are actually federated data sets. And what do I mean when I say federated data sets? A federated data set is a collection of smaller subdata sets where each image in this smaller subdata set is exhaustively annotated for a single category. So here on the left, we can actually see 2 examples of, although they're a single image, these are technically federated data sets. So for the example on the far left with the bus, within this image, all bus examples are exhaustively annotated. There's only one bus. And we don't guarantee that anything else in the image is annotated. Same thing for the example with the motorcycle. So given this example, it intuitively may seem pretty straightforward why standard fine-tuning doesn't work. Because if we apply standard fine-tuning techniques, all unannotated classes are considered negatives, and this will negatively impact your fine-tuning performance. Okay, so how do we solve this? Well, we leverage the zero-shot capabilities of these foundational VLMs to generate pseudo-labels. But trusting these pseudo-labels doesn't necessarily get us the performance that we want, because we can't necessarily trust that the VLM is aligned to our target data set. So rather than trusting the predictions themselves, we can actually use these predictions to identify what classes are not in the target images. So we can run our VLM, and our VLM tells us that there are no examples of strollers in these 2 examples. So when we actually fine-tune our data set, we can apply a penalty such that our detector doesn't predict that there are any strollers in this data set. So the second baseline uses multimodal in-context prompting. So the previous example is a more traditional detector-based baseline, but it turns out that in recent years, there has been tons of work in multimodal prompting. So here we have a model called MQDet, which takes as input a few shot image queries and some textual descriptions. So we can, given these training image queries and this text description, we can use the VLM, which is pre-trained on a large scale amount of data, to detect this instance of a stroller in a new test image. So importantly, we don't use any gradient-based fine-tuning here. We're simply tokenizing the few shot examples from our annotated instructions and using this as context to detect what we mean when we say stroller in a new data set, in a new image. And we can actually look at some of the incredible performance from state-of-the-art multimodal queried VLMs. So given a simple image prompt or a text prompt, we can without any fine-tuning, detect all examples that are similar to the query within the image itself. So this sort of highlights the power of scale and the power of multimodal queried inputs. So the third baseline, which we want to highlight, is using multimodal chat assistants like ChatGPT to improve the quality of few-shot object detection. So one key insight is that whenever we actually want to build a data set, there's an iterative process between stakeholders and human annotators when constructing the annotator guidelines. So human annotators often need many rounds of clarifications and iterative feedback to fully grasp the target concepts. And we can even see this within the new images guidelines themselves. So let me read a portion of this guideline to you. New images defines if an object has extremities, the bounding box should include all the extremities, and in parentheses, exceptions are the side view mirrors and antennas of vehicles. So even in that particular example, you can almost see how they're defining what to do and what not to do. And this probably came about through multiple rounds of iterations, where a human annotator probably annotated the wrong thing at first and tried to fix this in subsequent iterations. So we actually construct a baseline using ChatGPT 4o. And the first thing we try is to ask ChatGPT, given the list of new images classes, classify the given image crops and output a confidence score. And surprisingly, it does something reasonable once in a while, but more often than not, ChatGPT will give you highly correct yet incorrect labels. So another thing which we can try is rather than asking ChatGPT to solve the classification problem for us, let's rather try and get ChatGPT to give us more creative ways of prompting. So using ChatGPT in the loop as a black box optimizer to improve the quality of our prompts. So given this visual example of a debris, we can ask ChatGPT what it thinks it should call these things. So for example, it tells us maybe we should call it a traffic control sign, temporary warning sign, road sign, or warning boards. And given all of these rich textual synonyms, we can actually use these to prompt a VLM, and we find that this improves performance. So of all the three baselines, we find that multimodal prompting, so the second baseline, which I highlighted, performs the best. But despite the strong performance which we got with our baselines, we were kind of blown away by the response from the community. So we ran this challenge for just a few short months, and we had over 50 submissions from 8 teams. And notably, the top team beat our strong baseline, which is MQGLIP, by more than double. So the top baseline achieves 45% accuracy overall versus our baseline, which is 21.5%. So unfortunately, the top performing team did not provide us any details about how their method works. But even without this, we can analyze some of the qualitative and quantitative performance. So first, we note that this top performing model provides significant improvement in performance across both common and rare categories. So you may be thinking to yourself, I would have thought car detection accuracy would have been really high, right? Because there are tons of examples of cars on the internet. But it turns out that because of the specific quirks of the new images annotation guideline, for example, cars that are not in the drivable area should not be annotated and should not be detected, right? So being able to specify this through few-shot fine-tuning actually significantly improves car performance. And as you may expect, having a few-shot examples of these rare and ambiguously defined classes like pushable, pullable, and debris also significantly improves performance. And we can see this play out in the qualitative examples. So our baseline incorrectly predicts that barriers and traffic cones are considered debris. But through the fine-tuning that this method performs, they're able to correctly identify the one example of debris in this image, and they don't incorrectly classify anything else as debris. So I think this is a pretty cool result. So I'd like to also highlight 2 more methods, and importantly, we do have details about these 2 methods, so we can kind of dive a little bit deeper into the specifics. So the second place team achieves 32.5% accuracy, and the way in which they do this is a little bit unsurprising. So they pre-train on basically every data set known to man, and the large-scale pre-training is one of the key reasons why this method performs significantly better than our strong baseline. But they have an interesting approach beyond just pre-training on tons and tons of data. So similar to our multimodal chat agent baseline, they first try to prompt ChatGPT with the few shot examples and ask for descriptions. So given this image crop, what are the referential descriptions which might be able to describe this particular instance? So given these referential descriptions, we can then prompt a VLM with these text descriptions and image prompts and match the specific random combination of text descriptions that best aligns with the ground truth. So what this means is this simple heuristic identifies which particular ground truth, which particular random combination of referential descriptions best matches the ground truth descriptions of the within the data set. So once we have a set of referential text descriptions and images, we can pseudo-label the rest of the data set. So importantly, as we showed earlier, the new images few shot data set is federated in nature, and this means that it's not exhaustively annotated. So this method uses the textual descriptions to generate pseudo-labels, and given the images, textual descriptions, and pseudo-labels, we can then fine-tune the VLM. And specifically, this paper uses Grounding Dino as their backbone model. As I mentioned, the key to addressing federated labels, or one of the key ways this paper addresses federated labels, is through pseudo-labeling. So given an input image here with the single motorcycle that's annotated, we can generate pseudo-labels and feed this back into the VLM for self-training. And this paper finds that this is incredibly effective. So qualitatively, we find that performance on rare categories like barrier is significantly improved. And one of the key insights is that aligning the prompt and importantly, aligning the textual description to what ChatGPT thinks is a better description of this particular image significantly improves performance from 11% to 46%. So notably, in the baseline, you can prompt with just the word barrier, but barrier is very ambiguously defined. And this sort of iterative process finds that single short tart barrier is a much more descriptive way of identifying this particular instance. Okay, so we can look at some visual examples here, and you can see that MQGlip, which is just prompted with barrier, identifies that some debris is mislabeled as barrier, but this method finds that they're able to remove these false positives. Okay. And our third team here, which we want to highlight, does something a little bit differently. So importantly, although they also do pre-train on basically every detection data set, they have a very different fine-tuning strategy. So instead of using just positive pseudo-labels for addressing the federated nature of foundational few shot data sets, they use both positive and negative pseudo-labels. So again, they use off-the-shelf VLMs like Clip and others to identify examples that are likely to be within the federated few shot data set. So the examples on the left here are things that we know are potential object categories that are within the data set, because these are the 18 classes which we care about. And we can mine a set of negative pseudo-labels by simply querying large text corpuses of nouns. And using both positive and negative pseudo-labels, we can then fine-tune these object detectors. And importantly, differently from the previous method, this approach uses prompt tuning. So given an input text string called stroller, we can encode the class name with the text encoder, and we can throw away the text encoder. And we can fine-tune the embedding, just the embedding, to better align with the target class or the visual example here. And importantly, this doesn't require that we have interpretable tokens. So if you take this fine-tuned embedding and look for the nearest neighbors, you'll find that sometimes these don't really make sense. And this is one of the benefits of using these implicit encodings. Okay, so we can look at some qualitative results, and we find that MQGLIP, or baseline, is basically unable to detect emergency vehicles, but this method is able to significantly improve detection of emergency vehicles. And one hypothesis here is that because we're able to use negative prompts, so we're able to train the detector to explicitly identify that the car on the left is not a police car, we think that this is what really contributes to the improved performance. Okay. So a retrospective on the first challenge here is that we outlined some limitations of what data people can and can't train on. So although it makes sense that people should not train on new images and new scenes when we evaluate on the new images foundational object detection challenge, does it make sense to allow people to train on other in-domain datasets, other autonomous driving datasets? And our answer is yes, because in a foundational world, in the foundational paradigm which we want people to live in, it really doesn't make sense to allow people to train on some data and not others, unless it's absolutely necessary, such that we're not training on the test data set. So that seems to be the only limitation in terms of what people can and can't do. Another perspective here is, rather than limiting the data that people can train on, maybe we should be testing on totally out of distribution data. So although many of the pre-training data sets, like COCO, contain similar images to urban scenes, so although COCO contains cars, maybe the right answer here is that we should be training on data sets, or we should be evaluating on data sets that are totally out of distribution. So something like medical images or aerial photography, which is probably unlikely to be captured in standard pre-training data sets. And yet another potential solution is to collect totally sequestered data sets. So if I were to go outside and take a picture right now, I can guarantee that it will have never been in any of the pre-training of these foundational models. So collecting and curating a data set that will never be released onto the internet may be one way in which we can evaluate such foundational models in the future. Okay, so with that, I want to highlight a couple of future directions for this foundational FSOD challenge. Our top competitors seem to have two different ways of dealing with alignment. So we saw examples of explicit alignment, where people can explicitly mine different prompts and examples versus implicit alignment through prompt tuning, where we didn't necessarily need a interpretable set of tokens. So identifying which is actually the right strategy remains to be seen. There's also scope for improvement between textual versus image alignment. So a lot of the top methods this year focused on improving prompting, textual prompting, but there is scope for using generative models. For example, although we don't see many examples of strollers in our data set, we can query DALL-E 3 for examples of strollers, and maybe we can use this to augment our training data sets. As I mentioned previously, out of distribution data sets is another area of interest. And lastly, although we really focus on 2D foundational detection in this challenge, there's a very natural extension to 3D as well. So with that, I'd like to thank the organizers of this challenge, and in particular, I'd like to highlight the efforts of the lead author here, Anish. So shameless plug, Anish is applying for PhD programs. He's an expert in VLMs. So if this stuff is something you're working on, go talk to him. And with that, I'd like to thank the audience, and I'm happy to take any questions. Thank you. Who's next? Yeah. Yeah, so my sense is whenever you try and crop a bounding box and pass it to foundational model for classification, you lose out on a ton of context. And I think that context is really what allows detectors to identify different classes. So I think that would be my bet, is because MQGlip is trained actually as a detector, it's able to leverage the surrounding context and do a better job at classification. So the real difference there isn't the foundational level of pre-training, but rather sort of the alignment to the task. Mm-hmm. Yeah, absolutely. So I think the way in which MQGlip uses the few shot examples is through in-context pre-training or in-context learning. So I think this is important to distinguish between the interface of the challenge itself and sort of the way in which the model itself operates. So if we think about this as a black box, the method is still taking as input the training examples, and whatever they're doing with it is sort of totally something which people can play around with. So it turns out that, you know, if we compare baseline 2 with baseline 1 does more traditional fine tuning, but that performs worse. So clearly the difference isn't, do we do gradient-based fine tuning versus in context prompting? So I think this is another area of interest for future exploration. Cool. Thank you very much.
Yeah, hi, can you hear me?
Yes, but let's wait. Just want to make sure that
Okay.
the sharing.
Okay, guys, so this is our next challenge. It's about open vocabulary part segmentation. So Professor Meng, she will present remotely, and also we have another student over here to present in person. So, Professor Meng, would you please check if you can talk to see if we can hear you, please?
Yeah, can you see my screen sharing?
Yes, we can see you. Yes, we can hear you.
Okay. Let's get started. Hello everyone. My name is Meng Wei, and I'm a PhD student from the University of Hong Kong. This is the presentation of our Open Vocabulary Part Segmentation Challenge. I'm your host today. First of all, thanks to all my co-organizers from Shanghai AI Lab, the University of Hong Kong, the University of Sydney, and the University of Macau. Okay. In this presentation, I will first introduce the background and motivations of this OVPass challenge, and then I will walk you through the challenge setup, explain our objectives, and then I will introduce 3 outstanding teams who will share their innovative approaches. Okay, finally, I will give a brief summary and discuss some future works. Okay. Every day we come across a diverse range of visual and textual content. This open world is full of abundant and constantly evolving information, which presents both challenges and also huge opportunities for artificial intelligence. Recently, there have been significant improvements in how we can use this open world data to develop large foundation models with advanced pre-training techniques, such as the contrastive learning, which we have seen in the groundbreaking models like CLIP from OpenAI. These foundation models give us the key to unlock the full potential of the open world data, allowing us to explore new frontiers in our AI research. So far with these foundation models, the research field of open vocabulary learning has shown impressive results across a wide range of object-central applications, like object classification, detection, segmentation, language grounding, and so on. But compared to what has been achieved in the object-level open world understanding, the exploration of part-level understanding has not received the equal attention. Actually, this detailed level of comprehension is much more practical for real-world applications, such as in autonomous driving and in robotics, like object affordance learning and object manipulation. We identify two primary challenges in adapting these foundation models to fine-grained understanding. Firstly, these foundation models have limited part-level recognition abilities, as they were not explicitly trained on abundant part-level data. And in the analysis of several state-of-the-art vision language foundation models, we can observe their consistent struggles to recognize the object parts or fine-grained object affordances, which we think is resulting from the scarcity of the relevant training data. And secondly, there is the open granularity problem, which in real-world applications, we usually expect the models to dynamically adjust their granularity to segment parts at different levels of detail to fit various scenarios. Okay, so we set up this OVPaths challenge. Our first objective is to learn a model to handle the parts of the relevant novel objects without extensive retraining. For example, if we train a model to segment the defined parts of a cat, the model should also has the zero-shot generalization ability to segment the corresponding parts of a dog. So in the first track of our challenge, we focus on the generalized zero-shot path segmentation task. Firstly, we provide the Pascal part 116 dataset. This dataset is improved from the original Pascal VOC 2010 dataset. It has A431 training images and A50 testing images, covering 116 object part classes across 17 object classes. And we split the object part classes into seen and unseen class splits. The seen classes includes the parts of 12 objects, and the unseen classes contains the parts of the remaining 5 objects. each unseen object has a corresponding relevant object in the same class split. The models should be trained only on the same classes and will be tested on both the seen and unseen classes. And for evaluation, the metric is calculated with the mean IOU across both the seen and unseen classes. And we choose the harmonic mean IOU as the primary metric. Also, we assume that the oracle object masks are known. Okay, the second objective is we want to explore the model's ability to generalize across different part granularities, which means the trained models can also handle customized user prompt, which may require paths defined in different level of details. So in our second track, we focus on the cross dataset path segmentation task. We also provide AD20K 234 dataset, which has 73447 training images and 1016 testing images, covering 234 object part classes across 44 object classes. But although our provided baseline is trained on this dataset, we also allow usage of other datasets, excluding the in-domain test set from Pascal part 116. We make this track more flexible. If the participants want to use pre-trained foundation models, which already can segment the parts of objects, this is also permitted. But the foundation models should not be trained on the Pascal part 116. Our baseline we fine-tune some ways of the CVPR paper in CalipSec, and the evaluation measure of this track is the main IOU across all object classes. Also, we assume oracle object masks. And this is the challenge results. In track 1, we receive submissions from 8 teams and submissions from 7 teams in track 2. Some teams submit results to both tracks, and we are denied to invite the teams which submit the top 2 results in track 1 and track 2 for sharing their solutions. The first team is from Xidian University, China. They won the first place in track 1 and the third place in track 2. The second team is from KAST, South Korea. They won the second place in both track 1 and the track 2. And the final team is from the University of Hong Kong. They won the first place in track 2. Congratulations for the winning teams and thanks for their outstanding efforts. Okay, for the next part, let's move to the team presentations. I think I will stop my sharing now. Okay. Hi, Shujian, can you share your screen?
I will show the recording of our master. Can you hear?
Yes.
Okay.
Good afternoon, everyone. I'm honored to have the opportunity to share with you the methods I used in the Open Vocabulary Part Segmentation Challenge.
Sorry. Hi, Shujian.
Hi.
Hi, Shujian. I cannot see your screen.
Okay, thank you.
Okay.
Okay.
Good afternoon, everyone. I'm honored to have the opportunity to share with you the methods I used in the Open Vocabulary Part Segmentation Challenge. My team is from the School of Artificial Intelligence, Xidian University in China, and I am team leader Xuejian Gu. I am currently a master's degree student at the School of Artificial Intelligence, Xidian University. My research interests include machine learning, deep learning, and multimodal learning. Team members include Xinliang Wang and Kexin Zhang. We were supervised by Professors Fang Liu and Lingling Li. The two datasets used during the competition are first described as Pascal Part 116 and ADE20K Part 234. Pascal Part dataset is an extension of the Pascal VOC 2010 dataset, further annotating objects part masks. Pascal Part 116 is a more practical version of Pascal Part, where some over-segmentation parts are merged. Pascal Part 116 includes a total of 116 object part classes across 20 object classes. ADE20K dataset provides open-ended annotations of 847 objects and 1,000 plus parts, following the WordNet hierarchy. ADE20K Part 234 only keeps the objects which have more than one frequently annotated part over 100 occurrences, and the parts which have more than 10 occurrences. To reduce noise in the annotations, duplicated parts have been manually merged. Our team participated in Track 1 and Track 2 in this competition, according to the requirements of the competition given a natural image and a set of candidate object parts described by text labels, accurately assigning a label to each pixel. In Track 1, we train the OV parts model on the training set of Pascal Part 116 and test it on the test set of Pascal Part 116. In Track 2, we train the OV parts model on the ADE20K2234 training set and test it on the Pascal Part 116 test set. Our solution to the whole task is shown in figure. For the segmentation results of the original baseline model, the results are first visualized and analyzed, then pre-processed for the background classes, and finally, model fusion is performed according to the segmentation effects of the different models to achieve complementary details and obtain the final results. The key to this task is to exploit the potential of the existing base model in solving OV parts and thus accurately assign a label to each pixel. In addition to this, the segmentation model should be able to handle classes outside of the training vocabulary at object level and part level during inference. Therefore, we first choose to train the existing model under different configurations to obtain different learning results under different configuration adjustments. Analyze the details of different models and training results through visualization. Merge the segmentation results of different objects by further pre-processing the background classes to integrate the results, and based on the trade-offs between different segmentation effects, further highlight or weaken the details of the fights. Segmentation effects and their final effect merging, realizing the purpose of complementing the advantages and disadvantages between different models, and finally obtaining excellent segmentation results. Based on the method in the existing baseline model OV parts for inferential segmentation of the race test set, according to the segmentation results, show that the zero-shot setting in the ClipSeg model has the best segmentation results. So we fine-tuned the model and trained it on the NVIDIA GeForce RTX 4090. And by using different training configurations, we obtained segmentation results of two different result areas. The results were tested. Only 33.95 and 34.38 scores did not reach the original segmentation scores in 8 GPUs, analyzed maybe due to the existence of the number of graphics cards and batch size and LR differences. However, the results were further visualized subsequently, and the segmentation was better on some of the images, so it was also put into use subsequently. According to the existing segmentation results of different models and different training parameters of the same model, we visualize the different categories separately and find that the background category exists in the same image according to different objects divided into multiple background category annotations. So we firstly post-process the segmentation visualization results and merge the background category annotations of the same image as shown in this figure. According to the existing post-processing segmentation results of different models and the same model with different training parameters, we visualize the results for different categories separately, and the obtained visualization results are shown in figure. And immediately after that, we analyze the segmentation advantages and disadvantages of the different models, although the segmentation category coverage of ZSSEGA Plus is the highest. But due to having a low detail correct rate, it will be in part of the categories with the ClipSeg has moderate segmentation category coverage and high recognition accuracy during category segmentation. So we use the category segmentation results of this model as the final category segmentation results. For the existing categories, the CatSeg model segmentation has a high degree of boundary clarity and target integrity, as well as a certain degree of recognition. Therefore, we weigh the existing segmentation results for different needs, set 4 different weights, fuse the results, and finally add the fused results for different needs to get the final results. We used the above method to get first place in track 1 and third in track 2. Thanks for your listening.
Oh, okay. I think, Jihu, can you share your screen?
Yes.
Okay.
Can you see my screen?
Yes, yes.
Yes. Okay. Good afternoon, everyone. I'm Jio Choi from KAIST. This work was done with another first contributor, Sonu Lee, and our teammates. First of all, thank you all organizers for this challenge, and thank you for inviting us to this presentation. We appreciate this opportunity to share our work. In this talk, I'm going to briefly introduce our team solution for this challenge. To begin with, our team solution achieved second place in both track 1 and track 2 of this challenge, which are the cross-category settings and cross-dataset settings. Open vocabulary part segmentation is a challenging task since parts are often smaller and more diverse, which requires a broader spectrum of information and accurate identification. To address this challenge, the baseline method ClipSeg has leveraged a vision language model such as Clip. Despite the progress, current state-of-the-art OVPS method struggle with generalization of object and often fail to predict less common or smaller parts. These are some failure cases of VL parts and ClipSeg of OV parts, where sheep's ears are located inside a dog object and missing smaller parts like tail. Our approach aims to overcome this issue by utilizing object-level context with generalized parts. Our method interprets a part as a common structural component across different object categories, and also by integrating the context of the object, we can achieve more accurate segmentation result. For instance, if we train our model on a cat's torso and disjointly learn object-level instance cat and part-level instance torso, the model can better inference the torso of an unseen object, which by applying the generalized torso information trained with the base category. This is the overview of our method. We use the modified Clip architecture to parse object-specific part category names into object-level and part-level component. Similar to ClipSeg, these category name embeddings are then transformed into Clip embeddings and combined with the image feature using film. We reconstruct the object-specific part embedding from this generalized part and object embedding. By refining them, we can produce final segmentation prediction of object-specific part.
Our approach ensures comprehensive guidance by leveraging supervision of object-specific part, the entire object, and generalized part. The multi-level supervision enhances our model's capability to distinguish and generalize various parts, leading to improved segmentation accuracy for unseen categories. We compared the MIOU and harmonic IOU of the proposed method with the provided baseline ClipSec. In track 1 and 2, the proposed method part ClipSec showed a significant improvement over the baseline, which is 10.7% and 12.2% improvement, respectively. In addition to quantitative assessment, we also explore qualitative difference between the two methods. The visualization displayed here shows segmentation output from both ClipSec and part ClipSec compared with the ground truth. From the image, you may see that part ClipSec captures more diverse labels such as dog's ear and dog's eye. However, it is noticed that there are some samples where part ClipSec still miss the parts such as muzzle. And yes, there are some more qualitative results with object-like cars. Part ClipSec significantly reduced the misclassification of class label across different parts of the vehicles, resulting in more accurate and consistent segmentation. In conclusion, part ClipSec is a novel framework designed for open vocabulary part segmentation. By leveraging generalized part and object level guidance, we address generalization issue and improve segmentation accuracy for unseen parts. Our approach achieved noticeable improvement and achieved second place in both track 1 and track 2 of this challenge. And we actually recently released a preprint on the archive. Please feel free to refer to this for more information. And thank you for your attention. And for further information and details, please feel free to reach us by email. Thank you very much.
Okay, thank you.
Thank you.
Okay. The 13, Yunhan, can you share screen?
Okay.
Yes, I can see the sharing.
Okay.
No, maybe you should try another one because they cannot see full screen. So Floria first. Make it yes. Full screen. Sorry. No, share screen. Try.
It's not correct.
It's not loading correctly, so do not show the Microsoft. Try to share screen.
Okay, I just share this one. This.
There you go.
Yeah, okay. It is an honor to give a presentation here. I'm Yunhan from the University of Hong Kong. I will first introduce our method for OV parts
challenge and then talk about our further extension to 3D space for 3D part segmentation. As we know, segment anything model is able to produce high quality object masks from input prompts such as points or boxes, and it can be used to generate masks for all objects in an image. So the first stage of our work is to generate part mask proposals using segment anything model for an image in the test site. We first crop the object from the image with the mask, and then use mask generator, which inputs dense point prompts to Sun, and then filter fine-grained part masks with confidential value. Then we will get several high-quality fine-grained part masks. We then use some post-processing methods to filter and merge these masks. We first remove invalid masks, which have no overlap with valid regions or have more than 10% overlap with background regions. Next, then we remove redundant masks. If the IOU with any existing mask is greater than 97%, the mask is considered redundant. Next, we sort the mask from coarse-grained to fine-grained, assigning overlapping pixels to smaller regions and remove them from larger regions. After this, each pixel will be assigned a single part index. After obtaining part segmentation of an object, we further utilize GPT-4o to generate semantic labels. For each proposed part mask, we highlight it with a red circle and input it into GPT-4o with text prompts. And then we can get the label for that part. After performing this option on each part of an object, we can obtain the semantic segmentation result of the entire object. Here we show the final quantitative results on track 2, which we achieve an improved performance by around 9% compared to fine-tuned model on datasets other than Pascal part 116. But there's still a performance gap compared to fine-tuned models on Pascal part 116. We further extend this method to 3D space for 3D part segmentation, because 3D part segmentation is an important task, which is essential for robotics, controllable or computational 3D generation, and 3D editing. We aim to figure out whether can we utilize SAM and multimodal IOM to facilitate 3D part segmentation. There are 3 main challenges of 3D part segmentation. The first one is how to generalize to open world 3D objects without 3D part annotations, because collecting 3D part annotations is time consuming and costly. We don't have enough 3D part annotations data to train a big 3D part segmentation model. Second one is how to leverage 3D priors from unlabeled 3D shapes, because we have large-scale unlabeled 3D datasets, such as Observers, Observers XL, and Omni Object 3D. The third challenge is how to define the ambiguity of 3D parts. It is challenging to have a clear definition of parts of an object, so how to control the granularity of segmentation is also a challenge. To tackle these challenges, we propose 3D SEP, segment any part in 3D objects. We can segment 3D object parts at multi-granularities with zero-shot generalization. As shown, it can also handle complex 3D objects. We also try some simple editing applications with our part segmentation results, and we will further explore more applications for 3D generation. This is the pipeline of 3D SEP, mainly divided into 3 parts: large-scale pre-training, sample-specific fine-tuning, and semantic querying with multimodal LLMs. The first step is large-scale pre-training. To distill 2D visual features to 3D backbone, we sample the meshes in large-scale 3D dataset into point clouds and encode them with the 3D backbone to get 3D features. The dataset we use is Observers, and we modify an effectively 3D backbone point transformer V3 as our encoder to adapt to object level. We then encode multi-view renderings with DynoV2 to get 2D visual features. With rendering depth and camera poses, we can calculate the mapping between 3D point clouds and 2D pixels so that we can distill 2D visual features to 3D backbone. Then for each 3D object, we can utilize our pre-trained 3D backbone to encode point clouds effectively, and only need to train lightweight MLPs to generate segmentation or 3D features. We use SAM to generate multi-scale 2D segmentation masks from multi-view renderings and assign each mask a 3D space scale, which is also a control value inputted into the model. Then we sample pixels on 2D segmentation masks and use a contrastive loss to train lightweight MLPs. Then we can get 3D part segmentation results, which are multi-view consistent and multi-granularity controlled by 3D space control. After training, we can obtain segmentation-aware 3D features conditioned on a scale value, and then use clustering algorithm to segment point clouds into several parts, and can also get the mesh segmentation results voted by point clouds. Then for each 3D part, we highlight it in the 2D renderings and generate semantic description with multimodal LLM. For example, the multimodal LLM generates the description like the right foot or the right shoe. There are some visualization of multi-granularity 3D part segmentation results of our model. With smaller scales, value input, the segmentation results become more fine-grained, so we can control the granularity of part segmentation. There are more results to demonstrate the performance of our model on different 3D representations, including point clouds and meshes. There are some editing applications, including part material editing. We can change the material of car windows, and part shape editing and animation. We can segment the chimney and modify its position or let the fine rotate. And click-based hierarchical segmentation. By clicking on the object, we can obtain the hierarchical segmentation result controlled by the scale. We will further explore more applications in different fields. Our codes will be coming soon at this GitHub link, and thank you for listening. Thank you.
Okay, thank you. Okay, thanks for the insights and innovations from our participant teams. Finally, I want to summarize 2 key findings from these submissions. Firstly, as objects provide important context for parts and have much more annotated data than parts. I think it's important to use the learned representations from pre-trained object segmentation models and to effectively adapt the object models for part segmentation. Appropriate fine-tuning techniques are also very important. And the second thing is, we can say that even using the most advanced foundation models like Segment Anything model and GPT-4, there's still a significant performance gap compared to the supervised models. I think it's mainly because that although the vision foundation models like them can provide very accurate and fine-grained masks, but achieving part segmentation with controlled granularity by incorporating language context is still an unsolved problem. So for future work, I think bridging this gap will need more research and development. But I still think it is a very promising direction to further explore and optimize the integration of vision foundation models with multimodal large language models to achieve more robust and context-aware path segmentation and to enhance controlled granularity. I wish to make OVPaths more adaptable to various applications and extensions, such as 3D. Okay, thank you. I think that's all. Okay, thank you for joining today's presentation for our OVPath challenge. Okay.
Thank you, Mon, and thanks all the team for sharing the results.
Okay.
All right, let's move on to the third challenge.
Oh, sure. Okay. Object detection is a cornerstone for various real-world applications and has been extensively explored for years. It gradually goes from a closed set, fully supervised setting to a more applicable and challenging open world scenarios. And with continuous development, the object detection dataset undergo iterations. Examples including Pascal, Coco, OpenImages, Elvis, and more, each designed to meet the ever-updating requirements. However, compared to image classification, object detection datasets have a much smaller number of classes. For example, Elvis has around 1,000 classes. In contrast, the classification dataset with largest vocabulary, the Bamboo dataset, has a vocabulary that is 100 times larger. So the dataset with limited classes are insufficient for training and evaluating detectors in the open world. So accordingly, we propose V3Dat, a vast vocabulary visual detection dataset with 3 appealing properties. The first one is vast vocabulary. It contains over 30,000 categories on real-world images. And the second is hierarchical category organization. The vast vocabulary of V3Dat is organized by a category tree. And the third one is rich annotations. It is composed of precisely annotated boxes and category descriptions. This table presents a detailed comparison of various datasets. Notably, our dataset has much more categories, extending others by more than 1 order of magnitude. V3Dat has a suitable amount of images and boxes, sufficient to ensure the reliability of experiments without huge training cost. Furthermore, the classes of V3Dat are organized by a well-designed category tree, and this tree offers insights for recognizing numerous classes and exploring category relationships. We also offer detailed information for each class, including class name, object-centric example image, and descriptions crafted by GPT-4 and GPT-4 Vision. This vision language knowledge is crucial for open world perception. Notably, visual prior is crucial for accurate category descriptions. For example, without the example image, the GPT-4 describes spring as a season, while with the example image, GPT-4 Vision can correctly describe it as a mechanical device. Finally, we split the images into 3 sets for training, validating, and testing. And the test site annotations are held out for our V3Dat challenge. There are some visualizations of annotations in complex scenes and fine-grained categories. Based on our dataset, V3Dat challenge invites visual perception experts to advance the boundaries of object detection. There are 2 tracks in our challenge. The first track is the vast vocabulary object detection, which provides an arena for different supervised learning techniques in extremely large number of classes. And in this track 1, the model can be trained on the train set of V3Dat and other public academic datasets. But the submitted technical report should clarify the used datasets. The final performance is evaluated on the test set of V3Dat with the AP metric as in COCO benchmark. And the second track is open vocabulary object detection. This track splits all classes into base class and novel class. Detectors are expected to detect objects of both base and novel classes. For the base split, the complete annotations are given during the training. And for the novel split, only class information is given, including a name, a class description, and an object-centric example image. And we prepare a subset of train split for this OAD track and with only base class annotations. The evaluation is performed on both base and novel classes, and the final AP is a weighted sum of AP base and AP novel. Finally, we have 20 registered teams and 68 valid submissions. Those 2 tables show the entries with performance higher than the provided host baselines. The top 3 teams are winners in each track. For the track 1, the first place is the team CZM 369 from the Tsinghua University. And the second place is the team LC Meng from Fudan University and Microsoft Research. And the third place is the team TCSVT from the University of Science and Technology of China, Zhejiang University, Northwestern Technical University, and Northwest University. Congratulations. And for the track 2, the first place is the team LC Meng from Fudan University and Microsoft Research. The second place is the TC SVT from the University of Science and Technology of China, Zhejiang University, Northwestern Polytechnical University, and Northwest University. And the third place is the Team Innovation from Tsinghua University. Congratulations. We invite the winners to introduce their solutions. The first one is the team Alcimon from Fudan University and Microsoft Research. They win the first place in track 2 and the second place in track 1. Welcome.
Okay. Thanks, Jesse. I'm Ling Chengwang. I'm excited to share our solution, real-time Dino FocalNet for V3DAT. This work is collaborated with Yao Wenhao Yao, Si Hongwu, Jian Weiyang, Zhineng Chen, Zhu Xianwu, and Yu Gangjiang. Our solution built upon our previous work, reset, and achieved first place in the OVD track and the second place in the supervised track. Here is the outline. It includes a dataset overview of our solution and the experiment results. And the main challenge lies in object classification for vast vocabulary and proposal regression for high-resolution images. To address this challenge, we propose our method, Rich-Sam Dino and FocalNet. We developed a strong baseline and extended to open vocabulary detection by aligning the prototype embeddings for classification. The first feature of V3DAT is its vast vocabulary. Specifically, it has more than 10,000 categories with which is more than 100 times category in COCO and 10 times category in LWIS. Due to this vast vocabulary, we found many previous training techniques used in LWIS, such as RFS and the federated laws, do not fit well for V3DAT. As shown in this table, we conduct an ablation study on the threshold of RFS, but it results only a minor improvement of even performance drops. We also conduct ablation on federated, a common used trick of fed loss, but unfortunately it's failed in the V3DAT. Another challenge is the Boss regression of high-resolution inputs. It's challenging to cover a dense object and achieve a high recall rate. Okay. Based on this challenge, we developed our framework, namely Rich-Sam Dino FocalNet. Given a classic detector pipeline, we utilized Dino and FocalNet in our framework, and we apply Object 365 pre-training for improved performance. Additionally, we proposed a simple but effective prototype alignment method to convert closed set classification into open set classification. Here we previous experiments on model evolution of LWIS dataset. Using Dino as a strong detector, the backbone plays an important role in the final performance. When we switch from ResNet to SwinTiny under a comparable flops and increase the model size of Swin, the performance consistently improved. At the large model size, we replace the Swin large with the FocalNet large, resulting further performance improvement. Finally, after scaling up the FocalNet size to the huge and introduced Object 3 365 pre-training, the model achieved the best performance on LOS. Therefore, we directly applied the FocalNet huge as backbone and the Object 365 pre-trained rich-time Dino as our detector. To convert to further convert the traditional closed-site classification into open-site classification, we propose a simple but effective alignment-based classification method that includes both region language prototypes for classification. Specifically, we encode the given image, the given object-centric image, example image to obtain the visual embedding. We further increase the number of images by introducing crop the image from the training set and whole image from the ImageNet. We encode the GP4V description as a language prototypes and maintain a closed-site classifier for supervised setting. Finally, we align the object features with this prototype embedding to obtain classification logics. Here is the detail. We utilize OpenAI clip large for vision encoding and long clip large for the text encoding. We also found that increase the number of prototype image improves the performance. In our final summation, we utilize approximately 100 images per category using only the provided example image and the ImageNet image for the novel categories. Here are our final results. Without sophisticated training scripts, we achieved APO 53.1 under the supervised setting with approximately 80% recall. For the open vocabulary detection, we achieved a novel APO 22.9 and a novel APO 15. We used the TIDE toolkit to analyze our detection errors in the supervised setting, as shown in the figure. And the errors mainly stem from the object classification subtask. This further highlights the challenge of classifying objects within a vast vocabulary. Inclusion equipped with a strong detector, and strong backbone and extensive pre-training. Our rich-time Dino FocalNet achieved outstanding performance on V3DAT with a high proposal recall. However, the main detection error persists in the classification subtask, underscoring the challenges of classifying within a vast vocabulary. Looking forward, leveraging classification data sets to enhance detection performance, especially the object classification for both the open vocabulary detection and the supervised detection, is a logical step. We have already explored the pipeline and that incorporated inject as acquire data for LOS long-tail detection. And this approach should be further developed for V3DAT. Thanks for your listening. We will release the training code and checkpoint in our recent repo. Feel free to ask me any questions.
Any questions? Okay, thank you. Okay, sure. The team CZM369 recorded a video to explain their solution. They win the first place in the track 1.
Hello everyone, my name is Zeming Chen. I graduate with a master degree of computer technology from Tsinghua University, and my advisor is Associate Professor Zhi Wang. Our first place solution is called mixed pseudo labels based on CodeETR. As we all know, V3DAT significantly increased the number of categories before then than previous data sets. But generally, more categories requires more samples per category to ensure performance. But we can see the average number of images and annotations per category in VSANDAT is too slow. So it's increased the difficulty to train a detector on VSANDAT. COCO is a famous benchmark on detection. In fact, methods achieving over 60 MAP on COCO usually use Object 365 pre-train, but this shows limited benefits on the V3DAT dataset. One key difference is that the former fine-tuned from 6065 to 18 classes, while the latter is from 365 to 13,029 classes. Analysis of datasets and exciting methods reveals V3DAT lacks sufficient samples per category, and fine-tuning with Object 365 does not align well with V3DAT detailed category space. So surprisingly, semi-surprise learning could solve this problem. We use V3DAT as a labeled dataset and Object 365 as an unlabeled dataset for semi-surprise training on the pre-trained Object 365 model. The model generates pseudo-labels for Object 365 using V3DAT's category space, enhancing sample availability for each category and aligning it with the pre-trained with visual representations. The method we use is MISPL. MISPL is a universal semi-surprise object detection framework, so we can choose the CoDTR as a detector, which is the SOTA detector on COCO benchmark. First, we duplicate the CoDTR, which has already been pre-trained on Object 365 into two copies, serving as the teacher model and the student model. We use the teacher model to predict pseudo-labels on weakly augmented unlabeled images, and then we apply strong augmentations on the same unlabeled images and mix the images and their pseudo-labels to get mixed pseudo-labeled images. We use this mixed pseudo-labeled images from Object 365 and labeled images from V3DAT to train the student model, and then apply the student's parameters EMA to teacher model, so the teacher could be optimized with the student. In addition, the CoDTR with the 3 large backbone and 5-scale LPN is too huge, and semi-surprise learning also required to calculate labeled and unlabeled loss within a batch. So we use gradient accumulation. We calculate loss in 3 iterations for labeled images and mix-up images and mosaic images. And we just EMA frequency to keep consistency with the students' gradient update. Let me explain why the MISPL work. Besides the relationship between pseudo-labels and samples, we can identify TP, LP, TN, and FN, true positive and false negative. Using a fixed high threshold, most IP sample can be filtered out. Look at the picture. The x-axis represents gradient norm, and the y-axis represents the number of samples. We can see the blue is above yellow, which means mix-up could provide more high gradient norm or TP samples, which is benefit to model. As for the FN sample, we can see the yellow is above blue, which means the mix-up could reduce the number of high-grade gradient norm or FN samples, which means reduce the negative effective of missing detection. And in addition, Massacre provides more pseudo box for small objects, increasing the number of TP samples for small objects, while also reducing the size of missed detection because the image is small, so the missed object is also small, thereby decreasing the number of FN samples. In visualization, we can see there is a zebra. The green box means it's detected correctly. It represents TP sample. We can see stronger augmentation results in a higher gradient response, and mix-up could increase the response further. Meanwhile, we can see the picture C. There is a dog behind the rearing. The red box means missing detection. So we can see the stronger augmentation could reduce the FN samples gradient response, and the mix-up could reduce the response further. It seems that it totally disappeared. In conclusion, we employed the semi-surprise object detection framework, MixPL, and the SOTA detector code ETR to leverage the complementary of V3DAT and Object 365. And this approach utilizes both the detailed categorized space of V3DAT and the large-scale annotated previews of Object 365 for joint model training and get a great score of 54.5 MAP. But since we did not utilize the class tree of V3DAT and not address the long tails issue, so there is substantial room for performance improvement and research potential on this task. We hope our approach could inspire you. Thank you for listening. Hello, everyone.
Okay, and the team TC SVT also recorded a video to explain their solution, and they win the third place in the track 1 and the second place in the track 2. There's their video.
Hello, everyone. I'm very pleased to share our achievement in the challenge of vast vocabulary virtual detection. At this CVPR workshop, our team achieved third place in the supervised track 1 and the second place in the OVD track 2. I'm Bo Songchai, and it is my honor to represent our team to present and share our work. In the following presentation, I will cover 4 main aspects. First, I will provide basic information, briefly introducing our team and background. Secondly, I will explain the significance of this competition and its importance in the field of virtual detection. Finally, I will provide a detailed introduction and analyze our method and experimental results in track 1 and track 2. First, let me introduce our team members. I'm Bo Songchai, currently a PhD student at the College of Computer Science, Zhejiang University, affiliated with the State Key Lab of Brain-Machine Intelligence. My research focused on brain-inspired computing and computer vision. Peiqi Wu is currently studying at the Department of Electronic Engineering and Information Science, University of Science and Technology of China. Our team also includes several excellent PhD students, Longquan Yan, Zeyu Wang, Qifan Zhou, and Boning Wang. In this competition, Professor Xuan Nie provided us with meticulous guidance. His extensive experience is crucial to our success. He is an associate professor at the School of Software, Northwestern Polytechnical University, with research interests in computer vision and remote sensing. With the continuous development of the field of computer vision, object detection as a crucial component has made significant progress. Traditional object detection tasks usually focus on predefined set of categories, such as Pascal VOC and MS COCO datasets. Although these datasets provide rich annotated data, the number and the types of categories are still limited. These datasets fail to encompass the complex and diverse object categories found in the real world, thereby restricting the generalization of detection system in real-world scenario. The V3-DAT challenge aims to overcome a limitation of traditional object detection datasets by constructing a large-scale dataset with over 13,000 categories. This initiative not only better reflects the diversity of objects in the real world, but also provides an important experimental platform for the research and development of open vocabulary object detection. It is organized using a hierarchical category tree structure, detailing the inclusion relationship between categories. The dataset includes precisely annotated object bounding box in 245,000 images, and each category is accomplished by expert description written by human specialists and ChatGPT. Track-1 primarily evaluates supervised learning-based object detection models trained and tested on the entire V3-DAT dataset consisting of 13,204 categories. Participants can use public available academic dataset but are prohibited from using V3-DAT validation and test sets for training. Track-2 divides V3-DAT into base categories and novel categories, requiring detectors to accelerate identify objects from both segments. Base category comes from complete annotation information, while novel categories provide only category name, description, and example image of objects. The official benchmark models for this computation are listed in the table below. The first 10 models are based on the detection framework, while the last 2 are based on Detection2. We select the 2 best performing models for the subsequent testing and computation. First, we conduct various conventional supervised object detection improvements for Track-1. These include adjustments to the model structure, such as replacing FPN with PAFPN. Path aggregation FPN enhance the interaction and integration of multi-skill feature by introducing a path aggregation mechanism within the feature pyramid network. Additionally, we implement various data augmentation strategy to enhance the generalization capability of the model. Adjusting the loss function was also a key part of optimization efforts, particularly through the introduction of generalized focal loss and the distance in IOU loss. These novel loss function better balance the weight between positive and negative samples when handling object detection tasks. As shown in Table 2, after trying various methods, we find that while some improvements seem effective, they don't achieve the expected results. To further enhance the model's performance, we turn to the EVA model based on Detection2. This model is based on CLIP and employs masked image modeling to reconstruct image text aligned visual feature generated by CLIP, achieving strong generalization performance. CLIP outstanding performance stems from its training method, which integrates visual and language information, enables the model to efficiently understand and infer image content. The design of EVA model relies not only on adjustment to its structure, but more important to an innovative training method and the effective utilization of pre-trained models. In construct, our attempt to achieve significant in the V3-DAT challenge by simply modify and design model structure are unsuccessful. These findings suggest that feature research and improvement direction should focus more on innovation training strategy and deep integration of model pre-training. We submit a baseline-based EVA and achieved a 3rd place on Track-1. As shown in the figure, we visualize the distribution of class and samples count in the dataset, revealing an uneven distribution among classes. This obviously helps explain the efficiency of GFL loss. Following the requirements of Track-2 from the competition organizers, we trained our improved KIST RCN on OVD-based class data. We approach the track 2 as a supervised object detection task without extensive experiments, achieving a second-place result. For further tasks, we plan to employ the large language model to enhance the model's ability to learn textual features in a multimodal context. Our success can be attributed to the rich variety of classes and hierarchical annotations in the region. V3 datasets, which provide diverse semantic information. Coupled with excellent detectors and datasets, our model demonstrates considerable generalization capability. Implement our model using PyTorch 2.1.0 and conduct our experiments on a system with 4 H100 GPUs, using a batch size of 48. We use Adam W with a learning rate of 0.001. We sincerely thank the CCNT laboratory at Zhejiang University for their strong support in this competition. We appreciate all teammates for their hard work and contribution. Special thanks to Professor Xuan Nie for his careful guidance and support throughout the competition. The following archive link provides a detailed presentation for our experimental details. We hope our experience and findings can provide some insights for you. Thank you all for listening. Hello, everyone.
In summary, first, the open vocabulary object detection is still far from being solved. There, we can see here, there is a significant gap between the supervised performance and the open vocabulary object detection. And the winner of V3 track 1 achieved an average precision of 15.4, while the performance in the track 2 for novel classes was only 16. And the second is leveraging both visual and language priors is a promising approach for open vocabulary object detection. I believe that leveraging the generalizability of multimodal large language model will further advance this field. And I will thank all organizers in the V3 Challenge Visual Perception While Learning in an Open World workshop, and our sponsors, Shanghai AI Laboratory, the Chinese University of Hong Kong, and Shanghai Jiao Tong University. And the technical report of winning entries is now available on archive. You can also scan the QR code of V3 homepage for more information about the challenge and the dataset. Thank you for your attention. Yes.
No. All right, I know it's getting late, but there is just one more thing left to do before we wrap up, and that is to thank all the people that made this workshop possible. So you know, in just one day, we've heard from 6 of the leaders in the field of open world vision, and we've heard from some of the 4 challenges and the competitors, and some of the innovative solutions they have to a variety of problems within open world perception. I'd first like to thank all of the speakers that spent time to help lead the discussion on open world perception. The goals of this workshop were pretty simple. There are 4 things we wanted to accomplish. We wanted to connect people, identify new opportunities, exchange ideas, and understand existing challenges. And by all metrics, I think we solved all of these 4 goals. There are many organizers involved in making this happen, but I'd specifically like to highlight Shu Kong, who unfortunately could not be here. He is sort of the leader of this workshop. He's been hosting this for 4 consecutive years, and this workshop would not have been possible without him. More importantly, we also have a number of challenge organizers, and there are simply too many to highlight individually. But I think this should show you that it really takes the computer vision village to put the show on. And lastly, I'd like to highlight our 3 on-site coordinators who throughout the day, their tireless work is what really made this workshop what it is. So with that, I'd like to conclude by letting everyone know that a recording of this workshop will be available on YouTube, and we have a link to the workshop website where you can take a look at today's program and revisit the recording. So we'll have a link to the recording there. And with that, I'd like to conclude by thanking everyone for attending today's workshop, and I hope to see everyone again at CVPR 2025 in Nashville.